Okay. What we have commonly described as relativity and the formulas behind Einstein's work is the most detailed description of the thing that we refer to as gravity. We do not know the cause.
Which is an effect.
Correct. We have a
And
description
the
of
cause,
effect.
the cause of
Is that Nick?
the cause of this effect is what?
We don't know.
No, that's not what Einstein says, is it?
That's exactly what Einstein says. He describes the effects that he's seeing as being attributed to curvature in space-time, but we don't know this for a fact. We just say that the accurate description that he gives is plausible and falls in line with his theory.
But it's an effect.
Yes.
How can an effect affect something else? It can't. An effect is the end of the line. An effect does not have an affect on anything else.
Right. So what we're seeing is stuff moving in a predictable fashion.
Which
and
is
what
an
we're
effect.
Yes. And all Einstein is doing is describing that effect. He's not claiming any knowledge of a cause.
But the gravity is the effect.
Yes.
So what is the affect to cause the effect?
We don't know.
So you're hypothesizing. It's a theory. You have no clue.
All of science is a theory. Like, explain to me how magnetism works.
So you're putting together. You are stating this as a fact when you don't know anything.
Right. Okay. You're mixing things here, right? So
but hang on. You are saying that gravity is the cause of things to fall.
No, gravity is the name of an explanation we give to an observed effect.
Right. It's not a factual explanation. It's a theoretical explanation.
Right. So this is where you're conflating ideas.
Why is it taught as fact?
There is the law of gravitation, and then there is the theory of gravitation.
The law of gravitation is not a law. It is not a natural law.
Well, it is. The law of gravitation explains that when things are dropped, they fall to the ground. That is a law. That always happens. We've never observed that not happening. So it's an observed law. And there is documentation for that. And there has never been any science or any explanation anywhere that anyone said, well, I dropped a thing and it didn't do that. I think this is where a lot of flat earthers get mixed up. They conflate the law of gravity and the theory of gravity and the explanation with the actual mathematical fact of what actually happens. What is actually going on with what we call gravity. There's a mathematical formula that explains stuff falls at this rate for this supposed reason, but it's not known as being like the be all and end all description. We're just saying mathematically this fits.
So it's a mathematical model.
Sure, it's a model of an observation.
So there's nothing based in reality about it.
Well, it's a model of something we've observed in reality, yes.
So there's nothing in your model that is based in reality apart from an observation. The rest of it is a mathematical model. So
this comes back to what we were saying earlier, the colour blue.
I didn't hear that. I had to speak to somebody else. So
so I can tell you mathematically speaking or scientifically speaking that the colour blue is a specific frequency of light. But all I can say to that is...
Hang on. What's this got to do with gravity?
Because it's the same thing. You could tell me, well, I don't accept that light has different frequencies.
How can the colour blue be the same as explaining gravity?
Because you can turn around and say...
How has light frequency got anything to do with explaining gravity?
It's the same concept.
It's not the same concept at all. It's not. The colour blue is something we can see.
And gravity is something we can see.
No, it's not. No, it's not. You're putting a word to an effect that has a mathematical model, but no actual real-world proof.
Hang on a minute. So if I told you the sky was blue, you're saying that I'm just putting in a word there and it's meaningless.
I can see the sky is blue.
Right,
And
and you can see
the sky
things
isn't
fall
always
around.
blue. The sky isn't always blue.
Right, but you can also see that things fall to the ground, and we can say that's gravity.
But you are putting a mathematical model to explain your observation. Your mathematical model is not a real world explanation. It's a model made of numbers.
Yeah, and the reason why I use the colour blue is because there's a mathematical model or an explanation for the colour blue as
You
well.
can see the color blue.
You can see
The color.
gravity.
You can see an effect of your claim of gravity. Things fall to the ground.
You can see the effect of things that appear to be blue.
You can see the colour blue. Which bit of this don't you understand?
Yes, I can see the colour blue. I can see light that appears to be, in my interpretation, blue.
Because of the frequency of that light. The actual name is just the name we give to that colour.
Yeah, and the name of stuff falling to the ground is gravity.
Right. Gravity is an effect.
The colour blue is an effect.
No, the colour blue is visible. You can see the colour blue.
What?
Things falling to the floor are an effect.
So, if something is blue, that is the effect of blue light.
This is a red herring. We can see things are blue.
Yes,
Why are you continuing down this line?
because what you're seeing is an effect.
It's a non sequitur.
So you
know
accept,
what a non sequitur is?
yeah, and it's a fallacy that you're coming up with here.
Yeah, well, move on. It's a non sequitur.
So, okay, the mathematical description of stuff falling to the ground is fake, even though it's accurately correct.
You can build a mathematical model to say anything.
Yeah, but not any mathematical model is going to agree with reality.
Right, so you take what's observed and you build a mathematical model around it. What are you proving? Nothing.
We're proving that we've got an explanation of how the world around us works.
Yeah, but you don't prove gravity. Gravity is an effect.
Gravity is an observed effect.
Gravity is an observation. Correct. You build a mathematical model around an observation. The mathematical model does not prove the observation.
Hang on, I started this whole conversation by saying the mathematical formula that we have for gravity is the documented observed effect. And now you're telling me what?
You've built your mathematical model around the observation. So how can you, and then given that observation a name, so how can you expect the mathematical model not to fit the observation?
That's completely the point of it. That's why gravity is real, because that's exactly what it is.
You've built the mathematical model around the observation.
Not just one observation, all observations.
The observation is an effect. You have a mathematical model of an effect,
Yes.
and then you say, "Oh, our mathematical model fits this effect."
Yes.
It's circular reasoning.
No, it's not. It's
Yes,
reality.
it
It's a
is.
description of something that happens in reality.
Oh my life!
That's
How
like saying
can
I can't call
how
something
can you
blue just
not?
because it's blue.
How can you not see how circular your reasoning is?
So I can't call things blue because they are blue in reality.
You have taken an observation. Something falls to the floor. You've built a mathematical model around that observation and given it a name. Oh no, actually, the name is the observation. And then you're crazy, man. You're absolutely crazy.
This is crazy. I think
You're crazy.
we documented it. Brilliant.
Sorry?
Okay. A thing happened, we documented it. Great. Okay.
and then built a mathematical model to suit that observation.
That documentation is the documentation of the mathematical model is the documentation of the thing that we saw happen.
Which is an effect.
Yes, this is how science works. We document things that we see and we describe them mathematically.
So how can that effect have an affect on something else?
I don't understand why you need to be concerned with cause and effect. We're seeing an effect.
Your explanation of gravity, the definition of gravity is an effect.
Yes, an observed effect.
An effect cannot affect something else.
Yes, something affected stuff, and we saw an effect which we documented.
Right. Okay, and the affect of
Is
gravity
unknown.
Is, according to Einstein, the unequal distribution of mass.
Sure, that's an explanation.
Is the scientific explanation in the scientific world at the moment.
It's an explanation. What we use from a gravitational point of view.
This is the affect. The effect is gravity. Now, the effect of gravity cannot then affect something else.
You're stuck on terminology. You're playing the quantum eraser game.
Words have meanings. This is why we use words, to give things around us meaning. And if you don't understand those meanings and you don't like those meanings, that's not my problem.
So that the problem that you have,
my problem. I don't have a problem.
The problem that you have,
you don't understand the difference between an effect and an affect.
I do. And
no, obviously you don't.
So the issue that you've got here, right, is
I don't have an issue.
You think that gravity or some part of it is explaining the affect, and it isn't. It's just explaining the effect. And that's all that matters, because the effect is the thing that we're using in scientific or like engineering circles when we care about doing something with that piece of knowledge. The affect is irrelevant.
Finished your monologue?
Well, it's the first time I've been able to get a point out since I joined.
Right, the scientific world says that the affect of the effect of the unequal distribution of matter is gravity. It's an effect. The effect cannot affect something else. It's that simple.
In your interpretation, yes.
It's not my interpretation. It's the meanings of words. It's
relativity describes an effect. It has nothing to do with an affect.
Relativity is hypothetical.
Yes, the explanation for it is.
It's hypothetical.
The mathematical formula is documented effect in reality.
Mathematical formula is not real world. A mathematical model is not real world. Maths is not reality. Which bit
if you say so.
You seriously think maths is reality?
Like the entire world runs on mathematical and chemical knowledge of the world and the way that we describe the way the world works and how pretty much everything we have today is mathematically driven.
Hello, maths is not reality.
It's a description of, as I said earlier.
It's not reality.
It's a description of.
You can describe reality using maths.
Yes, which is what that's doing.
You cannot say maths is reality.
I didn't say that. You put that in my mouth.
I said maths is not reality, and you laughed at me.
Yes, because you're going round in circles.
You laughed at me when I said maths is not reality. So
because we'd already had that point.
That is implying that you think maths is reality because you think it's funny that I don't.
Right, now you're straw manning me.
So now I can laugh at you because you also think maths is not reality.
You're straw manning me.
Well, I'm just going by your reasoning and the
I have
way you laughed at me
right.
when I said
I have
maths is
not
not
once in
reality.
this conversation said that maths is reality. All I have said is
No,
that
no,
math is a description of
I
reality.
said maths is not reality, and you laughed at me. So tell me why you laughed at me.
Because it was like the third time you'd made that point in this conversation, and I'd already told you that that was not the case.
What, that maths is not reality is not the case.
Maths is not reality is the case.
Well, thank you. So we cannot
Brilliant.
live inside mathematical models.
We can use mathematical
We
models to
cannot
describe
live.
what we're going
We
to
cannot
see in the real
live
world.
inside mathematical models. Is my statement.
Sure, we don't live in a mathematical model,
We
no.
don't live in a mathematical model. So mathematical models can be used to describe things, but they're not actual reality.
Right.
Correct?
Maths is not reality, yes.
So
For the
you can model.
100th time.
You can model something, but it's not an actual factual.
It's a description of our observation, nothing more.
Thank you. It's a description, so it's not real in any way, shape, or form.
Right. So the point is,
Okay. Your explanation of gravity is a mathematical model. It's not real in any way, shape, or form.
it's the documented fact of something that happens in reality.
It is a mathematical model based on an observation.
Again, the colour blue.
The observation is the only thing that happens in the real world. The rest of it is a mathematical model, which you have just said is not reality.
Right. So if I say the sky is blue, your
The sky
argument
is
is blue
blue
isn't
because
blue.
we can see blue, and it is the name we give to that colour.
Right. Gravity is the name we give to shit fall into the ground.
Gravity is the name you give.
No, that's not how gravity
Just to the ground. What's that about?
That's not how gravity is defined. The name we give to gravity isn't shit fall into the ground. It goes further than
It's
that.
mass attracting mass. Yeah, I know. I'm trying to simplify because apparently this is a complicated conversation.
Mass
It isn't.
attracting mass.
It hasn't been mass attracting mass for 110
Well
years.
done, mate. You just dug yourself a really deep hole. Off you go, Tony.
Yeah, now we're talking about curvature in space-time according to relativity, etc., etc. Yeah, I get it.
No. You don't seem to get it because you cited gravity to be mass attracting mass, but that's not the current science for gravity.
Okay, go on then. School me.
Well, you tell me, if you think you know what gravity is, you could at least define it accurately within the current physics.
Well, see, this is the thing. We've gone round and round in circles. I began this conversation by explaining that what gravity is actually unknown. But what we attribute and call gravity is an effect. It's a mathematical effect that we have observed and documented.
Right, it's not a mathematical effect. It is an effect, but gravity is currently defined, and we are told what causes it in current physics.
You can disagree with me, that's fine, but
what?
But the math is the math, and the math is basically.
Do we live in a mathematical model?
The math is a description of something that actually happens in reality. So unless you're going to say the math doesn't agree with reality, then you have a
built
problem.
around an observation.
Hang on. Let's start with the agreed term for gravity. Let's have the definition for gravity, and then from there we can either go in whatever path or agree or disagree. But at least let's start with a common
I'm not going there because you're going to play the word game with me, and I don't want to play word games.
I'm asking you to define it for us, and let's see if you understand what the current definition for gravity is.
The definition, as I understand it, is, well, the most accurate definition is the formula that we use for relativity.
Yeah, define gravity, please.
No.
Relativity explains a thing that actually happens in reality.
No, it's defined. Gravity is defined. We have the definition and we know what causes it. Can you please cite the current physics for gravity?
The problem is that you're going to try and play the word game with me, and I'm not going down that route.
Just define gravity. For God, you're the one that came in here and wanted the bloody argument. Define what you're trying to argue.
How many times now? I keep referring you to the math, and I'm saying the math is gravity.
Gravity.
That is the definition.
Define.
What is the definition for gravity? Come on, spit it.
The math. Look at the math.
Right, maths is not a definition of gravity.
It's the observed effect that we've seen. That is as close.
That's not gravity. That's an attempt at defining gravity, but that's not what gravity is defined as. It's specific. If you don't know it, just say and I'll tell it to you.
We don't know what it is. We've got a lot of things that we just call gravity, but we don't know what it is.
What we do, it's defined for us and we know what causes it. If you don't know, just say and I'll tell you.
We don't know what causes it.
I actually told him. I told him about 10 minutes ago, Tony. I told him.
We don't know what causes it.
We do.
What did I tell you about 10 minutes ago? And you said, yeah, that's one of the causes. You
went down this whole effect thing.
What was it? No, what was it I told you that was one of the presumed... Well, you put presumed or scientific, one of... What was it? Come on. You can remember. It wasn't that long ago.
You went on some weird monologue between affect and effect, and I'm telling you the math is the description of the effect, and the math isn't wrong. So what's the problem?
Come on now. You can remember. It wasn't so long ago.
Don't try and straw man me.
What was the effect? What was the effect? Affect that causes the effect. Come on. No, Tony, we went there. We went there, Tony. So he does know.
Yeah, you were starting to presume an affect.
What was no? You agreed.
I told you we don't know what the affect is.
Yeah,
we know what the
agreed
effect
it was
is.
one of the what could be. Come on, what was the effect? What was the effect? Come on, you know it.
We don't know what the affect is.
We went there. We went there. Come on, little man. We went there.
Straw man away.
Come on, little man.
Right, hang on, guys. Gravity is defined. We know what gravity is, and we know what causes gravity because Einstein defined it for us. He told us what it is.
He gave us an explanation of his formula and how he derived it.
He defined it. He defined gravity, and he told us what the cause is.
Get down.
Yes, he gave us his definition of gravity.
No, it's the current definition for gravity. It's the current physics.
So come on, Mr. Physicist.
You
must.
If you can't do it, I'll do it for you, and let's move on.
He can do it, Tony, because like I say, we went there about 10 minutes ago. I need to get the countdown clock.
Go on then, what's your definition for gravity?
I don't have a definition for gravity. I do have my own view on it, but I'm asking for the current physics.
Whatever I say here, I'm going to be wrong because no flat earther agrees with the scientific definition.
It's not about agree or disagree. It's just about agreeing terms. If you're going to talk about gravity, we should at least start on a common ground, which is the current physics. And it is defined, and we do know what causes it in current physics. Can we have the definition or not?
Well, straight away we disagree because I don't think we do know what causes it.
How can we disagree when we haven't had a definition yet?
Because you're claiming we know what it is and what is the cause of gravity, and I'm saying we don't. So clearly you're reading from a different book.
Current physics defines gravity, and current physics tells us the cause. If you don't know it, just say, and I'll do it for you.
Current physics defines a formula that explains an effect that happens in the real world.
And what causes the effect?
We don't know.
Come on, little man. We went there about 10 minutes ago. You're getting really tedious.
We don't know.
You're getting tedious.
I'm going to keep repeating the same answer because it's not going to change. We don't know what causes it.
We do know it's defined.
Then clearly you know something I don't.
Well, you should go and read some physics books before you come here and start making the argument.
I'll tell him. I don't mind telling him as long as he just says I don't know. That's fine. Current definition for physics of gravity. It's the effect of the curvature of space-time caused by the uneven distribution of mass. So the uneven distribution of mass causes the effect of curvature of space-time. That is supposed to be gravity, right? That's the current physics. Now, I don't agree with that, but that is the current physics. So now that we've got that definition, do you agree or disagree with the definition?
I would say that that is the most accurate definition that we have, yes, but science doesn't claim that that is finite.
I never said that it was finite. I said that it was defined and we know what causes it. And that is the definition and we know the cause.
Right, but that definition doesn't describe a cause. Yeah,
it does. The cause is the uneven distribution of mass.
Sure, I mean, you can word it like that, but that doesn't define the cause.
I didn't word it like that. That's what Einstein worded it as.
If you can think... Okay, if you're thinking of gravity wells as basically being a hill that a ball is rolling down, so to speak, then sure, you can say the hill is the cause in a weird way. But science is a bit more nuanced than that, and therefore the hill isn't really the cause, if that makes sense. This is where there's been theories around things like Higgs bosons and stuff like that, which is why I say the cause is currently unknown, and any scientist worth their salt will tell you that.
It's not true. It is defined. Whether or not it's true is a different question, but the cause is defined by Einstein as the uneven distribution of mass. Now, you can disagree with that if you want, and I would agree with you that it's nonsense, but we need to have that as a common ground to start from, because if we can't start from a common ground, then there is no conversation.
So the issue here is that you're classing the curvature as being the cause.
No.
And I don't agree with that.
No. The cause is the uneven distribution of mass. The effect is the curvature of space-time.
Oh. I don't know what you mean by the uneven distribution of mass. I mean, you've got two masses, and you need to compute, for example, how long it's going to take one to collide with the other. We have a formula that explains that, and the explanation behind it is curvature in space-time, but the explanation is somewhat irrelevant as long as the formula tallies up with reality. That's my point.
But even if the formula correlates or tallies up with reality, correlation is not causation.
I would agree with that, yeah.
Right. So in that context, even though the current definition states that it's the only... Even you calculate that to give you an orbit, we'll just say orbit loosely, then does that mean that the cause of the orbit or the cause of anything that you're describing mathematically is actually what you're calculating? Or is it correlative? Because if it is correlative, then what we're asking really is how do we prove that planets are orbiting the way that we're told they are?
So I don't want to straw man or reword what you say, so let me get my understanding of what you're saying out, okay?
Yeah.
You're saying that we've observed one or two things happening, we've drawn some correlation, and then we've built some formula based on that correlation, and we're saying that's now fact, right?
Correct.
Right.
Correct.
I would say no, that's not the case.
Okay, so now we're talking about science, because if we're trying to prove that the cause of the effect is the correct mathematical expression that you're relying on, then we need to have some experimental application, don't we, for science to satisfy the definition of science? Because in science we need observation, but we need experiment too. Do you remember? Do you agree with that?
So the scientific method is an intricate and complex beast, and when you get people like... Well, let me finish my point, okay? So when you get people like, for example, Quantum Eraser coming out saying this is the scientific method, there's only one way to go about it, and that's the be-all and end-all, he's wrong, in my opinion. Because the way that the scientific method works is it's not like a guy sits down, does science, and out pops some, formula for reality. It doesn't work like that. And relativity is an interesting case because... Einstein wasn't proven right, essentially, until after he was long dead, because he proposed some experiments that he wasn't capable of doing.
So when you say experiments, would you agree that an experiment is a hypothesis test?
Hang on a minute, Tony. You said Einstein was proven right.
I know, I'm coming to it. I'm getting to it. I'm just leading.
Sorry, mate.
I'm leading.
Yeah.
So when you say he was proven right, do you agree that an experiment is a hypothesis test?
So let me explain what I mean first by the word prove. Okay, I don't mean it in the mathematical sense. So a mathematical proof is
Sure.
factually correct and is always right, essentially. When we
Yeah.
talk about scientific proof, we're talking about this is the most accurate version of events from reality that we can represent today. There's always means by which you can prove someone like Einstein wrong by coming up with a more accurate model. For example, we know for a fact that
No, not true. You can't prove somebody else wrong or right with a model because that's modeling. That's not science. You can model all day. You can model anything you want modeling. That doesn't make it true.
so, well, okay, Einstein to some extent proved Newton was wrong in that he was less accurate than himself.
What
But that
experiment did
doesn't,
you ever do? What
but that
experiment did
doesn't
you ever
make
do?
Newton wrong. So,
Yeah, but when you use the word prove, if Einstein proved Newton wrong, I'm going
yeah,
to immediately ask for what experiment did he do and what was proved in the experiment that was then claimed to be a proof that Newton was wrong.
so one example where Newton's formula falls down, but Einstein's relativity holds up, is in gravitational lensing. So in the example that was given was that he proposed an experiment whereby during a solar eclipse we could
Yeah.
see stars that were technically behind the sun, and we could
Okay.
see the effect of that gravitational lensing effectively bringing the stars back into our view by curving the light
What's
around
I
the
beeping?
gravity well. Sorry?
So there's so I'm sorry. Something happened in the background. Someone's beeping for attention. It's okay. Right. Okay. So we have the observed phenomena that stars appear to be visible when they should not be visible. That's the observed phenomena. Would you agree that that's an accurate representation?
So, yeah, Einstein's explanation of that was gravitational lensing.
Okay. So the hypothesis was the cause of the stars being visible when they shouldn't be was gravitational lensing. Is that a fair representation of what?
The
What you
effect that we would see would be gravitational lensing. The cause was presumed to be, shall we say, um, based on his theory of curvature in space-time, because the shortest distance between 2 points is obviously going to be a straight line, and the straight line on a curve is effectively a curve, if that makes sense.
Not really. Let's try and clarify. So, what did you? Because we've just agreed that the observed phenomena is stars appear to be visible when they should not be visible. So, the cause of that stars being visible is what? I would suggest it would be gravitational lensing, but if you don't agree, tell me what you think it should be.
So I would say that Einstein would describe that as the effect.
Okay.
What he believed, I guess, would have been what his cause would have been
The
the
pro-
curvature in space-time. Sure.
Okay, but the problem that you've got now is that you've got a conflict between your observed effect, which you just said would be gravitational lensing, and the observed phenomena, which was stars appear to be visible when they weren't previously visible. Them two should be the same thing in an experiment because your dependent variable is your observed phenomena because that's the effect that you believe that you know what's causing it, right? You can't
So
have
the thing,
what I'm saying is you can't have an observed phenomena which is stars appear to be visible when they shouldn't be if your dependent variable is something else completely because your dependent variable is the thing that you're trying to prove.
so the thing that you're trying to prove is the bending of light. So your independent variable is essentially the path of the light.
Okay, so the path of the light gives the effect that you can see the stars when they shouldn't be seen. Is that what you're saying?
Yes, and by the fact that that light is deemed to be curving because of gravitational lensing, or
Okay.
Einstein's definition would have been gravitational lensing effectively. What we're
Now
saying is that it
scientific
coincides with
fact.
his
There's
theory.
no real evidence
I
for
agree
it,
with
but
that.
it is
What you've just said
scientific
there is
fact.
correct. I agree.
Now,
So if
is
the observed
scientific
phenomena,
fact. There's no real evidence for it, but it is scientific fact.
who's playing that? So I agree that the observed phenomena is stars appear to be visible, and the cause of them. Didn't you say the cause was the bending of light?
So the
Is that what you said?
effect is the bending of light. The cause, as
Okay.
Einstein proposed, was gravitational lensing, i.e., curvature in space-time.
I would agree with that, and it was caused by what?
That's the thing that's largely unknown. So Einstein proposed that space-time curves, but he doesn't know why. That's the big
He does.
unanswered question for gravity at the moment.
He defines it. The cause of bending space-time is the uneven distribution of mass.
Yeah, so he talks about mass, and he basically says, okay, fine, mass is the cause to some extent, but then science looks at that and says, well, okay, what is it about mass that makes it bend space-time? And that's the thing that we don't know.
Okay,
So
but
Einstein is a partial explanation of the problem,
I
is the
can
issue.
accept that. I can accept that. Let's move on. So now we've got the observed phenomena, we've got the cause, which is the bending of the space-time, and we know from his definition for general relativity that it's the uneven distribution of mass. Now, however you want to interpret or describe or explain that, the next question for it to be science, that if it's going to be an experiment that proves Newton wrong, we need to know how did he manipulate that presumed cause to prove that it is the cause of the effect, rather than calculate and correlate. So what was done to manipulate the presumed cause to establish the cause and effect relationship? Or did he just do a bit of maths?
I feel like I partially understood that. I don't want to call you on word salad, but I would like to get some reiteration there.
Okay, so we agreed before that correlation is not causation with maths. But what I'm asking is, if we've just agreed the observed phenomena and we've agreed that the cause is bending of space-time, what is the independent variable to prove Newton wrong? Because you said that Einstein proved Newton wrong with this experiment. Now, I agree that there's an observed phenomena, and I agree that you've correctly identified the cause and the effect. The issue is, how did he prove it? Because I know that Einstein calculated it, and you're going to tell me.
So where Newton and Einstein, if you like, differentiate is in relativistic physics. So we're talking about light traveling over long distances, and we're showing that gravity has an effect on literally everything, including light. But Einstein couldn't, Newton couldn't have possibly known anything about the behavior of light in certainly the level of detail that we know it today, because obviously today we know that light is somewhat both a particle and a wave in terms of how it behaves. So there was no way that Newton could have understood the impact. And what Einstein was adding was the additional detail that, as well as kind of like regular mass that we're used to dealing with here on Earth, light at a galactic scale is also affected by this thing that we refer to as gravity.
Okay. Now, that's lovely, and that's a lovely story, and I'll just accept on face value that all of that is true. Okay, I don't agree with most of it, but I don't want to go on tangents. I want to stay on point. I want to go back to the part where we say that Einstein proved Newton wrong, because if Einstein proved Newton wrong, he must have done an experiment to demonstrate that Newton was incorrect. Now, we've got to the bit where we've got the observed phenomena, we've got the independent variable, we've got the dependent variable sorted. I'm at the point now where I say Einstein simply calculated and therefore correlated. But you've made the claim that it's an experiment that proved Newton wrong. And I want you to qualify that with where the experiment was performed, that there was an independent variable that was manipulated to prove a cause and effect relationship. Because we know that Einstein calculated this. He didn't do any kind of manipulation test. He calculated it. That makes it correlative. It doesn't prove Newton wrong. Mathematically, it might do because the maths always works out. But the word you used was proved. But it can't have proved him wrong because he's correlated mathematically. That's not proof in science.
Yeah, so what Einstein came up with was essentially just the mathematical model, and I would agree with you to some extent that he didn't himself directly actually take part in any experiment that proved him right, or more right than Newton, shall we say. So in that sense, Einstein was never able to prove relativity. Okay? But the reason why we accept relativity as being a more accurate description of gravity than what we had under Newtonian physics is that now that we've got things like, for example, better and higher quality telescopes, and we're moving into like radio telescopes and things, we can see that on a galactic scale, Newtonian physics just doesn't add up, whereas relativistic physics do add up in some situations, and those scenarios are things like gravitational lensing, and we can even see to the point that we're seeing like light bending around distant galaxies.
Okay, I've got two. Let me respond with two counters. Your opening line was this is how we accept that Einstein's relativity was correct, or words to that effect. I might have got it slightly wrong. Forgive me if I got that wrong, but you said something like, this is how we accept that Einstein's general relativity, would you agree, is a mathematical model?
In the same way that the Newtonian formula was as well. It was a mathematical explanation of something that was true.
But at least with Newton, when you have something and it's applying a force, you can measure forces and you can do stuff within scientific experiments to prove cause and effect. Now, whether or not you agree or disagree with the outcomes or whatever, what I'm saying is Newton's was capable of experimental application to test cause and effect. Whereas Einstein's is purely mathematical, it's conceptual. It's based around a mathematical model that we call space-time. Would you agree? Is that a fair description?
So on the basis that you can't, like, I don't know, build a planet in a lab and then orbit that around a star, basically. Yeah, because we can't reproduce stars in a lab,
I agree. But here's the thing, though. I do have 2 points, and this is the end of the first point. If we use any kind of mathematical model, by definition, relying on a mathematical model is a reification fallacy. It's fallacious reasoning because it's reification. You're relying on a model because you can't test it experimentally real world. Now, that is fallacious reasoning to justify a scientific endeavor. Not strong enough because it's reification. But the second point is that what was my second point? It'll come to me. It'll come back.
Do you want me to address the first one, and then we'll move on to your second point? So, I completely accept that if you just accept the mathematical model and rely on that, then yes, it is a reification fallacy. The problem is that that's not how science works, and this is where peer review and ongoing testing and observations and experiments come into play.
Okay, stop. I've got my second point. Let me get my second point. When you just said then that's not how science works, I'm going to cite Max Planck. Max Planck said that anything that doesn't have experiment is nothing more than poetry. Now, Einstein is a theoretical scientist. He's not a physics-based scientist. He's a theoretical scientist. He has a mathematical model that conceptualizes general relativity, and there's a shitload of complicated maths, which, let's be honest, nobody really understands but him. And nobody can really validate them to test to see whether or not they're true. We're just told that they're true. But let's just say that they are actually true. Max Planck said without experiment, it's just poetry. Now, Einstein is a theoretical physicist with a mathematical model that is reification. Max Planck says it's poetry. And I agree with that because there's no experiment. Now, we've just talked about the experiment for the light and stuff, and we haven't got an independent variable. And we've kind of agreed that he had a mathematical explanation. And when I say that that's a reification fallacy, that's the bit where we don't necessarily agree. But that point is important because you say this is where science and peer review papers and get involved. But that's the point where I go on a different angle and say, what application, what validity does that reification fallacy have in science? And the answer is it doesn't have any, because it hasn't got any experiment with it. It has to have experiment. So it takes us back to the original definition. Any definition of science includes the word experiment. So without experiment, what are you left with?
So where we agree is that Max Planck was right. Without experimentation, without verifying your proposed hypothesis, we can't say that any science is effectively valid. Where I think we're diverging is that you're either working under the assumption or you're stating categorically as a claim that we haven't been able to test relativity properly. Is that the divergence point, or am I missing the...
No, the divergent point is that when we've got Einstein with his mathematical model that I say is a reification fallacy because it doesn't have experimental application, at that point, we have to divert because you say, well, that's not how science works, and then start to justify how science works. And I say science requires experiment. So if without experiment, whatever arguments that you have about peer review and all that, and they may well be true, it still requires experiment. It pervades science. It's not something that you can dispense with because it doesn't suit because you're talking about planets at intergalactic scales that we can't comprehend. You've still got to have experiments. So we come back to Einstein's position that he is a theoretical physicist. Are we accepting that a theoretical physicist is able to demonstrate that we live the world in which he tells us we live, when one error mathematically in his model can totally transform the perception?
Yeah, so this is where the problem comes in, is that what Einstein is describing is gravity at essentially an intergalactic scale. And we're never going to be able to experiment on galaxies, are we? So
I agree.
So all we can do is observe the behavior of galaxies and observe the light that comes from them and say, does it fall in line with what we've understood from Einstein's predictions? And so far, since Einstein predicted what he predicted, Einstein has there's only been one real case where he's been wrong, and that's to do with the edge of black holes, effectively. And so we do know that Einstein is wrong at some level, but we're not quite sure how wrong he is and what it is that goes on with black holes that makes him wrong, if that makes sense. But
you describe this as one thing that we can do, but there is actually another thing that we can do to test whether or not Einstein's is possible in the first place. And it's really simple. You can look at the planets that we're told, the wandering stars, and you can say, right, that red one there, they tell us is Jupiter. And they describe Jupiter as a gas giant. Would you agree that's how they describe it?
Yeah, I think that's the common sort of description for Jupiter. It is a gas giant, yeah.
But they also say that that gas giant exists in a vacuum. Now, we know that gas pressure in a vacuum fills the available volume. But if the infinite vacuum of space it's like a magnet towards gas pressure, because gas pressure wants to burst into it.
So
now,
gas pressure in a container is uniform. So if I have like a box on a table and I fill it with gas, the pressure inside that container will be the same throughout, right?
Yeah, that's Boyle's law, right?
Yeah, but if I have the vacuum of space, which by vacuum they just mean an area of virtually no pressure whatsoever, then the only thing
let's call it a huge differential. That's more accurate.
So when we're talking about the vacuum of space, if you're in reference to like the difference between here on Earth and outer space, then yeah, it's a differential. But if you're just talking about space on its own, it's just an area of very low pressure, virtually none. Obviously, there's no such thing as science currently believes as an absolute vacuum, which is an area of space with literally nothing in it. We've not been able to kind of find that yet. It's deemed to be virtually impossible, essentially. But if you've got just an area, let's say a volume of space, and you just put a load of stuff in it, gas basically, and there's nothing kind of like containing that, or there's no forces or anything acting on it, so to speak, then that gas will just remain a blob of gas, right? Nothing's going to cause those things to move.
No, you correctly cited Thingy's law before, Boyle's law, which said that the gas pressure would be even across the whole container.
Well, yes, but we're talking about a container there. When you've got uncontained stuff.
Yeah, I know, but bear with me. We've got the infinite vacuum of space that has an infinite volume, so essentially gives no container.
Yeah.
So how can there be a gas pressure within a no container environment without Boyle's law applying immediately and saying that the gas pressure immediately evacuates into that vacuum and just becomes the matter for which Einstein says is what bends space-time? Let's not go back to Einstein. Let's deal with the gas pressure. What keeps the gas pressure in a state of pressure without a container?
So this is where we refer to gravity, because here on Earth, as observed, as a fact of our reality here, at sea level, that gas pressure, that atmospheric pressure, is like 14.7 psi. And then when we go up mountains, it's much lower. It's like, 6 psi at the top of Everest or something silly.
And what causes that gradient?
So Well, this is the thing that I was sort of going to explain about the blob of gas in space. So everything that is or has mass, if you like, everything that has weight effectively in the universe has a small amount of gravitational attraction. This is the mass attracting mass thing that Cavendish came up with. And so what happens is if you just have lots of stuff, just let me finish, and then you can put a counterpoint in.
Derailing
Okay.
badly here, though. We're derailing badly because you can't have the gas pressure gradient in the first place without some element of containment. That's why I asked you what causes the gradient in the first place.
So yeah, if you let me finish, I was going to explain what causes it, but just let me finish, and then you'll understand. So I've just got lots of separate, if you like, atoms or molecules of some gas just floating around in space. They have a small amount of gravity that acts upon them individually and the atoms that they're close to. So what happens naturally is that they start to gravitate towards one another. And so, of course, when you've got something the size of a planet, it has a lot more gravitational pull, and then the atoms start to stack in columns. And obviously, the further you are away from the center of that mass, the less the force is. And then, of course, you've got the counter of that, which is entropy.
Stop. Please forgive me. I don't mean to appear rude, and I'm trying not to be rude. I'm trying to be as polite as I can. But what you seem to have done, you seem to have flipped from an Einstein perspective of gravity, which is the effect of the curvature of space-time, and you flip back to a Newtonian principle of gravity, which is mass attracting mass. That's not the current position of gravity. It's been superseded and replaced. So can you explain to me how we have gas pressure in a vacuum applying, if you're going to say the cause is gravity, which it isn't, I know the cause, and it isn't gravity, but if you're going to tell me that the cause is gravity, don't explain it to me with Newtonian concepts. They've been replaced. Explain it to me with Einsteinian, or ask me to explain why we have the gradient in the first place, and I'll tell you the alternative.
So if we're talking about this from an Einsteinian point of view, imagine you've got a flat table and you've got lots of little balls on it. They represent the individual atoms. Each one of those is going to put a tiny little dent in that tablecloth, and they will.
What would happen? What would happen applying Thingy's law, Boyle's law, is that the balls that are on the table would immediately fill the room that the table is in until it got to a point where it hit the walls, and then it would bounce off the walls and it would begin to create a little tiny bit of pressure by the collisions against the walls of its container. They would not stay on the table and they would not cause a dent in the fabric of space-time.
So what you're talking about there is entropy in the second law of thermodynamics.
Correct.
So you're saying every atom in the universe has an amount of energy which causes it to basically travel. The converse to that, of course, is when you have lots of mass in an area. What essentially happens is the combined force of that mass is more powerful than the amount of entropy, which is why the atmosphere only goes so far.
No,
and then obviously the atoms fall back down.
That's not right. Remember, Einstein's definition is the uneven distribution of mass, which would be all of the gas particles that are all congregating in an area. And rather than applying the second law of thermodynamics, entropy, where they fill the available room and bounce off the walls, which is what I said they would do, for some reason, you've got the nucleus in the middle, and you're again flipping back towards a Newtonian concept of gravity by saying that they're all interacting with each other. They're not. There's nothing holding them together. Remember, Boyle's law applies. All of the pressure is evenly distributed within the container, but there is no container. There's no volume. So there's nothing to keep them together. You have Boyle's law that says that they will immediately disperse, trying to find some to bounce off, because that's what gas pressure does. But we haven't got any pressure because we're in the infinite vacuum of space. It's very, 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 very tiny. We'll call it zero pressure, but we haven't got any pressure. So how can there be nucleus in the middle when Einstein's current definition is the one that's accepted? You keep wanting to revert back to Newtonian principles, and even if you did do that, you've still got to apply Boyle's law, which you correctly cited in the first place, to say what they would do. All of that gas pressure would try and disperse into that pressure because it doesn't want to hold in the middle. There's nothing to hold it in the middle on the table.
Your assumption is that if if you don't have any planets, if you don't have any like large masses at all, then under the model that you don't accept anyway, if there is not any kind of gravity in the first place because there's no large masses effectively, stuff will just spread out forever and will never form any kind of planets. Is that what you're saying?
I'm saying that entropy applies. I'm saying that Boyle's law applies. And what you describe as the nucleus of the collection of atoms on a table in a room can't happen, because that defies the second law of thermodynamics, because entropy always puts things to the highest state of entropy. So the decay, everything wants to decay to its worst possible state. That's entropy. Now, gas pressure, by holding its position and staying as a nucleus, that's energy. But that's the opposite of what actually happens, and Boyle's law proves that. So how is the gas pressure of Jupiter? I think it might be better if you ask me to explain how it happens on Earth, because on Earth we're supposed to be an open system, and the gas pressure immediately goes into that pressure, into that lack of pressure, because that's what gas pressure does. It's Boyle's law, which you correctly cited before. There's nothing stopping it or creating it. There's no force. We know that gravity isn't a force, unless you flip back to Newtonian concepts, in which case I'll point that out and say, no, that isn't the current science. Now, if you want to claim it's a force, then I'll flip the Einstein card and say, hang on a sec, he expressly states it's not a force, it's an effect of the curvature of space-time cause, and that's why you can't answer it, and you have to flip back to Newtonian principles. But we know it's not one. So I'm not going to allow you to do that, because one, it's not the current position in science, and two, there's a much easier and demonstrable and experimentally valid way of demonstrating why we have a pressure gradient in the first place. Because as you correctly cited, Boyle's law applies. The pressure would be even across the container. Well, we have a pressure gradient, so therefore that indicates that there's something else going on, and Boyle's law can't be the cause, because if Boyle's law was in place, it would be uniform all the way up across the container, and therefore, you're right. On the face of it, you seem to be right, but there is an alternative explanation that goes beyond Boyle's law to explain how we have a pressure gradient that hasn't dispersed into the vacuum of space. Are you prepared to listen to it, or would you rather tell me about Newton again?
So I kind of get what you're saying. So you're basically saying that Newton and Einstein don't agree with one another because they have a different description for what is essentially the same observation.
Correct. Newton said it was a force that he didn't. He actually said, "Do not ascribe gravitation to me," in his letters to Bentley. He did not want any force. He said, "It seems to me that inanimate brute matter should be attracted to each other without an external agent. Seems to be manifestly absurd," or words to that effect. He says, "Do not."
Yeah,
ascribe
you're talking about
gravitation
Newton's
to me."
laws of motion, yeah?
I'm talking about gravitation. Newton said, "Do not ascribe gravitation to me," and he wrote it in his letters to Bentley, saying that it seems to me that inanimate matter should, without external agents, be attracted to one another, is so manifestly absurd, or words that I'm butchering it. I could read it to you. I'm not at the computer.
Yeah, I know the quote you're referring to. Yeah, Newton basically said he didn't agree with gravity at all. But
correct.
But what he was.
Hang on, that's where C.V. Boyes came into it with the Cavendish experiment. C.V. Boyes added an attractive force between masses, and then Cavendish tried to replicate the planned experiment that C.V. Boyes wanted to do 120 years after Newton had died. So what's really happened is Newtonian gravitation is what a lot of guys want to revert back to explain the gas pressure point, but don't realize that Newton didn't want gravity ascribed to him in the first place. It was C.V. Boyes that put it against him when he died. In other words, he stabbed him in the back. But that's the bit that most current guys in this topic don't realize is what happened. But that's why I won't let you go back to Newtonian. And that's why I'm imploring you to let me explain it the alternative way, the only way that explains it properly. And it's stuff that we learnt in GCSE school, like when we were about 8. But you've probably forgotten it.
Well, let's hear your alternative description then.
Okay, so the cause of gas pressure in the first place is a container. You can't have gas pressure without a container. Quantum eraser is correct. But the reason why we have a gradient isn't because there's a gravity force pulling it down. It's because we've got something called the Biogeochemical Cycle, which is a collection of cycles like the carbon cycle, the oxygen cycle, the nitrogen cycle, the hydrological cycle, and there's about 12. I've just named 4 off the top of my head. There's about 12. And they're all created at ground level caused by the sun. So in other words, the sun heats the surface water of the oceans and it causes evaporation. That evaporation is the breaking of the hydrogen bond that makes water become a gas. And obviously the compression ratio is high. So there's a lot of gas created by the hydrological cycle. And then it goes up into the atmosphere as vapor, it condenses and then reforms back into liquid and comes back down as rain. But that hydrological cycle is the creation of gas and then the condensation from gas back to liquid again in the form of rain, and that's just one. But that process, that condensation process as it converts back to water again, that is the creation of the gradient from one aspect. But there's about 12. We have the nitrogen cycle, we have the carbon cycle, and there's like 9 other ones. They all create the gas pressure at ground level, be it sea or land, that is what we breathe. It all gets mixed up by the sun, and it happens because we're inside a container. And that cycle, that constantly cycling cycle, and there's about 12 of them, is the cause of the gradient. It's got nothing to do with a force attracting a mass attracting mass.
So what I would say to that is, to some extent, yeah, you're right in that those are the things that are commonly accepted by science, and they explain things like how water and carbon and things like that are moved around. But what they don't explain is the pressure gradient and why down is down, so to speak.
They do explain the pressure gradient because all the gases are created at ground level, and the higher you go, that gas pressure is pushing upwards at all times because of Pascal's law. Pascal's law and Boyle's law states that the gas pressure should be continuous in the volume, but Pascal's law states that it's pushing the pressure pushes evenly against the surface of the container, which would be the crust, evenly in all directions. Well, that means all of the gas pressure that's created at ground level is pushing out in all directions towards space, evenly in all directions. Now, the problem we've got is Newton's laws of motion state that an object in motion will remain in motion unless acted upon by a force, and an object at rest will remain at rest unless acted upon by a force. Well, we know that we've got gas pressure at sea level at 14.7 psi, and we know that Pascal's law states that it's going to be pushing against the walls of the container, which is where we get the pressure from, the surface, in all directions towards space evenly. Now, we know that that's what gas behaves like, but we also know that we need a force to bring it back to Earth again, otherwise it's going to go off into space. And it's going to do it fast because of the differential. There's a 14.7 psi at sea level compared to the 0.000000, and however small you want it to be in the vacuum of space, differential. Now, I accept that there's only a little tiny differential at the edge of the gradient, but at sea level, 14.7, that's bursting to get into that vacuum. So we know that it can't be a vacuum in space. So we have the explanation for why there's a gradient. We know that the creation has to be within a container, otherwise it disperses very fastly into space. But when we look at, going back to the original point, when we were looking at Jupiter to try and establish whether or not Einstein might be right or not, because they tell us it's a gas giant, but they also say it exists in a vacuum of space, and we know that gravity is not a force, what is it that's holding the gas particles of the gas giant that we're told is Jupiter? What's holding them together without them immediately dispersing into space? Because from where I'm standing, it looks just like a light, and I can't tell what it is.
So let me just pick apart pieces, because you said you've made a lot of points there, and some of them I agree with and some of them I don't. The first one is, okay, you agree that there's a pressure gradient, and you agree that on the very edge of that gradient there's virtually no pressure, but you disagree with the definition of vacuum of space. So what do you perceive as being the difference there?
Well, it's not that I disagree with the definition of vacuum of space. I disagree that space is a vacuum at all.
Okay, but when they say vacuum, they just mean area of extremely low pressure.
Yeah, but space can't be a vacuum because we're breathing gas pressure. Now, the fact that we're breathing gas pressure means that Pascal's law applies, and Boyle's law applies. All of the pressure that's created at sea level, ground level, would immediately evacuate into that vacuum because that's what gas pressure does. It's entropy, isn't it? All pressure goes to non-pressure always. Now, I don't know why it does that, but we know that it does do that. So we know that when we look at Jupiter, and we know that we accept that we do breathe gas pressure, we know that space can't be a vacuum, because if it was, Jupiter wouldn't exist, and our own atmosphere that we're breathing would immediately evacuate into that vacuum. So whatever space is, and I'll just call it sky, whatever sky is, it can't be a vacuum, because it has to be within the container that we're in, and it forms part of our gradient. It's just too high for us to get to. But you say it's a vacuum, and I say, well, the gas would immediately go into it, because that's what gas laws do. Boyle's law tells you that it will be evenly distributed within the confines of the container. But if the container is infinite, mathematically speaking, if you try and multiply anything by infinity, you get infinity. So where do we end up getting the gas pressure that we're breathing, and where does Jupiter get its gas giant status from if the vacuum of space is what it is? And remember, this is within the confines, or within the description or the discussion of Einstein and general relativity, because we were challenging how would we test it, because you said we couldn't test it. And I said, well, what we can do is negate it, because we can demonstrate that Jupiter can't be a gas giant in a vacuum of space, because gas pressure doesn't exist in a vacuum in space. So
Well,
I'm not trying to.
So here's the problem, right? So you accept that there's a pressure gradient from ground level up to really high above our heads that goes to virtually no pressure. But virtually no pressure is somehow different to vacuum, right?
I'll call that sky.
Okay, so in sky, there is so there's ground level, then there's sun pressure, then there's sky. Okay, but there are also other ground levels and other really high up and other skies. That's basically what science is saying.
How does it say that? I don't understand that. Can you explain that a little bit better?
So Earth is considered to be one of many planets in the universe, and every planet is essentially the same as what Earth is. It has this pressure gradient from its center point all the way out into sky, as you put it.
Okay.
So what we're saying is we've observed this happening here on Earth, and we're saying, well, we've looked out and we can see all these other circular balls in the sky, and we believe that that's the case over there as well.
That was the key word there, believe.
Right, with a reasonable level of, yeah, I see what you mean. There's a certain amount of, obviously we don't know until we go there, right? That's kind of the argument being presented. Once we go to, I don't know, Mars and land on Mars, then we can say, yeah, okay, everything's the same here as well. I mean, it's a different ecosystem, but the same rules apply.
I love your idea. Should we set up an agency that's dedicated to getting to Mars? Should we call it NASA?
I've got an alternative. Let's call it SpaceX.
Yeah, we'll give them a shitload of money, and we'll give them the best technology to recreate what they tell us is what they think that NASA should, that Mars should look like, and then we'd have no way of validating it. But we'll believe them because they're showing us pictures, and we'll just we'll accept that that's what's really up there.
So
we've got no way of validating it though.
We're communicating over the internet. Do you know how the internet works, or do you just trust it?
Yeah, but technology is not the same as science. Do you agree? Technology is the application of science for the consumer purpose or whatever. But technology itself is not science.
So if you got a telescope and you saw lights that were to do with a base on the moon, would you then believe that we were on the moon, or would you still deny it?
Well, I know that we were able to bounce lights in the form of radar and signals off the moon before we had the Apollo moon missions. So I'm
saying, like, if we, for example, established like a small town on the moon, and at night that was lit up, and we could see those lights from Earth, would you then accept that we had been to the moon and that gravity was real, or would you still deny it?
I wouldn't describe lights on the moon as a town, if that's what you're asking. I would say that they are lights. How would you prove that it's a town? You'd have to have a bloke with some kind of Morse code beacon flashing a signal back to us that we could interact with and say, right, press A, B, C, Z. And then he does A, B, C, Z. And then we could say, right, that must be a guy really doing it.
You would only accept that if you were part of that interaction, right?
Well, if it was verifiable to be the case that anybody could do it and it was verifiable, I think that's more plausible than just giving us pictures that look like CGI that everyone tells us is true. So it's a two-way communication, isn't it? That is capable of verification.
Yeah, you want to be able to get some feedback for the evidence that you're gathering because it's more scientific, right? That's fair.
I wouldn't say it's more scientific. I'd say it's more credible.
Yeah. Okay. Sorry. Yeah, that's what I meant by the term scientific.
Yeah.
What can I say? I associate the word scientific with being the means by which we gather knowledge or evidence that we can kind of trust to some degree. As opposed to something like faith. I believe something just because I believe it because somebody else told me, or I just take it to be. Well,
or NASA.
NASA's an interesting contention point because I know that obviously most flat earthers would say, okay, NASA lies, but I don't want to start then saying, well, what about, say, JAXA or the European Space Agency? They're not NASA, but they're selling the same story effectively. So what's the issue there?
Well, there would be a common reason for all of them to lie, isn't it? It's the control element of their own population. If they see that NASA are able to provide a persuasive story that persuades the Americans that their story is true, then if they jump on with the same story, they might be able to persuade their nation that their story is true. As long as it's similar, they'll be able to persuade their own nation that they've got all the answers, right? Because China believe that they've got all the answers with regard to the moon, because they believe that they've got a satellite orbiting the moon and taking all these pictures. Yet the Americans don't seem to even have any weight to the claims by the Chinese agencies at all. They just kind of forget that they don't talk about them, they don't credit them, they don't say, hey, this is fantastic for mankind. It's almost as if it's compartmentalized just for the Chinese part of society, and the Americans are just for the Americans, and there's a bit of bleed into the English because we don't have one. And the European space, they can have a bit of the Americanisms too, but what I'm saying is they've got a common reason to keep up the story, control.
And also the Chinese images don't match the American ones at all. So surely if they were taking images of the same thing, then the images would match.
So
but clearly they don't.
The main point there is that the Americans are putting 4K cameras in space. The Chinese are still running on Stone Age technology.
So how come we don't have a 4K camera on the moon looking back at the Earth?
That is a good question, and I would love to see that someday.
Why has that never been done? I would always be looking at that.
What I would say at this moment is that we're deep within the begging the question fallacy, right? Let's go back to the basics. We were trying to establish whether or not we could demonstrate that Einstein proved Newton wrong. So what we said was that we agreed that the experimental application of Einstein's time couldn't exist because technology and whatnot. And I said, well, we can demonstrate that Einstein's is incorrect because we can demonstrate that gas pressure, Jupiter, Earth, can't coexist in a vacuum without containment somehow. Now, my contention
where's the container?
It doesn't matter. I don't know where the container is. I can't explore the domain. I don't have the ability. I've got a P900 and a compass. I can't explore the domain that we live in. NASA can, and I believe NASA know exactly, because I don't want to go into it too much, but I say that Operation Fishbowl and Operation High Jump was proof that they found the container, because why the fuck would you send a load of nuclear or high-yield kiloton weaponry up into the higher stratosphere just to explode it? It seems to me that they were trying to break out of here, perhaps. It might be, it's conjecture on my own part, but my point is this. We know by the definition, by all experiments, we cannot create gas pressure without a container. It needs to be contained. So if the starting point is space is a vacuum, then we have gas pressure. Well, we need a container to have the gas pressure. We can explain the gradient if we've got a container, but you guys can't explain the gradient if you've not got a container, because you need gravity and you need to then revert back to Newtonian principles, and we know what happens there.
What do you think the disagreement is then between Einstein and Newton? Because they're both saying the same thing, but one, in my opinion, is a more detailed view of the other, essentially. So it's a bit like me saying, well, this mouse is made up of plastic. That's the Newtonian view. And then Einstein comes along and says, no. This mouse is made up of atoms.
No, right. So the conflict between Einstein and Newton is that they are literally opposing. Einstein said that gravity is an effect. Newton said, and Newton didn't even say this, but this is what's pinned on him. Newton said it was a cause, it was a mass attracting mass. Now remember, Newton didn't say that. That was what CV Boys pinned against him 100 years after he died. Newton's position was that it seems to me that inanimate matter should, without external agents, be attracted to each other, such a manifestly absurd or whatever. So Newton didn't even say this. This is just what you guys tell us Newton said. Newton said, I don't want gravitation ascribed to me. But
Yeah, Newton was basically saying that he didn't agree with the concept that mass could just will itself together, so to speak. The Cavendish way of thinking, right?
Correct. That's what Newton actually said. But the reality is that everybody seems to think that gravity is mass attracting mass, and they pin it on Newton incorrectly. But that is where it's pinned. Now, the reason why Einstein and Newton are not compatible is because Einstein said that whatever gravity is, it's an effect, right? It's the curvature of space-time caused by, or the effect of the curvature of space-time caused by the uneven distribution of mass. But the key word is it's an effect. That's on the right-hand side of the equation. Newton's gravitation, mass attracting mass, that wasn't even Newton, that's on the left-hand side of the equation because it's the force. So F equals ma is on the left-hand side, F being on the left-hand side, but Einstein is the ma bit on the right-hand side. So you couldn't get more opposite. They're opposed, they're fundamentally opposing each other. One's a force, one's an effect.
Okay, so yeah, I can see why you would come to that conclusion. So F equals ma is saying, given I have a mass and I have an amount of acceleration that takes place, because mass doesn't just move on its own, there must be what we describe as a force acting on it, and the amount of that force is described by the formula, right?
Yeah, but usually a force is a push. It's not usually a pull, apart from magnets, which seems to be the exception to all the physics. But I don't know what magnetism is, and I don't want to go into it. But usually a force would be a push. But
right. So your understanding is that what is attributed to Newton is that formula, basically. So Newton is saying, well, gravity is a force, right? But the problem that we have with forces is there used to be four, now there's only three, what we class as the fundamental forces of nature. But we don't really know what a force is, what causes one. We just know what we describe as their effects. And this is where the problem comes in, because Newton was looking at that and saying, well, it's a force. It behaves just like other forces that we've seen, like magnetism, right? And so Newton was going, see, don't attribute this nonsense to do with space and time and curving and stuff with me, because...
No, that's not what Newton was saying. Space and time and curving of space and time was 100 and odd years after Newton. 100 odd years after.
Sorry, mass attracting mass. My apologies, I misquoted you.
So Newton wasn't saying don't ascribe that to me. He was saying don't ascribe mass attracting mass to me. So Bendy space time that wasn't in the equation at that time. He was saying mass doesn't attract mass, which is what we say. We kind of agree with Newton, but the way Newton's represented is a misrepresentation. But let's be clear though, Newton's gravitation is mass attracting mass. That's not really Newton's, but is pinned against him, right? We're saying that mass doesn't attract mass, which is what Newton said. But because everyone thinks that mass attracts mass, we have the contradiction with Einstein that said it's an effect. The curvature of space-time.
So Newton, Cavendish, and Einstein, to my understanding, don't disagree with one another. They just explain it differently. But what they're explaining is varying detail levels of the same concept.
Yeah, so it's like saying it's literally in its simplest of forms. It's the same as saying that 2 + 2 = 4, and that would be Newtonian explanation. 2 + 2 = 4. But Einstein says no. The 4 bit's right, but it's 1 + 3. So you still get to the same outcome, but you just get there with a different mechanism. So it's 1 + 3 now. And I'm saying that the 1 + 3 is not right either. But that the current physics accepts that 1 + 3 is the way to get to 4. They don't accept the 2 + 2 anymore. But because everybody needs that force to exist, they always flip back to Newtonian principles at some point in the conversation to get that nucleus of gas existing in a vacuum of space. Well, you can't do that because it doesn't do it.
So given that we've observed situations, like I said earlier, like black holes, where relativity falls over, I would say you're probably right in that assertion that Einstein is wrong. The question is how wrong. But what we do know is that relativity at the moment enables a lot of our technology to work the way that it does based on our current limited understanding of the universe. It doesn't
we know
mean
that-
that we're not going to find a better solution in the future. It just means that that's the best possible understanding that we have so far.
Well, I can answer your question when you said we know that Einstein, because you said about black holes and you said we know that Einstein's wrong. The question is, how wrong is Einstein? We know that he's absolutely wrong, 100% wrong, because if space is a vacuum, there needs to be an explanation for why mass seems to be attracting mass that creates a gas nucleus for a planet that we call a gas giant called Jupiter. Because there are no experiments that demonstrate gas pressure without the confines of a container. You need the container. So
Right.
if Jupiter really is a gas giant, it has to be contained within a bubble, right? It can't exist otherwise. Now, I'm not saying it is, but what I am saying is you can't have the gas pressure in a vacuum without some kind of containment, because you can't demonstrate it. Now, if you haven't got...
But then you accept that we've got that on Earth. This is the thing that I'm confused about.
No, I say that we don't have that on Earth. We must be in a contained environment because we've got gas pressure. If you just go to Google and just type in what is the cause of gas pressure, you will see that there are 50 million citations, one of which is NASA, that says that it's the collisions with the walls of its container that gives you gas pressure. Well, we have
Right,
gas
but
pressure.
gas pressure is not atmospheric pressure. Those two things are different. You understand that, right?
Okay, so what I'm going to say now is I'm all right with the conversation for atmospheric pressure, but what I'm going to say is that by the end of when we've had this conversation, I'm going to say that it's literally a special pleadings case which doesn't exist. But let's do the atmospheric pressure. Do you know what atmospheric pressure is defined as within physics?
So I'm going to preempt where this is going to go. Okay, so.
Okay.
The reason why we say atmospheric pressure is not the same as gas pressure, despite the fact that the atmosphere is entirely made of gas, okay, is because gas pressure purely talks about gas in a container, and the atmosphere is not contained in a box or something in the same way. What contains atmospheric pressure is gravity, and that's why we have a gradient. It's a different behavior.
Just for this conversation, I'll just give you gravity, right? Let's just say that Newtonian gravity applies. It doesn't, it's Einstein, right? And we can't explain gas pressure with Einsteinian gravity because you just can't do it. It doesn't work. But let's just give you that. Well, because remember the definition, the curve, gravity, as current science tells us by Einstein, is the effect of the curvature of space-time caused by the uneven distribution of mass. Well, you can't formulate that to explain gravity in the context of gas pressure.
Why not?
Try it. You tell me how gas pressure is created within Einsteinian gravity.
Well, relativity tells us that the gas, when nearer to a larger mass, because of that lack of uniformity across space, will fall into that larger mass's gravity well. It'll roll down the hill.
All the particles are on their own geodesic, right? So, and we know that gas law states that, as you said earlier on, that all the pressure is even across the whole place. So
that's entropy. It expands. Yeah,
and we know that Pascal's law states that it pushes evenly against the surfaces of the container. We know that it's pushing all directions or away into space, and we know that each particle is on its own geodesic according to Einstein.
Yeah.
What stops it from going into space as per Einstein?
The mass of the Earth.
How?
So at ground level, you've got a lot of gas pressing against a lot of other gas molecules with a high amount of energy. So they push up and up and up until there's a lower amount of energy. And then that lower amount of energy, entropically speaking, is less than the amount of energy that gravity then imposes on those same atoms. So they get pulled back down. So it's a cycle.
See, what you've done there is you've flipped back to Newtonian concepts when you're trying to explain Einsteinian.
Why? Why have I shifted? It's the same thing, right?
The only way you can get the gas particle to fall back to Earth under Einstein is to warp space-time 180 degrees so that the path, the geodesic that the gas particle's following isn't actually going out to space. It's coming back to Earth again on a totally new geodesic. But you've bent space-time around that one molecule. But you've got to do that trillions of times, 100% of the time, all the time, to get the geodesic to fall back to Earth under Einstein.
I see what you're saying. So you're looking at the drawings that people have of like a kind of like grid net with a ball sat on it, and you're saying, well, that grid net is like a billion different grid nets. Yeah, that's the thing that
Because
you've got
all
to
the molecules
understand.
have got their own. Yeah, but you've got to bend that
Yeah.
grid 180 on itself so that the geodesic, so that the molecule's still taking a straight path, because that's what gas pressure does, pushes out until it hits summit. So it's still taking a straight path, but you've bent the path that it's taking, so you've bent space-time around it so that it comes back to Earth. So it's technically straight still, but you've bent space-time around it to force it back to Earth on its own geodesic. That's the only way to explain it with Einstein, but that doesn't make any sense whatsoever, because we know that gas particles are not, they're going straight. So unless space is some kind of wrapped round thing that's limited to just our environment, and we're in like a lotus flower kind of pattern where everything's wrapped round itself, then that's the only way to explain gas pressure with Einstein. Now, I'd say that's poetry.
The problem that you've got is, how do you represent a spherical hole, so to speak, or spherical hill? That's probably the better, more accurate description. I've got a hill that's going down in every direction towards a sphere. Like,
Yeah, that's what I'm saying about bending the space-time back on itself. We're on the same page.
you can't represent that on a screen. So there's not ever going to be any accurate depiction of that on a screen, effectively. So,
but the problem with that, though, is then you're defying Boyle's law, because Boyle's law and Pascal's law state that the pressure pushes itself evenly in all directions, but it doesn't say that gas particles can follow curved trajectories on a different geodesy.
correct.
So what it seems is that you're curving the straight line into a curve.
Yes. So no, you're taking what potentially would be a curved line and you're turning it into a straight line, and
No,
the molecule will follow the most straight line, the path of least resistance, shall we say. So it's all to do with the interplay of forces and the interplay of these rules all playing against one another.
No. You've got it the other way around. It's not. What is essentially happening is the gas particle that wants to fuck off into space on a straight line at 500 meters per second or whatever speed gas travels at, that straight trajectory under Newtonian principles, because it needs a force to change its path. Otherwise, an object in motion will remain in motion unless acted upon by a force. Einstein's not applying a force to it. Einstein's changing the curvature. It's moving its path so that it's, even though it's going on a straight line, somehow it bends back to Earth again. And we describe that as a loss of energy or as a force of attraction. But he's warping space-time around back on itself so that the particle comes back to Earth. But that's basically changing the geometry from Euclidean geometry, which is straight lines, into non-Euclidean fantasy poetry stuff that Max Planck would say no, because there's no experiment for it. It sounds lovely, and I suppose psychedelically speaking, if you were high, you could probably imagine it. But the reality is, an explosion only goes out in one straight direction, and it's the direction in which the particle is exploding. It doesn't change its trajectory until it runs out of energy, and that's because of a load of other things. But the point is this: the gas pressure is still pushing away from the Earth at all directions.
So if I pick up a ball and I throw it up in the air, there's going to be a point at which that ball has less energy than the amount of gravity acting on it.
Running out of energy doesn't change the trajectory of a path. You need a force.
Of course it does.
No. If it
so
runs out of
when
energy,
we're talking about Einsteinian physics, we're talking about that path is changing due to gravity. So it's being in the same way that the ball that I throw is going to come back to Earth. That straight line that I threw it in isn't a straight line forever, is it? The ball curves back down.
Under Einstein, he would have to argue that the arced trajectory of the ball that rises, gets to its crest, and then comes back down again, he would have to argue that that's a straight line, because the warping of space-time around it has made its future, its path, its future, the ground, and space is warped around it, which is complete nonsense. But this is why I'm saying you can't formulate what gas pressure does.
The line would be a straight line, but there's already existing forces already acting on it. The ball that I threw has existing kinetic energy, which also comes into play. When you compute the amount of kinetic energy and the amount of gravitational force being pulled, you get a different trajectory. You don't get a straight line, you get an arc. And that's the same thing that's happening with entropy.
Einstein argues, for Einstein's thing to make any sense, you've got to argue that the trajectory of the ball as it goes up, turns around, and then comes back down again is actually a straight line. Because Einstein says that
No,
it's not
no,
the
no,
line
no,
that's changing.
no. You don't have to argue that at all. That's completely wrong. So it would be in ideal circumstances, but the ball has two effective sets of energy, if you like. There's one being imposed on it by the pull of gravity, and there's another being imposed on it by its existing kinetic energy that it has. You
But
have to
now what you're
calculate for
doing-
both.
You're making two flips now. You're flipping back to an element of Newtonian principles because you're saying the force of gravity. Well, we know it's not a force, it's an effect. But you're also refusing to accept that the geodesic path that ball is on, the trajectory that ball is on, you're refusing to accept that has to be described as straight in Einsteinian.
When an object is stationary, it would be a straight line, but the object isn't stationary. It's already moving.
The path, no.
It's
Einstein
Newton's laws
said-
of motion and Einstein's relativity playing against one another.
Yeah. So Einstein says that the path that the ball takes is a straight line, but everything warps around it. That's what Einstein says, because the geodesic path of the ball is a straight line, but everything's warping around it. Now, I say that's complete nonsense, but that's the only way to describe the trajectory of the ball with Einstein.
So that the ideal path would be a straight line, yeah.
No, Einstein says that the trajectory of the ball, its path, its geodesic path, is a straight line, but it's the warping of space-time around it that gives it the perception of curvature. In other words, Einstein's got to argue that orbits that we perceive as curves are actually straight lines, because it's the warping of space-time around it that gives us the perception of an orbit. That's what Einstein's arguing.
Yeah, okay. I see what the confusion is. Right, we're conflating orbits with the throwing of a ball.
No, we're comparing orbit with the changing of space-time that gives it the geodesic path that we perceive as an orbit, but is actually a straight line traveling through space-time.
So an orbit is when the object in question is at a velocity that is equal to the amount of gravitational pull that's on it. So it naturally follows what is essentially considered to be the gravitational straight line, which in reality, due to that curvature, is a curve.
No, you've just flipped back to Newtonian principles for orbital mechanics again. That's not.
No, that's literally what relativity talks about.
No, it isn't. Relativity is the curvature of space-time caused by the uneven distribution of mass that we perceive.
That curvature is taking what would be a straight line and bending it. So it's still, if you take, for example, a tablecloth again, let's take that, or a sheet of paper, right? The shortest distance between 2 points on a sheet of paper is literally directly between them, right? If I bend the sheet of paper, the shortest distance now becomes the distance between those same 2 points, right?
Yeah. But which way does the trajectory go? Does it go between the 2 points and not on the paper, or does it stay on the paper and follow a curved path?
Right. So you have to follow space and time because that's a law of reality, right? So what's happening is space is being bent and then it's following the new trajectory of space.
So it's not short circuiting across, it's following the contour of the paper that you've just created, right?
Essentially, yeah. You're bending space itself, so the new trajectory, that straight line from the, think about it in terms of reference frames. I don't want to get too bogged down in reference frames, but from the point of view of the observer, you're traveling in a straight line. But actually, from a space-time point of view, you're curving.
I agree, but the same definition that you've just described applies to the ball. The ball, according to Einstein, is going in a straight path, but it's warping the space. So the piece of paper is creating a horseshoe, and the path that the piece of paper, the ball takes, is a straight line on the piece of paper, but the piece of paper is bent back on itself like a horseshoe.
Yes.
Right. Now, in the context of gas pressure, how does that work?
So the difference between obviously the ball and the something in orbit is that the ball is not going to have enough energy to keep itself in orbit, is it? So there will be an offset. So that will actually curve. That's not a straight line in the same way, if that makes sense.
I agree, it does actually curve, right? I don't think that they're following a straight path and bending space-time to get back down to you when the ball comes back down to you. I agree with that. But that's but the fact that I agree with that doesn't mean that we're at a meeting of minds, because I'm saying that Einstein's is nonsense, right? I don't agree with Einstein's relativity. But what I'm trying to say is that Einstein can't explain gas pressure in a vacuum by applying anything to do with bendy space-time caused by the uneven distribution of mass. It doesn't work. This is why we're having a struggle. We're actually, by failing to describe gas pressure, applying Einstein's gravitation and bendy space-time, by failing to do that, we prove that Einstein is incorrect. Jupiter can't be a gas giant in a vacuum space because we can't formulate how it happens using Einsteinian relativity.
Why not?
Because we're failing at it right now. You can't tell me how gas pressure is provided by Einsteinian gravitation.
So the thing that I'm sort of failing to understand here is what you think Einstein is doing that directly contradicts what Newton told us, other than the fact that they disagree from an explanatory point of view, what the cause is, so to speak. The effects that they're both describing is identical.
Right. Do you want to ask that again, but in a more concise way?
Yeah, I was sort of formulating my idea as I put that sentence together. I admit it probably wasn't clear. So Newton basically says, look, I've observed stuff falling to the ground. And Einstein says, based on that observation, I can deduce that at a galactic scale, if this was due to the curvature of space-time, then a few things would be true, such as gravitational lensing, which would also result in the effect of stuff falling to the ground. So it's adding detail to something that already existed, so to speak. He's not contradicting Newton in any way. He's adding more detail.
He's not. He's changing the geometry from three-dimensional Euclidean geometry to four-dimensional pseudo-Riemannian force space. Now, the three-dimensional Euclidean geometry is something that does actually exist. We do have X, Y, and Z axes, right? But Einstein added a fourth axis called time. Now, that fourth axis doesn't actually exist in the sense that time's conceptual. It's a human-created concept that we use to measure the passage of time. Now, time itself doesn't actually exist. The passage of time does, but time itself does not. But time has been added as a fourth dimension to a three-dimensional Euclidean three-space. Now, the problem with that is the minute you go away from Euclidean three-space into some other form of geometry, we have big problems with how we accept the credibility of that new geometry, because Euclidean three-space is credible. But if you go into a different geometry, you might as well go into Narnia. You've heard Nathan talking about Narnia, right?
Nathan talk about a lot of stuff. I don't really take much stock in anything he says, but
if we're working within Euclidean three-space, at least we've got finite and defined parameters that we can all test, play with, wiggle, do science with. But if you go into a fourth dimension, like pseudo-Riemannian force space, where you've added time into the mix, now we're not in a medium anymore that we can actually do anything with, because the medium is created by its creator and it exists within the rules that he puts to it. Now, he may be right, but the chances are he probably isn't right, because we can demonstrate it by saying, well, if Jupiter is the gas giant that we're told it is, that exists in the vacuum of space, what's keeping the nucleus of the gas molecules together?
Gravity.
But you instantly flip back to Newtonian. But Einstein, we're supposed to be arguing that Einstein's is correct.
Right.
Because
so
hang on. You said that he proved Newton was wrong. Well, okay. Well, how does he prove the gas giant of Jupiter exists in the vacuum of space? Because there are no gas laws that allow for that, and there's no experiment that demonstrates it. But we're told that that's what it is. Accept it.
Yeah. So what you want to see is an experiment that proves how gas behaves in a vacuum, is what you're saying. And does
Absolutely.
that then show a pressure gradient?
Well, just have gas pressure. Forget about the gradient. There might be reasons for that, because we have we know the reasons on Earth. The Biogeochemical Cycle, 12 cycles that are caused by the sun. Them planets will also have the sun. So we could transpose the Earth Biogeochemical Cycle into one for them, maybe. But we need to show how it's possible that we have gas pressure without a container first, because we know that in a vacuum, gas pressure fills that just disappears into. Now, if that vacuum is the infinite vacuum of space with no volume because it's infinite, then you have no gas, you have no pressure.
Yeah, I mean, there's some. I don't know how I can correctly explain this because there obviously is a limit to my knowledge. I'm not a theoretical physicist, but what I would say is that, in my understanding, and you're welcome to disagree with this, by the way, because we're at the limits of my knowledge here, but I can see if I can drag somebody who's a bit more scientifically informed in here if you want to have that discussion with them. But in my understanding, Euclidean geometry, so to speak, with the three dimensions, the x, y, z that we have, still technically applies. The unification that goes on with relativity, adding the fourth dimension into that as time, doesn't distort the way that the other three still work, if in that respect. But it does have. It shows that there is an impact, that things change over time effectively, and that's the unification that relativity is supposed to provide us with. It's basically
there is another interpretation for what you've just said.
Yeah.
When you said when I'm going to describe it as moving away from Euclidean geometry, right? When you described it moving away from and into four space,
yeah,
we could also describe that concept or that thing that's happening as going into a reification fallacy, because the further into a reification fallacy you go, you can paint the Narnia picture any way you want to, because you're creating the narrative. Well, I'm saying, well, let's not create the narrative. Let's just see if we can demonstrate or experiment with gas pressure in a vacuum. We do have vacuum chambers on Earth, and we know that nature abhors a vacuum, apparently. Some people say that that's not true, but the point is that we can create a vacuum, and NASA have the ability to do it. But there are still no experiments that demonstrate gas pressure in a vacuum, because the minute they try and inject any pressure into it, it fills the available volume and it raises the gas pressure and a little tiny bit. And we see that when we open the gas release, the pressure relief valve or the vacuum relief valve, when they let the pressure back into the container, that's the gas pressure going back in, and it fills the available volume.
Which is what we would expect to happen, right? Because if you put two containers next to each other and you have a vacuum in one and you have gas in the other, and you just open a wall between them, then obviously they're gonna match, right?
Why can't you apply what you've just said there with Jupiter and say, well, if the gas pressure fills the available volume, why is it that Jupiter can be a gas giant in a vacuum?
Can you not see the difference between like two containers that I've got on my desk and the gravity of an entire planet?
Right, what gravity?
So the way that science, modern science today describes the reason for that pressure gradient that we have in our atmosphere is that gravity well creates that pressure gradient. This is why we don't require a container in the same way that you flat earthers feel that we do.
No, it doesn't. No, you need a container because one, gravity is not a force. Einstein said it's an effect, right? So whatever you want to argue about gravity, who cares? I'll just give it you. I don't. It's wrong, but I'll give it you anyway. We know the cause of the pressure gradient, and it's not gravity. The cause of the pressure gradient is the sun heating up all the land that it's underneath and whatever, creating the biogeochemical cycles. That is the cause of the gradient. But you can't have the gradient without a container because it disperses into the vacuum. So even if I give you gravity, there are still no experiments anywhere that shows gas pressure in a vacuum without some kind of containment. Now remember, you need a vacuum chamber to create the vacuum in the first place, right? So that should be ringing alarm bells.
Yeah, so in the interest of meeting you halfway then, if I said, fine, okay, let's throw away everything that Einstein told us about the universe, and let's just stick to Newtonian physics for 5 minutes, okay?
Yeah.
Within the context of that discussion, what Newtonian told us, with what is essentially referred to as the law of gravitation today, is that stuff, when let go at altitude, naturally goes back towards the Earth. And obviously,
that's not true.
Well,
that's not a conditionally true statement, because helium balloons seem to be attracted to the clouds.
So yeah, I mean there's buoyancy and things like that we would obviously have to consider. There are edge cases, and I will accept that. I would accept that, for example, helium doesn't go down; it goes up, and there are reasons for that. But
Yeah, well, do you agree though that helium? You use the word buoyancy, right? And buoyancy, mathematically speaking, at least relies on gravity being a force. Let's
it
just
does,
say that
yeah.
gravity is a force. Let's just say that it's not, but let's just say it is for the sake of this.
Okay.
If Newton's apple, Newton's apple that fell off the tree,
Yeah.
if that apple, at the moment it broke its stalk and it was no longer attached to the tree, rather than being in air, if the medium it was in was water, would you agree the apple would go up? Because apples
Uh,
float in water, don't they?
yeah. Yeah, I would accept that. That seems like a reasonable premise.
Yeah. So let's just say that Newton's apple didn't fall off the tree in air; it fell off the tree in water. Then the apple goes up. Now you would describe that as buoyancy, wouldn't you? But I
Yes.
would say that it's just less dense than the medium it's in, and it's not in a state of equilibrium. It's in a state of disequilibrium. So if you've got an object, and I can demonstrate that with a helium balloon or in air, or I can demonstrate it with an egg in water, because a helium balloon in air and an egg in water are very similar in densities. Now, if you mix helium with a bit of air, you can get the helium balloon to sit in the middle of the room and not move anywhere. It'll sit in that layer and it'll not move up or down, provided you've not got any windows open and air's not being disturbed. It'll sit there. And that's how those. Have you seen those sharks that float around the room? They got a little fan that pushes them and whatever. Have you ever
Yeah.
seen them?
Yeah, or
Yeah,
like, I had a helium balloon for my daughter's birthday, and as it went down, there was less and less helium in it, and so it balanced
yeah.
after a while. But yeah, I mean, I get what you're saying, but the point there is that the common explanation for that is buoyancy, and like you've quite rightly pointed out, buoyancy is dependent on gravity. So there are two
Yeah,
forces,
but
so to speak, that are in
you're
that
right. You're
description that
right.
are
Yeah,
playing off on
just
one another.
forgive me. Let me interrupt. You're right to say that the common explanation for that is gravity. But when we go back to what science is all about, remember when we said Max Planck says without experiments, it's nothing more than poetry.
Yeah.
We do know that if we've got the helium balloon floating around in the room and it loses a bit of its helium and it begins to sag and it floats in the middle of the room, we know that if we were to either add more helium into the balloon or add more helium into the air around it, we can make that balloon move up or down, because we're changing the medium or we're changing the subject relative to the other. So we can manipulate the environment to prove what a cause and effect relationship. Now that's science. It might not realize it initially, but if we were to add sulfur hexafluoride to the room, that's more dense. That would make the helium balloon rise in the room because you're changing its position of like equilibrium, because you're adding heavy gas to the room. So the balloon's going to rise. Equally, if you added helium to the room, the balloon's going to fall because you're changing the density of the medium around it. Now, in science, in experiments, your independent variable, the thing that you manipulate to prove a cause and an effect relationship, that's your cause. So if you manipulate something and it does something, the cause of the balloon rising or falling would be the manipulation of the medium, right? But it wouldn't be the gravity, because that's where Max Planck would say, well, that's where it goes beyond experiment into poetry, because you can't manipulate gravity.
Your argument is basically that density is the cause of things rising or falling, essentially, and it's purely
The manipulation of the density is the cause of rise and fall. Yeah, and that's entropic gravitation, as per Dr. Eric Verlinde. That's what he argues. He argues it's on a macro scale. Tiny particles increase their pressure, and that pushes, not pulls, it pushes the object into its equilibrium point.
So there are ways of kind of addressing that argument, is to basically look at it and say, well, okay, if something is more dense, then it goes down, and if something is less dense, then it goes up. But the question that is attempted to be explained by gravity is, well, why does it go down when clearly the thing above it, like the air above it, is less dense? So it would be easier for the object to go up than it would for it to go down. Why did it choose to go down?
There's two ways to describe that. You can either apply a force and call it up and down, or you can relabel the axes. Instead of being up and down, relabel them and say less dense and more dense. And by adding more density or removing more density from the setup that you're talking about, whatever that is, then when your object then moves and accelerates, rather than it being a force of attraction or whatever, a force doing it, you are literally changing the density of the medium or the object So the object finds its equilibrium because that's the way entropy works. Don't know why pressure goes to non-pressure, but it does. You're creating a change or an imbalance in the pressure around that object, and then it finds its equilibrium in the same way that entropy always applies: hot to cold, pressure to non-pressure, and that's all that's happening. So if you say up and down, then it becomes a force. Well, actually, the thing that you are manipulating that creates the acceleration is the density of either the medium or the balloon in that medium. And if you're changing the density, if you then change the scale, so instead of it being up and down, the scale is now more dense and less dense, and you manipulate the density, then you've just got your object finding its equilibrium in lines with the second law of thermodynamics, entropy, because that's what happens in nature. We don't know why hot goes to cold or pressure goes to non-pressure, but we know that it does do it. Well, if we change the pressure around the object by adding mass, then you're going to create that there's an imbalance, a disequilibrium. So it's just going to find its new level, because that's what entropy does. We don't know why it does it, but we do know it does it. And we do manipulate that independent variable, and that is the cause. So if you keep the scalars up and down, then you need a force to explain it. But you haven't manipulated the force. But if I do manipulate the mass that's around it, or the mass of it, then the scale needs to, instead of being up and down, the scale needs to be more dense or less dense, depending on which way it goes, based on how much you manipulate the medium or the subject.
Right, but if you're saying that my use of terminology affects what I then need to explain, then okay, fine. If we're saying more dense, less dense, then why does something accelerate into a more dense area? Like, what's potentially the cause of that, or what's causing the acceleration? And that's the thing that we're trying to figure out. It's not the fact that happens. We all accept that happens. That's the universal law of gravitation. That happens.
Hang on,
that's the observed thing.
Let's not take big steps. Let's take little steps. Before you said about the universal law of gravitation, let's go back to what you said. What you started by saying, why does it happen that pressure goes to non-pressure, right?
So F equals ma is what you're talking about there, right?
No, you've mistaken me. I'm not talking about that.
Okay, in different terms, but that's what you're talking about.
No, it's the opposite of that, because we know that hot goes to cold always. Cold never goes to hot. We don't know why.
But why does heavy go to more dense and light go to less dense in your terminology?
Because pressure goes to non-pressure always. It never goes the other way. Now, we don't know why it does that, but we do know that law of nature does that.
Right, pressure goes to non-pressure, okay? I weigh 80 kilos for argument's sake, right? Yeah. So naturally, according to that law, I should be going to non-pressure. Why am I not?
Because you're, relative to the density of the medium that you're in, you are far greater, more dense than the medium that you're in. But if you go to water, so if you go to a swimming pool where your density is roughly similar, you can vary your density by inhaling and exhaling in your lungs, and that's the difference between you sinking and floating. So if you take a deep breath, you're going to float. If you exhale and get rid of all your air, you're going to start to sink. Now, what you're there doing is you're literally changing your density relative to your medium, and you're performing science, because you're increasing your volume, but you're keeping your mass the same. So you're increasing and decreasing your density relative to the medium that you're in. You're doing science, but you might not even realize it.
You're re-explaining the bit that we've previously both agreed without explaining the new bit that I'm asking you, which is, I have a thing. Why is that thing that has a given density not trying to go to less dense? Because in theory, based on the explanation or my understanding of what you're explaining, is the stuff that is most dense should be furthest away from us.
The reason is mass. You can't. We know that pressure goes to non-pressure. We know that temperature goes to cold, hot goes to cold. You're asking me, why can mass not go upwards into an area that is less dense, right? If anything,
because your argument is that it should, right? Because stuff should go to less dense, because otherwise, why would we have an atmosphere without a container? That's the argument, isn't it?
No, it seeks its equilibrium. So, do you remember when Felix Baumgartner jumped out of that Red Bull plane?
Yeah.
Initially, he was on what they tell us is the edge of space, right? And as he's he's virtually in a vacuum, right? As they said, as described by the current model. And there's very little gas pressure up there. Agreed?
Yeah, relative to down here.
Yeah. Now, down here, there's far more gas because we're in a thick layer of the atmosphere down here. Agreed?
Yeah. So I'm thinking the analogy here is he's jumping into a swimming pool, but there's no water. It's just air, and that gets thicker the further he goes.
Correct. Now, if it does get thicker, and my analogy is correct, what would you expect, applying my rules, what would you expect with his velocity as he jumps out the plane and he gets to terminal velocity? Would you expect that he would start to slow down because he's going into more dense medium, or would you expect him to speed up because he should be getting attracted towards the less dense stuff above him? What would you expect to happen?
So based on the description that you've given me, more dense goes to less dense. So I'd expect him to jump and fly away from the Earth.
More
Because
dense
what?
goes to-
Because why would he go
Pressure.
towards density when he could go away from density? Because more dense goes to less dense.
No. Equilibrium. It's relative to the state that it's in. So, basically, if I've got a helium balloon underwater and I let go of it, it's rapidly going to go to the surface and float quickly on the surface, isn't it?
Possibly, yeah.
Yeah, because if you get a balloon underwater, it's not that it's heavy; it's trying to pull itself back out of the water because it doesn't want to be there. So, what you're doing by pulling the balloon underneath the water, you're pulling it away from its equilibrium point, because when it's in air, it's a lot nearer to its equilibrium point. And if you let go of it, it'll rise above the house and it'll find a level like smoke does. Smoke levels off after a while, doesn't it? It doesn't continue off into space. It levels out in the atmosphere and disperses, right? The helium balloon would do the same thing. It would find its level and then disperse and sit in that level until it leaked out the balloon or whatever. And when you pull it underneath the water, because you're adding mass to the medium that the balloon is now in, you're giving it way more mass. That's further away from its equilibrium point. Well, it's trying to find its equilibrium point, but for the helium balloon, it's up. Well, the human is far more dense than air rather than less dense than it. So its point of equilibrium is down. So if you were able to continuously add mass to the density of the air that we're in, so that it gradually became more and more dense, and it ended up being like water, which we know that we can float in, then you would gradually slow your rate of acceleration to the point where you then stopped. And if your water got more dense than you would then start to go back up again and you would then float. So when you say, why don't you float off into space? It's because you're attracted towards your state of equilibrium, but you don't go against your equilibrium into space. You go in towards it. So you would have to go in towards the more dense material, because it's relative density that controls the direction and the vector, the scale and the magnitude, the direction and the magnitude. It is relative density that causes that. And we can prove it just by sitting in water and breathing up and down, and you rise and fall based on how much air you have in your lungs.
Yeah. So in your own words, you're attracted to your state of equilibrium.
Yeah.
That's gravity.
No. Gravity is the effect of the curvature of space-time caused by the uneven distribution of mass.
Which is the explanation in a lot more detail of what you just said.
No, because what I just said about the relative densities, we manipulate the medium or the subject and we cause the acceleration within scientific method. We satisfy scientific method, and we can experiment, and that is what we can prove. We can prove that it's the relative density.
What you're manipulating there is the amount of buoyant force and the gravitational force at all. But you're basically observing the same thing.
No. So, have you seen my egg test? Have you seen the egg test that I did?
Yeah.
So in that egg test, I didn't manipulate the buoyant force. I added salt to the water, and that salt is mass. And it changed
you made the water more dense, which means that, relatively speaking, the egg was more buoyant.
Yeah, but now you're inferring an extra cause.
No, I'm saying that's your description. That's your description. You're saying the egg will go up if the thing that it's in is more dense. And that's exactly what happened.
Yeah, but I added mass. And remember, in a scientific experiment, your independent variable, the thing that you would manipulate, is the presumed cause. You then manipulate it and see whether or not you cause the effect that you think you're going to cause. If you do, you accept your alternative hypothesis. If you don't, you accept your null. Now, in my one,
So
I'm
your presumed
manipulating-
cause is buoyancy. So now explain buoyancy.
No. My presumed cause was identified in the video as the density of the medium, because that's what I was going to manipulate.
Buoyancy.
No, density of the medium.
The density of the medium, yes, relative to the density of the object. That's
Correct.
buoyancy.
No, it's not. That's
That's
relative to the
literally the
density.
definition of buoyancy.
It's not. You're inferring that there's a force there.
I'm saying there actually is a force there because there's no bloody way that egg would move unless there was.
But the force isn't buoyant force. The force is pressure, because we're adding mass below it because the salt's more dense than the egg. The mass falls below the egg, changes the layer that the egg is sat in because you're adding mass below it. So that's creating a layer underneath that wasn't previously there of more dense material that lifts the whole layer up a little bit, and that's why the egg moved. So you're seeing the visualization of pressure go into non-pressure, but the egg's the vehicle that does it.
What you're literally describing there, I mean, it's pretty fundamental, but what you're literally describing there is buoyancy. You're just saying don't agree with buoyancy because
you're attributing what you're doing is changing the scale, saying buoyancy, force up, down, and I'm saying I wasn't working in scales of forces, ups and downs. I was working in a scale of less dense and more dense. I added mass, and I increased the density below the egg, because you can see it fell below the egg, and then once it got below the egg and it found whatever settlement position it's in, as the quantity below the egg increased, that then pushed the egg out of equilibrium, and the egg needed to find its equilibrium point again. Well, that's pressure going to non-pressure, not buoyancy, pressure. So the cause was adding mass, and the effect was changing the pressure gradient, and you see the visualization in the egg.
Yeah, what I'm saying is we both agree on the observed reality of what happened in that experiment. What you're disagreeing with me on is the terminology used. It's purely terminology at this point.
No, it's not terminology. You're adding or inferring a force that is already accounted for by adding mass. You change the pressure.
Eggs don't move on their own, and stuff doesn't just fall to the earth on its own. And something has to cause that.
You didn't listen to what I just said. What you've done is you've inferred an additional cause that's already addressed by what I did in the context.
The problem that you've got is you're saying, well, stuff just goes into this equilibrium state. It goes to the right high or low. More dense, less dense layer, right? More dense, less dense layer. Okay, it goes into the appropriate layer for what it is. I'm saying that, yes, that is combined, right? Whether you agree to it or not, but that is combined what science understands as gravity and buoyancy put together.
But gravity is the effect of the curvature of space-time, and it's caused by the uneven distribution of mass. So again, you're going to now.
You can keep quoting the definition. I'm fine. I agree with that. I'm not going to disagree with you on that. But what I'm saying is, what you're explaining, just in different terms, is exactly the same as what gravity and buoyancy are explaining.
It isn't, because gravity and buoyancy are inferring an additional force that's already considered and demonstrated within scientific experiments. That force is pressure. Added mass below the egg, that increased the pressure below the egg, it pushes from the underside up. Now, you call that a buoyant force, it's actually pressure, not buoyancy. And we know it's not buoyancy because buoyancy depends on gravity to exist, and we know gravity is the curvature of space-time. So the opposite of gravity in this context would be the non-curvature of space-time, right?
Yeah. So you're varying pressure.
Yes.
That's your explanation. You're varying pressure, which is the cause of the egg moving.
I varied the mass only below the egg. As that pressure, as the mass increased below the egg, that caused a change in pressure, and the egg moving is the visualization of pressure going to non-pressure. The egg moving up was pressure going to non-pressure because you've added pressure below it. So the egg's not actually receiving any force. It's just showing a change in pressure.
Let me propose a further experiment that you can do yourself, right? That same amount of salt in that same water solution with that same egg, okay? This time, take the salt and make sure it's completely dissolved in the water, so the salt isn't sat at the bottom of the water. and I bet you the egg will still float, even if you push the egg all the way to the bottom of that glass.
Hang on, slow down. I bet you the egg would still float. Do you mean it would still suspend itself in the middle?
So as you added salt, the egg rose up, right?
Yeah.
If I remember rightly from your video. And my explanation for that is the egg rose up because the amount of buoyant force imposed on that egg and the salt solution that you had in the water, it meant that the water and the salt collectively presented more buoyant force than the egg was exerting on the water through gravity. So therefore, the egg was considered to be buoyant, and so it rose up. Okay? You're basically saying right now that you poured the salt in. The salt all went to the bottom, and therefore that pushed the egg up. I'm saying do the same experiment, completely dissolve the salt, and I bet you the egg will still rise up when you push it to the bottom of the glass.
Yeah, but I bet you the egg would still rise up when you push it to the bottom of the glass. Do you mean when the salt gets to the bottom of the glass?
No, I mean when the salt is completely dissolved, so you have what looks like clear water, but perhaps slightly cloudy because it's got lots of salt in it. Yeah?
Yeah. Yeah.
Then take the egg and push it to the bottom of the glass, and it will rise up to the top of the glass again.
Yeah, because you're pushing it out of its equilibrium point. You essentially you're pulling the balloon underneath the water.
But the point that you just raised was that there was more pressure pushing up on the bottom of the egg because the salt underneath it was pushing the water up effectively.
No. You what you've done is you've changed what I said into a buoyant force, and that's not what I said. There is more pressure below the egg than there is above it. The egg's got a density, and it'll sit in the layer that is the equilibrium point relative to its density and the medium around it. So it finds its harmony, its equilibrium point, right? So
right. So my counter to you then is to show scientifically that the pressure below the egg is higher than the pressure above the egg when it's suspended in the middle of that water.
So what you're basically saying is that you don't think there's a pressure gradient in that container?
In the small amount of water that you had in that glass, I would say no. I would say that the amount of pressure that was acting on that egg was probably uniform throughout that glass, and it was enough that the buoyant force took over and pushed the egg up in the water. However, you seem to think that the difference that you were making was that the I've got to be careful about my terminology here. The not buoyant force, the density pressure, was greater below the egg, and that was what pushed it up. So the way that you can prove your theory is to show that the pressure is higher underneath the egg and lower above the egg.
So that means that you deny that there's a gradient, a pressure gradient in that container.
Yes.
So that all I need to do then is just show you any density tower and say that is a density gradient. You're just seeing it with colored liquids to emphasize the point. But if you dispute that there's a pressure gradient inside that glass, then I would say there's no reason for you to deny that. It's blatantly obvious that there has to be, because I'm adding the mass to it. Where does that mass go? You see it go to the bottom. So that adds mass below the egg.
Oh, so you're thinking like, I don't know, if you poured, say, oil into the glass, they would separate into their own layers. And your thinking is that it's that, essentially.
I'm disputing the allegation or the query that is that there's no density gradient because it's too small a quantity. Well, if there was no density gradient, the egg couldn't be sat anywhere in the middle. It would have to be either on the top or on the bottom.
So here, and it might be that we talk cross purposes and I've misunderstood what you're saying, but the impression that I got was that you were saying that within just the water itself, so let's forget about the egg for now, right? There is more pressure at the bottom of that water than there is at the top of that water, just in the water.
There's more mass.
More mass.
So remember what pressure is defined as. It is force per unit area. So the area is the glass, and the force is created by the mass that I added pressing against the containers. So that is creating pressure. Do you agree?
So help me to visualize this. If I have something at the bottom of the glass the tower of water, so let's say I put, I don't know, a penny in the bottom of the glass, right? The amount of pressure that's on that penny, the amount of pressure that's on that penny in the middle of the glass, those are two different amounts of pressure, is what you're saying.
No, I would say that they were the same. No. Oh, right, I see. So you're from the bottom of the swimming pool to the middle of the swimming pool. You know that there is because your ears prove that when you go to the bottom of the pool. You can only go so deep before you have to pop your ears, right?
Right.
So that proves that there is a gradient mass. There's more mass above you. The deeper you go, there's more mass above you that's pushing down on you. Do you
Okay.
agree?
So if you're around, I would call it density, classic flat earther density buoyancy argument, and you would say, okay, it's just more density, less density, right? But it's force, density-based force, right?
No, you've made two big leaps there. When you say it's the classic density buoyancy, that is
Yeah.
density buoyancy is the 2016 argument. It's been superseded now. We don't use the
Yeah.
word buoyancy as force, so we don't
Sure.
call it buoyancy. It's all different scales or different density, different quantas of density, and it's relative to each other. So let's not call it density and buoyancy. Let's call it less density and more density.
Based on density is your argument here.
Based on disequilibrium. Yeah, if they're in a state of disequilibrium, they've got energy and they will move.
What does disequilibrium mean?
When F equals ma and they say an unbalanced force,
Okay.
well, when an object's in equilibrium, it has balanced forces acting on it and it's not moving. But the minute there's an imbalance, equilibrium, if there's an imbalance in the state of equilibrium, that object has got the ability to move, and it will move if it's not stopped from moving, which is what the egg did, not stopping it.
So why do objects fall down in a vacuum? And why do they? And the other thing is, why do they not fall down when, like, say, in the comet vomit, and it takes a dive in air?
Okay, so let me deal with them in turn. The reason why objects fall down in the vacuum chamber, again, let's change, instead of calling it up and down, all objects have got mass and all mass values are greater than zero. But if you've removed the medium so that the medium is now zero, all objects of any, they're all greater than one. And there's no medium to work against to give you a controlled descent. Because that's why, because when Felix jumped out the plane, he was originally traveling at about 800 miles an hour. And as he started falling through the atmosphere, he slowed down to 120-ish. Then he pulled his parachute and landed. Well, that atmosphere was creating an element of, yes, there was friction caused by air resistance. But as the density is increasing, that's slowing his descent as well. So it wasn't all caused by air resistance. The medium was getting more dense as he was falling through it. And that's part of the reason why he was decelerating whilst he was falling through the air.
Yeah, we refer to that as terminal velocity when they're at the speed that they can go no faster.
Yeah,
and they end up slowing.
Because Felix was falling such a big distance, in that distance he was falling, the density was increasing as he was falling. Now that brings with it air resistance as a slowing down factor, but the density is also increasing. So part of the reason why he slowed from 800 to 120 was because of air resistance, but also part of it was because the density was gradually increasing. Now, if he was to gradually increase that density and continuously increase it so that it became the density of water, so instead of having a hard water line, it was a gradual gradient into that water, he would gradually slow down from 120, 100, 80, 60, 30, 20, 10, 5, 4, 3, 2, 1. He would gradually come to a halt. And then if the density of the medium got to the point where it was more dense than him, he would then float in the water in the same way that you take a gulp of air and you float on the water. So it's all relative to the medium and the object in question. But because
Just give me a minute. Be right back.
Okay. Has he had his din-dins? Oh! Have you had your din-dins? Have you? Emma UK, are you still there? Bev, are you still there?
Yeah, I'm here.
Are you actually listening?
Yeah, but I've also got a live stream running as well.
So
I'm
if
listening,
our
Tone.
friend came in before, this would have been the conversation we would have had if he could have got to definitions and stuff. But this guy's done it. The other guy couldn't.
You took a much softer approach this time, Tony. I'm proud of you.
I actually did the same thing. The thing that changed was the bloke that was on the receiving end was a lot more.
No, it wasn't.
Yeah, it was.
No, it wasn't. We'll agree to disagree then.
But we love you, Tony.
I wouldn't go that far.
Well, this is how you beat them on gravity. It's just how much do they want to fight?
This one's putting up quite a good resist.
He's the best argument for gravity I've had so far. He's been able to logically and progressively work his way through, but he's still coming to the point where he's about to die. He just doesn't necessarily...
Maybe why he's just run away, Tony. Maybe he's
he
figured
just
out.
Doesn't want to admit it at the moment.
Maybe he's just figured out he
Because
can't.
this is it. At the end of the day, the scale. If the scale is up and down, then he needs a force. But we're
Don't give your argument away. He might be listening.
Sorry about that. I'm back. So
okay.
yeah, so my objection to this basically is Felix jumps out of his spacecraft or whatever and starts plummeting towards the Earth. So your argument there is, okay, he's more dense than the air, so he's in a state of disequilibrium, to put it in your terms. So he's naturally going to start falling towards the Earth. Okay.
No, not towards the Earth. He's seeking his equilibrium because the density gradient he's in he's pushed into a state of disequilibrium, and the more dense matter is not where he is. Because he's in disequilibrium.
So there's just one massive glaring problem with this.
Yeah, go on.
The moon is not like falling to Earth right now.
The moon? What's the moon got to do with anything?
It's a whacking great big chunk of rock, and it's just sitting there.
How do you know it's a chunk of rock? Can spaceships land on it?
Yeah.
How do you know?
Because we've been there.
Oh, right. So you believe that we've been the moon?
Well, I've seen the moon fairly close up through my own telescope, and I'm pretty reasonable in saying that it pretty much looks like a big chunk of rock to me.
Yeah, it does look like that way, and I agree. It does look that way, but the problem is they say it's in the vacuum of space, and we know that it can't be a vacuum of space because you can't have gas pressure in it. So if the moon is in the same medium that Jupiter is, then it can't be in a vacuum of space. But I mean, to be honest, I'm not seeing how this is logically following the problem we have, because you said this is a massive problem, but I don't see where it connects. What's the connection between the moon and what we're talking about?
Well, so the issue is directionality. Is like this equilibrium requires that there is equilibrium, which means that there's a known state of where things are, like in terms of like, let's call it elevation, right? From zero, there's a certain height at which everything lives, essentially, unless acted upon by something else. So, for example, the reason why we're not all suffocating right now in a layer of carbon dioxide is because you previously described, there's a water cycle, an air cycle, a carbon cycle, and things. So that mixes everything up. So I'm happy with that. I'll accept that on face value.
The sun mixes all that up.
Yeah.
The cause
Okay.
of all that is the sun.
So the sun is another interesting point of contention, because obviously you don't agree that the sun is 93 plus million miles away or whatever. So how high up is the sun?
Well, hang on, let's try and close off the previous point with regards to the equilibrium, because I thought we were just about to. We're getting to. You asked me about the vacuum chamber, right? And I said, whilst you've got the scale which you've got as up and down, because your question was why do things fall down in a vacuum? You accept that my explanation is all to do with mass relative to its medium, density relative to its medium. All objects, be it molecules of gas or atoms or liquids or solids, they've all got mass. Therefore, they've all got a value greater than 0. But if you make it a vacuum, the best vacuum that you can ever get, as best as we can get it, you are essentially reducing the medium from a 10 to a 9 to a 7 to a 3 to a 1 to a 0.5 to a 0.2 to a 0.1, and you're getting less and less and less all the time. But relatively speaking, the masses that you've got are keeping their mass. So they're essentially getting more heavy, or like you would say buoyant or less buoyant or whatever. But you're manipulating the medium to remove the medium, so it's now a zero value. Now, we know that light is a massless particle, or we're told it's a massless particle, and we know that light still penetrates through a vacuum. But all other matters, objects of mass, are unable to be supported by the density of the medium, because you've removed the medium completely and given it a zero value. But all masses are greater than zero. That's the reason why there is displacement. But it's not up and down. It's just more or less dense. But you've removed the density, so it hasn't got any medium to work with anymore. But if you could find a nanoparticle that had a similar density, because you can't make a perfect vacuum, but if you could find a nanoparticle that was so small, you could probably get it to manipulate within the medium, within the vacuum itself. But because you're defining the direction as up and down, you're saying that means there must be a force, or there must be a center of Earth, or whatever. But I'm saying that the actual true scale should be more and less dense, because that is what you're manipulating. And because
so what
science,
I'm trying to say is,
yeah, but hang on. Because science says that in an experiment, the variable that you manipulate is the presumed cause, and you are manipulating the density of the medium. That proves that the scale that you should be using should be more dense and less dense, because all you're doing is creating a less dense medium.
so if we're working on the more dense, less dense scale, and we're saying, okay, everything fits in that scale somewhere, what defines the directionality of that scale?
More dense, less dense.
Right, but like if I said more dense was down and less dense is up, what's defining up and down as opposed to left and right?
The human.
So that doesn't make any sense. What's causing an object to go down?
The human is now defining more dense and less dense as up and down. If you take the human out of it, there isn't a direction. You've just got more dense and less dense, and you can prove it with the egg and water. If the human's not there to give it a direction, then it hasn't got a direction. You've just got a magnitude, because that's the measure of equilibrium over disequilibrium, and the direction, which we call up and down, left and right, forwards and backwards. You've got that perception given by the human. But we know.
Okay. No. You've misunderstood what I'm saying, right? So your experiment with the egg in the water with the salt, right? You're saying that you being there and pouring the salt in is what causes the egg to rise up, right? But I'm saying naturally, if that occurred, the egg would still rise up, whether or not there was a human involved or not. But why would it rise up? Why would it not go left or right?
Because the human is giving the direction a noun we call up. But the direction isn't actually up. Up is a relative direction that the human defines. We know the direction is relative. It's caused by the mass, because we're manipulating that, and that's giving it the change in the direction. But because we call
no. Right. Look, if I say the sky is blue, and we're saying, okay, fine, I've given it that term blue. Fine, that's acceptable, right? But I can't just then arbitrarily say, well, it'd be like me saying, well, why isn't the sky green, right? Why is it blue as opposed to green? You've got to provide that explanation. So it's like, why is up? Why isn't up like left?
This is where DP said it earlier on to you. We know that the sky is blue. We call it blue, and it's not contentious that it's blue, because that's the name that we give to the tone, the color that we perceive that we call blue. But it isn't contentious. But if I said blue, you're colorblind, it's actually red, and now it was contentious, then we would have to argue why is it red? But the point is that we give these things these names that we call nouns to distinguish from one from the other. But that doesn't change the fact that when we add mass and it changes a direction, the fact that we call it up and down doesn't mean that up is an absolute. Up, by definition, is a relative direction. Up, down, left, right, forwards, backwards. They're all relative to a human. If there's no human there to give it the direction, then you haven't got a way of describing it so that me and you can understand what we're talking about. But that doesn't mean that the egg doesn't move.
Bad analogy on my part, using color. Maybe it was like, what I'm trying to get at is, why is less dense, and why is more dense, as opposed to the other way around, for example? Or why is like more dense not to the left as opposed to below me? Like, what gives that directionality? What gives the universe that?
Okay, all right. So the answer for up and down in the context of mass is the mass itself, the quanta of the mass itself. So as the mass increases, that gives you a disparity between the previous value and the one that you have now, greater than and less than. That gives you a direction, and we call it up and down. But to get it to go lateral, you need to increase the volume of that mass. So if you want to get an object to move, displace sideways, and its density is 7.5, and it sits between a gradient of 8 and 7, and it sits in the middle like the egg. If I want that egg to laterally displace, I've got to add more volume of 7.5 mass, and then it will displace laterally like smoke does.
So you're saying if I have a swimming pool and I fill it with eggs, the eggs will go sideways instead of up and down?
No. I'm saying that listen.
They're still going to want to go up and down, right? But they're just going to have to go round each other, is what you're saying there. But what I'm saying is, why do they go up and down as opposed to not sideways?
And the answer, so the reason why they go up and down is because of mass. The reason why they go sideways is because of volume. So in the density gradient, right, let's just say at the less dense, you've got 7, and at the more dense, you've got 8, and the egg is sat in the middle at 7.5 density, right? These are relative numbers. If I want the egg to laterally displace, I've got to add more volume of 7.5 mass, and then it will laterally displace. And we know that because you can't fill a bucket of water with vertical strips of water. You fill it up by pouring the water in, and it goes laterally first, and then it starts to go up. So to get that lateral displacement, you've got to increase the volume specifically to that mass. So for me to get the egg to displace sideways, I've got to put more mass in of the same density as the egg, but just increase the volume of it, and then it will displace sideways. But we call that sideways, left and right. But really, what you're doing is increasing the density of that specific part of the density. You're just adding more volume, and you can test that yourself. If you get 3 layers of milk, water, and oil, let them separate out. Whichever one the middle one is, if you add more volume, it'll add height to it. But if you've only got a bead of it initially, and it's just one blob, if you add more volume to it, you're going to get 2 or 3 blobs, 5 and 6 blobs, and they're going to go laterally before they go up and down, because they can't move up and down because they're in their equal point, their equilibrium.
Yeah, so what you're basically saying is if I've got a glass with some water in it and I pour some oil in, then they will separate into their layers and then spread out within their layers. That's not quite the question I was asking. So, yes, they separate into their layers, and yes, they spread out in those layers, but those layers are... I'm trying to think the best way to put it. So if we have in the globe model, if we have just a ball of water, a blob of water in space, it will ball up, right? Because of gravity. That's it. So like raindrops, for example, are mostly round, but the air pressure on them causes them to deform slightly.
No, that's not right. But go on.
Well, okay, that's the explanation given by science. You can disagree with that. That's fine. But what I'm saying is
the reason why water falls a droplet shape is not because of gravity. It's because of surface tension.
Yes, that's what I'm saying. It's deformed by the atmosphere pressing on it.
No, by surface tension, not by gravity.
So if you had no atmosphere and you just had gravity, then I would expect that ball to just fall as a ball, right?
What gravity? Which gravity? Einstein, Newton?
Well, they're one and the same.
They're not. One's a force, one's an effect.
They're both describing an effect from different points of view.
No, Newton's was a force.
No.
It was not an effect.
Okay, we can continue to disagree on that point, but I would say that what they describe when you apply the mathematics to, if you want to compute like when something's going to hit the ground, you can use either equation and it would still work.
Let's go back to the egg, right? When that egg is sat in its neutral point in the middle, right? I can make that egg move in any direction I want. I can make it move up or down, left or right, by adding mass or removing mass, or adding volume of the same mass or removing volume of the same mass. I can make it move. Now, all of those directions are called relative directions, and they're relative to the human. If you have
how would you make how would you make the egg move sideways?
I've just told you, add more volume of the same density.
So what? You would add another egg?
No, add more volume of the same density. So remember, layers. All the densities are in layers, and they're all numerical, and they're all gradiented because of their mass.
Right, so but you've got an egg suspended in your water solution. How would you make that egg move sideways?
Add more volume of the same density. So whatever.
Right, I'm talking about real world here. What do you mean by add more volume?
Right, so let's
add
just
more
say
egg.
Let's just say that no, not egg. You want the egg to move, right?
I want you to say, okay, based on what your understanding is, you're saying without touching the egg at all, right? But just affecting the environment that egg is in.
Yeah.
How would you make the egg move left to right, as opposed to up and down?
Right. For the third time, and this is what I want you to listen to what I say. I will add more volume of the same density. Because if it's the same density, it can't go up or down. But if it's got more volume, it'll push against the egg. So if I add more density either side of the egg, and it's the same density as the egg, there's only one place that density can go, left and right.
So that's like my example of pouring oil into water. The more oil you pour in, it's going to spread out until it covers the whole surface, and then it will layer on top of itself. But it will spread to that point.
Correct. Yeah.
Right. But so I guess what I was getting at here is that like you can cause it to move next to itself, move side to side by basically having like liquid, for example, spread out, right? But then that's applying or adhering to effectively the laws of density, buoyancy, and then surface tension on top of that.
No. It's not got nothing to do with surface tension. It's got nothing to do with density or buoyancy. It's relative density.
But this isn't explaining the directionality is my issue.
Yeah. But what you're perceiving as the directionality is the term that we describe the direction that we're seeing. Now, the reality is the direction is controlled by the relative density, right? More dense or less dense, it moves up or down. If I want to move it laterally, I add more volume of the same density, and then it'll move laterally. But we describe them as up, down, left, and right. But because we're manipulating the density, the real scale should be more dense and less dense, because that is what we're manipulating within scientific method and experiment. So we call it up, down, left, and right. But this is why I was saying to you, if with that scale, you're then going to start saying forces, but we're not manipulating any forces. We're manipulating masses. And within science, the independent variable is the presumed cause that we manipulate. We're not manipulating forces. You're implying that we are, but we're actually manipulating mass.
So, okay, so based on your deduction from that experiment, you're saying that the density is causing more pressure on the thing that's suspended in it, or less pressure on the thing that's suspended in it, and therefore the thing that's suspended in it relatively to it is more or less dense, and therefore moves into its own new equilibrium state by moving up or down.
Yeah.
Okay, so the challenge that you have there is to show that relationship in scenarios that apply at the level that, for example, relativity applies. So show that applying to the whole galaxy.
Right. Why have you made the quantum leap from real-world scientific experiment where we manipulate independent variables into a Narnia-esque environment that does or doesn't exist, that only exists mathematically by expression by Einstein?
Because the level that you're at the moment is essentially just prior to where kind of Newton was at, right? You're saying that Newton doesn't apply, but I've got this kind of basic analysis of kind of how I see things working. But you have to show the relationship of how that fits, and then mathematically model it.
I can. I've shown the relationship by manipulating the independent variable. It caused the effect. See, what you're saying is you're trying to dilute the position I'm actually in, which is within scientific method. You're trying to dilute that by saying that doesn't go far enough because we want you to go into Narnia. And I'm saying, no, if I go into Narnia, that means I'm moving away from experiment. And Max Planck said, anything without experiment is poetry. I'm not prepared to go into poetry to satisfy your curiosity as to what I'm going to then predict for the intergalactic scale. I'm not doing that. Experiment is the only sense of knowledge at our disposal. Everything else is just poetry.
Right, but Max Planck didn't ever state that he didn't agree with Einstein.
I never said he did. That's a red herring, a straw man.
Okay, so Max Planck accepting Einstein, because Max Planck, as I understand it, was the guy that came up with the Planck length, right? Which is
Max
essentially
Planck,
one unit of distance. Is that right? Or
Max Planck said, without experiments, you're left with poetry. Now, I'm not saying whether he agreed or disagreed with Einstein, but I would predict that with Einstein not having any experimental application, Max Planck would say it's poetry. Because there is no experimental application with Einstein.
Okay, relativity does have applications. I mean, we're using relativity today.
We're not. Remember, Einstein's theory of general relativity is a mathematical concept based on 4D space. Mathematical concept. It's reification. There is no experimental application to it. You can't test models in maths because they just exist in maths. You need to experimentally validate or refute something. How do you validate or refute with experiments a mathematical concept when all maths is always correct?
Well, you can argue that it is just a concept, but it's a concept that has real-world ramifications, and we've got technologies built around that mathematical model. So the model clearly works.
No, it doesn't. It's a mathematical model. It's reification. Show me an experiment, real world, where it's been applied.
Well, I can show you technology where it's been applied.
Right. Experiment, not technology. Technology is not science.
Well, technology is the application of science that has been agreed as correct.
Okay, so which science has been applied with the technology that you're now going to rely
on? So relativity, essentially. If that's the subject that we're on. So if we're talking about things
not
like,
really.
for example...
Not really. We haven't really concluded off the egg point with regards to relative directions, up, down, left, right, forward, and backwards. Because I want you to accept that the up, down, left, right, forwards, and backwards is relative directions to a human, and we give them the names, but really we're not manipulating any forces. We're manipulating the mass, and the effect is the change in pressure, which is visualized by the egg moving. But the scale should be more dense and less dense, and we're manipulating the mass. Therefore, if you keep it as up, down, left, right, forwards, and backwards, you need a force, but we're not manipulating forces. We're manipulating the mass, and that's changing the pressure as per the definition of pressure within scientific method, which is mass per unit volume. That is what we're manipulating.
And so what's your definition of pressure?
Mass per unit volume, isn't it? Mass per unit volume.
Okay, so how do I measure pressure? What am I measuring?
It's the interaction of the molecules against the walls of its container.
So I'm measuring the amount of force applied to that container.
Yeah, like gas pressure or water pressure.
So the reason why your egg either floats or sinks is due to a force.
Yeah, one that we've manipulated, not one that we've implied or demanded that is there. One that we've manipulated.
Right, so you've manipulated a force.
We've manipulated a mass. We've manipulated the mass, the relative mass. That's changed the relative density, and that has produced a force. And we see the force with the egg moving, not the egg being pushed or whatever. We see the representation of the force because the egg's now moving to its new position.
So force is applied to the egg, and you're seeing the effect of that force.
The change in the pressure, yeah, because as you add more mass per unit volume, you increase the pressure.
Right. So what science describes as that force is buoyancy.
No, it describes that force as pressure. Mass per unit volume.
So pressure is how we're describing the effect of a force.
No, it's defined mass per unit volume.
Yes.
So I've
So-
added mass, but the volume has stayed the same. So because
So
I've added
if-
mass,
If a force is deemed to be the cause, pressure is the effect.
adding mass is the cause. The change in pressure per unit volume is the effect. The egg moving is the visualization of pressure going to non-pressure entropy.
Right, but you said there's pressure, and you said there is a force, and we're manipulating the amount of pressure by adjusting the unit volume.
By adjusting the mass per unit volume, not the unit volume, the mass.
Yeah, sorry, I shortened it. Apologies. I didn't want to misquote you. So I'm adjusting the mass per unit volume, therefore I'm adjusting the pressure, and that is seen as the effect of a force on the egg, which is the pressure.
Yeah.
Right, that pressure we describe as buoyancy.
No, we don't. We describe it as pressure. Mass
Well,
per unit.
pressure isn't a force.
It is. What do you think blows balloons up if it's not pressure?
Yeah, pressure. Pressure is what we're measuring. The thing that's causing pressure is a force,
No, it's the mass per unit volume,
which is a force.
which causes a force. That's correct.
And it's the force that will push the egg around.
Correct.
So it's a force that blows up a balloon.
Pressure.
So it's a force that causes air pressure.
Correct. Pressure.
Brilliant. And it's also a force that will cause a guy that jumps out of a spacecraft to fall to Earth. It's a force.
Let me think about that. It's a force that. What did you say? Say the word in again.
So what you're unilaterally saying here, this is where I'm going with it, right, is when something moves from a disequilibrium state to an equilibrium state, using your terms, that the act of that movement is the cause of it is effectively a force.
The cause
is that pressure change.
The cause is the mass itself, and the pressure is the effect. So if you've got the mass, or you add the mass, or you remove the mass, that's the cause, and then the effect is the movement, the acceleration. Pressure, caused by pressure. Mass per unit volume.
Pressure's the effect that we see, and the cause is a force.
No. Adding or removing mass is the cause, because it alters the mass per unit volume, which we call pressure. It alters the pressure value, the variable, the value, the pressure value.
Yeah, we're adjusting the amount of force or adjusting the amount of pressure. We're saying the same thing.
Yeah, but we're not changing buoyancy or gravity. We're changing mass.
But what I'm trying to explain to you here is when you're measuring a force, we have names for those forces.
Yeah, we call this one pressure, not gravity or buoyancy.
Well, okay, you're quibbling over terms now, but
not really. Quibbling over terms. This is the fundamental misunderstanding and this dishonesty on your guys' side that say that it's gravity that's doing it, and it's not. We're manipulating the mass, and that's what's doing it. Mass per unit volume. It's not quibbling, it's paramount.
Okay, I think we're going around in circles at this point. But
no, this is the bit where you died, and you just realised that you died.
Well, so you accept that things don't just move on their own; they move due to pressure or a force, causing them to move.
Yeah,
right.
Yeah.
So if I have, for example, like Brian Cox did in his vacuum chamber, I have a hammer and a feather, and I let them loose in a vacuum, they're moving because of a force. Something is causing them to accelerate.
Yeah, you've removed the medium that they were in. Your mass is now much greater than the medium of 0 because all values are greater than 0, and there's no air resistance to influence the rate of descent. So because they're in a state of disequilibrium, they've got energy, they're going to move. For the same reason that hot goes to cold, pressure goes to non-pressure. We don't know why hot goes to cold, but we do know it does it. It's the same with the pressure, and it's the same with the density. Because you've got no medium to support it, to interact with it, you've got 0, and all the objects have got mass, and there's nothing there to interfere with its fall rate, then it's going to displace the medium it's not in anymore because all values are greater than 0. And we know it because you can get it to a point where it's equal, like the egg, equal to its medium it's in, and it doesn't move at all.
Right, but these two things are not equal, right? So the egg being in water is the combination of things. When we're just dropping a hammer in a vacuum, there is only one thing going on here, right? These two things are not the same.
Yeah,
So
medium equals 0, mass equals greater than 0, and whatever value what you want to give it, be it a feather or a brick, it's still greater than 0. They're in disequilibrium, but because the value is 0, you've got nothing. You've got nothing to interact with any mass.
So, right, but you've got a mass, you've let it go, and now it's decided it's going to go and move in a direction.
In the same way that hot goes to cold, we don't know why it does it. It just does it. I would argue, and I'm not religious, but if I was religious, I would argue that hot goes to cold because that's the way it was designed. I would equally argue, and I'm not religious, but I would say that mass goes to non-mass or pressure goes to non-pressure because that's the way it was designed. And in this case, you've got no medium for the mass to react with. You've lifted it off the ground into a state of disequilibrium, and it's got no fall or rest underneath it to influence its path. Now it moves because you've just let go of it. There's no medium stopping it from moving.
So I feel like there was a point there where you sort of contradicted yourself.
Okay.
But my daughter interrupted me, which was really frustrating. So, okay, we've agreed that things don't just move on their own. They move because of a force.
Yeah.
And then if we take away the medium, stuff still moves because of a force, right?
Yeah.
Right. So why does stuff move in the direction that it moves? Because arbitrarily, it could go in any direction.
No. The direction, right, so we're back to relative directions. The reason why the object is moving in what we call down is because we've called it down. But really, in the vacuum chamber, it's moving in the direction that we call down because it's got mass that's greater than the medium it's in, called 0. There's no medium for it to play with anymore. And you've lifted it into a state now where there's nothing to interact with it. So when you let go of it, it's going to fall or rest because it's seeking its point of mass and equilibrium. But there's a ground underneath it that stops it from moving any further. But
So
you've lifted it into that position.
What there then is equilibrium for every type of molecule or atom in the universe. So if I have, for example, iron, right? All iron throughout the universe has a state of equilibrium, which is at a certain level below sea level, potentially, because iron is heavier than water, right? So there are planets that obviously we can observe through telescopes and stuff that are far away from Earth, and they haven't come anywhere close to Earth, and they're just up there. But why are they up there? Why are they not like making their way over towards us? Why is like the whole universe not coming this direction? Because this is the universal down, right?
Because you're assuming that the lights in the sky are mass. I'm saying that I don't know what they are, but they appear to be lights. And given that lights are massless particles, or many massless particles, or focal points of light, they're still massless. Why would you expect them to be attracted towards Earth if they're massless? You're assuming that they're mass. I'm not assuming that they're anything. I'm just saying that they're lights, and I don't really know what they are. But I know what they're not. I know that they're not gas giants in a vacuum because we can't demonstrate that could be even true. I don't know what the planets are, but I know what they're not.
Yeah, so the example that you're giving is Jupiter, and you're saying Jupiter can't possibly exist in the way that you understand science as describing it existing.
Not the way that I understand it. Jupiter can't possibly exist in the way that we can demonstrate that gas pressure works. We demonstrate that gas requires containment to have pressure. but we can't demonstrate gas pressure without a container. But they're expecting us to believe that Jupiter's a gas giant in a vacuum without any form of containment. I say no, it can't be demonstrated in any way that that's even potentially possible, but you believe it anyway. And I say
So
no.
do you presuppose a container on Earth then?
There has to be a container, otherwise we wouldn't have a gas pressure gradient. It would disperse into the vacuum of space.
But the fact that there's a gradient suggests that wouldn't happen even if there was a container up there.
No, remember, the container is what stops it from immediately dispersing into a vacuum. But the gradient isn't caused by gravity; it's caused by the biogeochemical cycle, which is powered by the sun. So all the gases are created at sea level or ground level. They all evaporate or they all raise. Then they get cooled down. Then they fall again. That's the gradient creation right before your very eyes. You think it's caused by gravity. I'm telling you it's caused by the biogeochemical cycle powered by the sun, and it's repeatable on a small scale if you just put any heat source at the side of a tin can of pop. You will put a heat source, you will create a gradient at a focal point of heat. You will create that biogeochemical cycle in a tin can with a little Bunsen burner. Literally, that's what you do, and we can repeat it.
Okay, so let's say I accept that description of the way that Earth's ecosystem works, so to speak. By that description, you don't need a container.
No, you do need a container, because if you have gas pressure and the equilibrium and the other part of the equation is a vacuum, you can't have any gradient at all if the other part of the equation is a vacuum, because the gradient...
We have gas pressure at sea level, we have less gas pressure at the top of Everest, and we have virtually no gas pressure up where the moon is, or shall we say, okay, where the moon is presupposed to be, because you're not going to accept that the moon is actually a thing. But so there's virtually no gas pressure whatsoever, and that virtually no gas pressure whatsoever is what we call the vacuum of space. And you accept that is possible in your model.
Yeah, absolutely. Because at the top of a bottle of pop, you always have that layer of gas. And then at that top point where the lid is, the pressure is always less. There's more pressure below the lid, and where there's liquid, there's the most pressure. But even half a bottle of pop, there's less pressure at the top. The pressure is all... Have you not seen the Action Labs video where he showed that the pressure inside the bottle of pop is greater lower down than it is at the top?
Okay, so you're insistent on arguing that there must be a container. So let's see if we can prove the container then, because that would be the thing that would convince me if your argument is insistent on it.
Well, let me ask you this: if you get a big piece of sirloin or ribeye or steak on your plate, do you feel the need to go out and prove that there was a cow that it came from, or do you accept that there must have been a cow because you got the meat on your plate?
I've seen the whole process of slaughterhouses and cows and how that works, so I can say, having had that experience myself, I can verify that is actually a thing.
Yeah, and it's also not contentious. Nobody disputes that a big slab of sirloin steak has come from a cow. Not necessarily, you don't necessarily know which cow it was or what field it was in, but you can say with certainty that there was a cow at some point in existence to give you that sirloin steak. We can all agree on that, and it's not contentious. But if it was contentious and cows didn't exist, or we were saying, nah, we don't think there's any, because it's the same as you saying there's no container. That would be like saying cows don't exist. We're living in an environment where there's no cows, but we have got sirloin steaks. And we're saying there's got to be a cow. And you're saying, no, there don't need to be a cow. We just got steak. And we can formulate a formula to explain how it exists.
It's the other way around. You're saying there has to be a cow by saying there has to be a dome. I'm saying I've not seen any evidence of a cow. I've seen meteorites, which I've seen flat earthers say, oh, okay, that's chunks of the dome. So I'm saying, okay, fine, there's holes in the dome then. So why isn't the atmosphere fucking off out into space?
Well, I'm not speaking for other flat earthers, and I'd ask that you don't speak. Don't pin on me what they.
Sorry, yeah, I don't want to presuppose your view on things, but what I'm saying is this is the common argument that I'm used to hearing, if you like, from other flat earthers. But I mean, okay, let's say you disagree with that. What's your position on the dome then?
It's just bigger than what we can get. Right, rockets, when they go up into what you accept as space, is the removal of the medium, and it falls straight back down again. Now, you guys say it's going into orbit, and that's why it starts to head laterally. Well, I think that the minute they go up and they run out of pressure and fuel and they drop the stuff and whatever, they fall straight back down to Earth again because they can't get high enough to do anything. There's nothing up there, and the rocket still has mass. So it's going to displace the medium it's in exactly like a vacuum chamber, and it's going to hit the deck fast because it's got no medium anymore. That's why we can't get high enough to see what we're in. Now, if the argument is, well, where's the container? I would simply say it's beyond our ability to get high enough to even see it. Now, it might be that a rocket could get there, like a small, short, like a missile, not a rocket as in manned rockets, not massive scale, like a thin scale, small scale thing. We might be able to get a bullet or a missile up there, but we can't get a manned rocket up there the size that they build because there's a point of diminishing returns. You can't get, the weight becomes that heavy. You need tons and tons of fuel, but the weight works against you. So you have to make it in like there's a balancing point. But to address your point directly, there has to be a container, and I would love to explore for where, but I know that I've only got a P900 and a compass, and I don't have $60 million a day. But I do know somewhere that does, and I'd like to be able to see what would happen if we did certain things, but they won't listen to flat earthers. But you've just conceded that it would be great if we could look for it, and I agree. But we do have a space agency that could do exactly that. But they don't tell us that there's a dome there. But they expect us to believe that a big slab of sirloin has appeared on the plate, and they argue that we don't need a cow. Well, I'm saying, well, we do need a cow for the sirloin in the same way that we need the gas pressure. We need a container to get gas pressure. So
your analogy is that the slab of steak is the gas pressure, and you're saying the gas pressure can't exist without the container, yet the space agency is saying that the container doesn't exist because they've been up, and here's the pictures of a round, blue marble in space, right?
Yeah, but if you're honest with yourself, I think you'd realize and accept. You won't accept it to me, but if you're honest with yourself, you'll accept that the pictures that they send us back from space do look like cartoon composites.
Now, one thing that I will say is, obviously, I've never been to space, and I don't know what the Earth looks like from space. I have seen things like the live footage that is claimed from ISS. Now, whether or not you accept that ISS is what it is and it is where it is, that's a different matter altogether. And I've also seen, obviously, the published blue marble pictures myself, and I've also seen the arguments that have been levied against them, such as the more recent compositions that have been made of the blue marble. Obviously, we're not able to we haven't been away from Earth for some time, and able to take a complete picture as a single shot. So we've had to build composites. So that's where the whole, it's photoshopped because it has to be comes from, right? So I'm willing to accept all of that as being saying, okay, I cannot personally verify that information for myself, but my counter to that would be, okay, fine. Flat earthers like to point at NASA and say NASA lies, specifically NASA, right? Then when I point out other space agencies, and you've done this yourself, you've basically said, well, they're all working together. And it's like, okay, fine, they're all working together. Brilliant. Okay, I'll accept that premise. So now the Americans are working with the Russians, who are working with the Chinese, who are working with the North Koreans, who are working with the Japanese, who are working with the Indians, right? So basically the whole world is unanimously in agreement on this one thing for some reason, yet the White House can't even hide a blowjob. So what the hell is going on here?
It's just farmers tending to their flock. You've got one farmer on one field, that would be America, and the farmer would be the president. And you've got another farmer on another field next door, which would be, say, Japan, looking after his flock. And you've got another farmer on his field looking after his flock. And they've all got the common interest of keeping their flocks contained. If they're containing the control of their flock is the common interest, if they can control the narrative with space and making everybody think that they live on an insignificant ball in the infinite vacuum of space, and hey guys, you haven't got any purpose to live in, hey, these are what we've got, all the answers, and we can tell you everything to be true, then you've got a problem there because everybody feels worthless. And I don't think that's true. I think that we're all special, unique.
So to my mind, if the Earth is flat, or if the Earth is a globe, and if the Earth has a dome or doesn't have a dome, I really actually couldn't really care less. Like from a kind of ethics point of view, or from a moral point of view, like if I found out tomorrow that it was all true and NASA does lie to us and the Earth is definitely flat, I'd be like, cool, the Earth is flat. The reason why I kind of argue that it isn't flat is that I kind of look at it and I say, well, there's a lot of evidence for a globe, and it all seems to tally up, and the whole world is kind of telling me that the Earth is a globe. And then there's this few flat earthers that are basically saying, well, there's a dome, but we can't find it. There's a way that light works, but we can't really define it. There's a horizon, but we don't really understand it. There's a thing that works exactly like gravity and a thing that works exactly like buoyancy, but we describe it differently. And it's like, okay, fine. So you disagree with everything about the globe model, but then you also actually agree with it, and then you sort of back off when pushed on it because we don't have all the answers yet. And it's like, I don't know. To my mind, it just seems like there's a lot of kind of like going round in circles. And what I would like to see from the, like the globe denying community is, okay, fine, come up with something that has the same explanatory power as the entirety of what is essentially currently globe science, effectively.
But
It
it's
covers
not science.
Well,
It's opinion.
I was going to say,
Well-
I did do that, and you guys raped it and said it was gravity, and it wasn't fucking gravity, was it? It was adding mass. So whenever we try and do anything, you fuckers lie about it and claim that it's something else, and it's dishonest. So how can you explain? And the
Yeah.
other thing is, if we had $65 million a day, we could get you far more answers, right? But we've got a P900 and a compass, and we've just improved them to a P1000. But let's be honest, we haven't got people, we haven't got resources, we haven't got technology, we haven't got anything. What realistically would you expect us to be able to do with fuck all?
Well, the way to go about it is to lean on globers that do have the technology and the money and things, and go to them and say,
Ask you a
look,
question, please.
sure.
Do you think that we've not been trying to get access to things like, I mean, Mark Sargent has challenged M. Scott Veitch to go into a vacuum chamber with a spaceman suit on and see if he survives. And if he does it, then he'll do it too.
I'd do
we
that.
are trying to get that to happen, but it's not going to happen, and we know why, because you can't go into a vacuum chamber in a spaceman suit. But they're
You know
going to
what
say
happened to the last person who went into a vacuum chamber in a spacesuit?
his spit boiled on his tongue and he passed out.
Tony, I think
Yeah.
Redman wanted to ask a question.
Go
I
on.
mean, just a quick question. Since you have in your mind that everything to you believe to be a globe. So why even argue with people that believe it's flat?
So I'm not here to argue. I might come across argumentative at times, but I'm here to understand why you guys reject modern science and things. And for me, it's fascinating from a sort of psychological point of view, so
It's
to
not
speak.
science, it's propaganda.
Well, yeah, I mean that's an interesting point of view in itself. It's like, okay, it's propaganda, but the way to look at it then is, okay, how can I actually prove that it's propaganda, or how can I?
By pointing out that Jupiter can't be a gas giant if the medium it's said to exist in is a vacuum. That's the proof.
You want the layman, you want the me's of the world to understand that I'm being lied to, and the only way that I can see that the masses can take flat Earth seriously is if it's approached with the same sort of logical, complete, and correctness as what is the accepted science, if that
Well,
makes sense.
that means you have to start being honest then, and
Yeah.
recognizing that gas cannot exist in a vacuum. Gas pressure cannot exist in a vacuum without
In the same
a
way
container.
that gravity, in the same way that there's a horizon behind the second oil platform on the Black Swan, and on your model, you tell us that thing that we call the horizon is what boats go over, and we say actually this is proof that the horizon, whatever it may be, is optical, it's apparent, and it can't be the geometric curve that boats are supposed to be going over. Yet you all cite it, and you continue to cite it, and you just ignore it. But there's another good example of something that you guys just refuse to acknowledge. Gravity. We can demonstrate within scientific method that gravity doesn't even need to exist. Now, I don't even care if it does exist or not. But if it does exist, you've got to prove it, right? I can demonstrate that it doesn't need to exist. Now, I can't demonstrate the negative, but you guys have got to prove the positive. And you guys can't even define it correctly, let alone demonstrate it. But you expect us to accept it and believe it. So there's three key tenets there of your principles, your religious views, whatever you want to call it, your narrative, your accepted science, that we say there's a problem here, guys. And all you guys do is go, morons. And we say, hang on a minute. We're saying that you can't have gas pressure in a vacuum. And you guys say, moron. That's not good enough.
Yeah,
How
that's
can you
not
even-
criticize us when
That's-
you don't even treat us with any amount of respect at all?
And
Okay,
that's not
so-
even bringing into it the horizontal plane and
Yeah. So let me address some of the
level.
points. Let me address some of the points that have been raised here, because a lot has been thrown at me at this point, right? So you can't have just gas pressure in a container without the container being there, right? So
You can't have Jupiter.
but when
Jupiter
we're
is an
when we're talking
impossibility.
when we're talking about
the way you worded that, then let me repeat it back to you. You said you can't have gas pressure in a container without the container. Well, that is in essence the problem with Jupiter existing in a vacuum, because Jupiter can't be a gas giant in a vacuum. It can't be.
Right,
I don't
but-
know what Jupiter is, but I know what it can't be.
Okay, but so the point that I was going to make there is kind of you're presupposing that there has to be a container because you deny gravity, when gravity is our explanation for the container.
Well, you don't
Hang
even
on a
know what the
minute.
definition of gravity is. But I'm not presupposing that gravity is the explanation. I'm saying that I don't know what Jupiter is, but I do know what it's not. Now, it appears to be a light in the sky that's pretty. Now, I could argue that that's the way that God made it to make us accept that it must be created, because it's incredible. It defies all known physics. It's moving without any form of fuel. I mean, I can give loads of reasons why it's creation, and that doesn't make me a creationist. It doesn't make me religious. But it says to me that whatever the lights in the sky are that we call planets, they're pretty incredible because physics can't really explain them, because flat earthers are saying you can't have gas pressure in a vacuum. But you've got other people that believe it that say you can. And we say this is ridiculous. Why? This is one of the reasons why a lot of so-called flat earthers become so-called religion guys, like John, for instance. And I'm not religious, right? But I realize that it has to be created, because you can't have, if you start with the infinite vacuum of space or whatever the starting point in time was, be it pre-Big Bang or post-Big Bang with a vacuum in space or whatever, wherever you want to start your point in time for the beginning of the beginning of the beginning, right? Something somehow has resulted where energy has gone into it. There's no two ways about it. Something somehow has created this in some way with energy. That energy has got to be come from somewhere, and it has to have been made in a way that is intelligent. Because I'm sorry, an explosion doesn't result in intelligent design. It's destructive, not constructive. So there's no way that a construct can result from an explosion, right? Now, I realize that it must be created. We can't result from a cosmic ejaculation. Can't have happened. Now, even if there was a cosmic ejaculation, that can also be interpreted as the moment of creation. Because if I was God and I wanted to create something, and I decided that the mechanism that I would use to create it was an explosion, you've got little bastards running around on the earth saying that Big Bang is the beginning of the cosmological beginning. And it was actually God himself making the moment of creation. It's been stolen by scientists that are misrepresenting what's actually happened. But
yeah, there's a lot of misconception around the Big Bang as well. But I'd like to address an earlier point, which was that, I mean, you guys regularly get called every name under the sun, get called morons or whatever. I've tried to be extremely polite with you guys here, and whilst I've debated everything, I've not been rude to any of you, and I'd like to just point that out. I'm being
and I'd like to say this. I'd like to think that I could say the same back to you, because I haven't run away from any point. I've tried not to swear. I've tried not to raise my voice until you said something like, well, why can't all the flat earthers do something? And I'm like, hang on a minute. Every time we try doing something, all we're met with is scorn, ridicule, trying to get people's jobs taken off them, Brian Mullen style. I mean, why does that even exist? You guys,
and we are the only ones that do anything. We are the only ones that get off our butts and go and take measurements and look at these things. All you do is you rely on science. You rely
hang
on
on.
God
Don't
bosses.
do the you lot, and it's.
I disagree with that.
Yeah, it's been a nice conversation, and it's been good to listen to.
But let me re-ask my question, or make my point. Have I been cordial back to you the way you claim that you've been cordial to us? I'd like to think that you would agree that I was cordial back.
Yeah, I mean, I would agree with Emma's thought. It's been a nice conversation to get involved with, and whilst we have disagreed on a lot of points, it's been very amicable, and I think we've gleaned a lot from it about each other's understanding of things. And whilst
I
I
agree.
think that we do disagree on the terminology and to some extent the explanation and the reasoning for things, I think that in the grand scheme of how the universe works, I think that at some basic fundamental level there is some level of agreement that we have. It's just how we choose to explain it that's differing. And I would say that I kind of have, if you like, the mainstream view of things. And yeah, I'm not the most like intelligent when it comes to like the scientific mind. I'm not a nuclear physicist or a theoretical physicist. I don't understand these things at insane levels of detail, but to the best of my knowledge I can say, okay, I understand this stuff for this reason, and I can at least feel justified in having the understanding that I have. But you guys feel justified in having a different understanding for your own valid reasons, and I think that's that's good. If you've got what you feel is a justified reason, then that's great. But it would be interesting to see if perhaps we could come together. I know you're in the UK as well, aren't you, Tony?
Yeah.
Yeah, so maybe there is some stuff that we can do to kind of like go out together and sort of agree on kind of, okay, let's try and figure out an experiment that we can do together and collect the results together and agree on, how to sort of, or there's something that you can do where you can kind of discuss the results in a kind of more agreeable setting. Because when I see a lot of these flat earth debates, it's usually like the Red's rhetoric style of debating, where you do get the you're a fucking moron because you don't get this trigonometry, and then I'm looking at that math thinking, Jesus, I did A-level maths and that's complicated.
Well, the thing is, the one question that would kind of resolve an awful lot of the misunderstandings of flat earthers is why is there no evidence, why is there no experiments and only sums as substitutes for key points that we say are wrong? For example, gas pressure in a vacuum without a container. You've got Boltzmann equations that calculate the probability of gas in a gradient and all that. That's lovely, right? But there's no experiment, and that's being substituted for experiments. And we say you need to have experiments. And then you guys say, well, that's not really how science works. It's peer review papers and all that. And we say, no, we need experiments. If you're going to do anything, if there's going to be any progress whatsoever, we need to see some experiments, because the experiments are it's the only means of knowledge at our disposal, as Max Planck says. That one sentence is paramount for the gas pressure giant known as Jupiter having any credibility whatsoever of existing in a vacuum of space. If there's something that can help us with that'll go a massive way forward for letting a lot of flat earthers at least consider their position as flat earthers, myself included.
Yeah, so there's a valid point in that, is that like if you're going to claim something is true or proven in a scientific sense, then you should at least be able to reflect that. And I think one of my favourite quotes, I can't remember who it was by, I think it was like Arthur C. Clarke or something, and he was saying something like, if you can't explain it in simple terms, then you don't understand it. And if you don't understand it, then obviously how can you claim it's true, right? So,
and that's the reason why when the Rumpus does what he does, I had a conversation with him the other night, and all I wanted to ask him was a simple question with regards to the Gravitron Fairground ride. And his style is to over-explain and compensate so much so that in the end, I was totally confused with what I was supposed to be asking to try and get from him. Now, in the end, I've remembered what it was, and I've gone back to it, and now next time I speak to him, I'm going to say, right, remember that conversation? This is where we're at now. And I've got him, right? But that inability to explain concisely, listen, and explain it in a way that is understood by the person asking the question is an issue. And that's just with the Rumpus. But explanation in itself is only half of the story, because it requires again, I'll say Max Planck, not experiments is the only real means of knowledge at our disposal. Everything else is just poetry. That's true, because we want to see the gas pressure in a vacuum without a container, because that's what they tell us Jupiter is.
So funnily enough, I've had the same conversation with Rumpus, and I've basically gone to him. I've said, look, you can't just come at a flat earther all like shouty and like basically taking the Nathan Oakley approach to debating. It just doesn't work. You're not going to prove anything by shouting someone down. And the point here is not to, as such, prove anything. The point is to discuss the point that we're disagreeing on. And you're not going to have much discussion if you're just talking over people all the time. And he does agree with me on it, but then he goes back to his old habits, which is really weird. And this is the same reason why I don't debate people like Quantum Eraser, because again, he does the same thing. It's very much a gish gallopum of of just like shoutiness, and then you get muted or whatever, and you don't get anywhere. But I have had some interesting conversations with various people throughout the community. Chemo, I notice, is in here. Me and Chemo have had our debates in the past, and we've disagreed on a lot of stuff. But it's been interesting sort of talking this stuff out. And I think the only way that the community as a whole, and when I refer to the community at this point, I'm talking about the globe community and the flat earth community as one big community. The only way we're going to progress is to learn to communicate with one another, agree what our terms are, and then have a discussion on level ground without one side calling the other side a bloody idiot or whatever because they didn't get some aspect that was trying to be explained. And this is why when you start talking about more dense and less dense, and we have the discussion on your terms, because I feel that that's the way that you're more comfortable having that discussion. But I will often then reference back to the density buoyancy thing, which I say, and here's the parallel drawn. And this is where we kind of can discuss what the discussion point is, or what the discrepancy is, if you like, and where the differences are coming in. And I feel like that's good.
They're all lovely, and they're at base 2 and base 3 and base 4, but we still want base 1 covering. We want to see the experiments that demonstrate the things that we're told to believe to be true. So gas pressure, we want to see evidence. We want to see the proof that the Earth's turning. Because if the sunrise and the sunset are supposed to be proof of Earth turn, why is it that planes are not showing the drift that's necessary? Because Coriolis requires that the object that's turning, and we're on that, we should see apparent deflection. So planes that travel east and west should appear to deflect. They should get there quicker and get there slower, and we should see that on every single flight, but we don't see it. So they say, well, conservation of momentum. Well, that's making the excuse for why we don't see it, working against Coriolis, but ballers won't accept it. Do
you not agree with that argument?
No, because if the conservation of momentum is the excuse for why we're not seeing it, well, that doesn't stop the Earth from turning underneath it. I accept that there's a conservation of momentum, but the Earth has still got to appear to deflect. So even when you factor in the conservation of momentum, you've still got a net change in Earth turn one way over the other. You can't demonstrate it. I've got a treadmill here, right? And if I walk on the treadmill one way, it takes me 6 steps to get to the other side of it. If I turn around and walk the other way, it takes me 1 step, and I'm already at the other end of it. So what I'm saying is the Earth's supposed to be turning underneath the plane. Well, even with conservation of momentum, there still should be an apparent drift. It's just smaller, but it should be there every single time, and there is no evidence of it. Weather affects it more than Coriolis does.
So, I mean, there's a certain argument to be had here about the explanation and the way that Coriolis and the way that rotation is explained. And I've actually argued with many globe earthers on this and basically said, look, you guys may have a point, and from my point of view, I can see, but then I've got quite a mathematical head. I'm a programmer by trade. I've been in the industry, 20 years now, and I've modeled a lot of this stuff out in like game engines and stuff, so I can kind of see how the physics and the math interplays. But obviously I'm looking at it from a very mathematical, conceptual point of view, and in reality, of course, you need to be able to relate to people, to be able to say, look, if I point at this thing here, this is it actually happening. And the examples that are often drawn are like, a drone taking off from a roundabout on a playground, and it's kind of like not the same parallel, if you know what I mean. So it's very difficult to describe some of these concepts, and I think this is where the misconceptions come in, because you end up trying to like debunk a straw man.
You can demonstrate it on an escalator. If an escalator moves up and down between 2 floors, if you go with the escalator, you get there much faster. If you go against the escalator, you have to run, and eventually you get there, and you've got to rely on your energy levels to maintain the ability to overcome the speed. But that's essentially the Coriolis argument. So with the escalator, you're going to get there much faster. Against it, you've got to run. Well, it's the same. The same is true for a plane. If the thing's moving underneath the plane, then it has to get there faster if it's going against the rotation. But we don't see that. And ballers just say conservation of momentum. That's not addressing the point, because you're supposed to be arguing for why there's deflection, not why there isn't one.
Yeah, I agree. It's a shit argument to just throw a term at you and say, see, that covers it. But I think what the problem that you have, Anthony, in particular, is that obviously you've been around long enough now to have heard all the arguments, so they can just throw the keyword at you, and then you go, I've already disagreed with that. So, you get frustrated by it, when in actual fact what needs to happen is, particularly people that are experienced in this kind of debating community, need to take a step back and say, look, what can we agree on? Let's start there, and then we can start to talk about the various concepts. So, if at some level there is some piece of Coriolis that is agreeable, then we can say, okay, how can we prove or disprove that Coriolis is a thing on either type of Earth, if you know what I mean?
Okay, well, let's try something that we should be able to agree on. Can we agree that you can't have gas pressure without a container?
I would say that that's a reasonable assertion to make.
Great. So that starting point is the thing that we should all be able to agree on, because you need that container. Now,
however,
then,
I will qualify that. I do consider on the globe model gravity to be my container.
Okay, but then I would say define gravity.
And that's the 4-hour conversation we've just had. So
I know, and it's convoluted and it doesn't work.
It's tricky, isn't it? Yeah.
You need Newtonian gravity to explain it, right? But the current science is Einsteinian, and however you want to word it, right, it ends up being poetry, because Max Planck says, and rightly so, without experiments, it's nothing more than poetry. Well, Einstein doesn't have experiments, so however you formulate the Einsteinian explanation, the considered current position of physics, it ends up being a poetry explanation, which lovely, you can calculate it, and it sounds lovely, and it sounds fantastic. And I'll be honest, there's been a couple of people that have been able to give good explanations for Einstein's stuff, to explain stuff, but it doesn't change the fact that it hasn't got any experiment to support it. So we're back to square one. Where's the experiment that demonstrates gas pressure without a container? So it ends up being a cyclical argument, but really that should be the point where ball earthers go, do you know what? I don't agree with you and I don't believe what you're saying is true, but I can at least accept that it's a cyclical argument, and we're back at base one, where we're saying, where's the experiment? Because that is what defines it. Nobody disagrees that water will boil at 100 degrees at sea level and standard atmospheric pressure, but that's not contentious. But if it was contentious, we can demonstrate.
One thing I am prepared to accept is that there are a lot of varying levels of understanding of the globe model, and the globe model is considered, even by the most advanced people in the industry, to be a complex thing to understand by its nature, which doesn't help because there are varying descriptions of that. What that leads to is misconceptions or badly written statements or quote mining problems. And what I think should happen realistically is that the model is meant to be an approximation of what we believe our understanding of reality is. So what I think needs to happen is that flat earthers need a flat earth model, and then we can compare and contrast the two. But whenever we start talking about models, the common argument that a lot of globe earthers get is that no, models don't prove anything, or models are not reality, or those kinds of arguments. So I think that there's something to be said for having an equal opportunities argument, but you've got to begin somewhere, and we can't obviously at all times be out in the world doing an experiment in real time. We have to be able to sit at our desks and discuss the points outside of that.
Isn't that the purpose of science, though, to do the experiment, so then we can cite it? So at least with Newtonian concepts for gravity, right, you've at least got Cavendish that you can cite as an experiment that's said to prove something. Now, I don't want to go into Cavendish. I'm not going to argue the merits of Cavendish. But the point is that you've at least got an experiment that demonstrates something, and there's an argument that we can have there. But with gas pressure, the only supporting evidence that you've got, apart from the visuals of the planets and what they tell us, is the Boltzmann formula, which is a probability calculator for the way it should appear if there was an atmosphere around the planets and the gradient that would be supported in it. Well, that's lovely, right? But it's not a substitute for the experiment. So it's like...
So what I would say is, if you want an experiment, the way to look at it is to say, okay, if the Earth is a globe, then you have some hypothesis or statement, okay? But alternatively, if the Earth is flat, then you have an equal hypothesis that cannot be true if the Earth is a globe. And then we say, okay,
where's Bev?
let's
suggest-
form
if
an
the-
experiment around that,
Yeah.
basically.
Let me go. If the Earth is a sphere, the surface of standing water must curve. If the Earth is not a sphere, the surface of standing water will not curve.
Okay, so how do we build the experiment that allows us all to unanimously agree whether or not water curves?
Do you know what a
That's what
water
we're
level
trying to-
is?
Well, that's what we're trying to engage Sly Sparkane, because he's got a claim of a water test that he wants to do. Bev's got
Yeah.
a claim of a water test that he wants to do. There's a discrepancy between the two. Sly thinks that Bev's whatever. Bev wants to talk to Sly, he won't talk, because Bev thinks that Sly's test is inadequate and is set to fail. I don't know either way. I'd like that conversation to happen, but for some reason, I don't know why Sly won't talk, but he definitely doesn't want to talk to Bev. Well,
It's fair.
maybe Bev's right.
would-
Maybe
I
his
would pressure
test-
him on that. In fact, as a globe earther, now that I know that that's been presented to him, I would put pressure on Sly and say, look, there's a guy here who's got an equal and opposite reaction to your proposal. Why won't you have the discussion? If the whole point is proving or disproving, let's do it. Let's call everyone on their bullshit. Let's collectively get together and say, look, if you want to prove something, you've got to prove it to your target audience. You can't just block them out.
That's why Bev went on Fight the Flat Earth last night. No one likes Flat Earth on either side. I think we can both agree with that. There's very few people that like Fight the Flat Earth, unless you're a narcissistic, sadistic bastard or whatever. But most people that are interested in the topic don't like him. Yet Bev went on Fight the Flat Earth last night, and he had the conversation with them simply to raise awareness, even though he doesn't like him, and he calls him a child abuser. Fight the Flat Earth calls Bev a child abuser. He was prepared to go on his platform, give out the message and put the flag up to raise awareness to try and get something done, because Bev thinks that there might be something in it and it's worth challenging. But it seems to be met with, well, I don't know, Bev can probably explain it better than I can. I'm not sure if he's here. Bev, are you actually here? No, I don't think he is.
No.
But Bev is trying to get the conversation going, but Sly doesn't want to have the conversation, and he's been invited and he refused. And now when the conversation's starting to happen, now he wants to be in, but he doesn't want to be in with Bev. He wants to be in a one-way unilateral conversation that Bev's ridiculed, rather than having the conversation about whether or not the test is going to do what he says it is. And if it doesn't, can it be modified slightly to achieve something that might not be foreseen right now, but after a conversation might be agreed that it might be a good alteration to achieve something that previously couldn't be achieved.
Yeah. Oh, that's interesting. So, yeah, I never would have thought of Sly as being one to shy away from a bit of kind of, feedback regarding his experiments. And it's interesting to hear that, actually. But, I mean, to be fair, I don't really actively follow Sly. It's been a while. But I think that, yeah, he should be called on that, because that's just bullshit, right? I mean, if somebody's got feedback on something he's actively doing, he should be reacting to that. There shouldn't be any of this kind of...
Normally, Sly will stand his ground and he'll argue, right? I've argued against him in the past and we don't always agree, and sometimes I'll get kicked and booted for a few weeks and whatever. But he will normally stand up and be counted. But on this one, he won't, and he isn't doing. And it's like, what the hell's going on here, Sly? At least when I've done my egg test, anybody and everybody that's challenged me on it, like you did today, I've had the back and forth with them. And even if we don't necessarily agree, we've had the conversation. But on this one thing, for some reason, he just doesn't seem to want to do it. And it's like, that instantly makes it look like he's being suspicious in some way, because normally Sly's one of the better people to talk to. He's good with his, we can have the conversation, but he doesn't want to do it at the minute. Yet he's doing a water test.
Yeah, you've got to have at least an open forum if you're going to do something that, because like the whole point of his experiment is he's not proving to globe earthers that the Earth is round, because globe earthers already assume that or know that from their point of view. What his target audience should be in this case is the flat earthers, and he should be presenting them with something that before he goes out, the flat earthers should say, yeah, if you get this result, I'll accept it. And if he's not giving flat earthers the opportunity to be able to give him that feedback to put him in that position, then he can't argue when his results come in that his experiments have passed the flat earthers litmus test, right?
I agree. There are criticisms on his test. If you watch what he says he's going to do, he says he's going to do it this, then that, then the other. And the first bit he gets right, but the second bit is based on a visual representation of what he says is level. And then the third one is dependent on the second one being accurate and reliable. But there's question marks over it being accurate and reliable because it's visual, based on optics, not based on measurements. And it's what he's assuming that his premise is correct. But the premise is the test that he's trying to prove. But he's assuming that the premise is correct. And we're saying, hang on a sec. Or we're trying to say, hang on a sec. You're assuming that in the first instance, this is correct. But that's actually the thing that he's testing. So you're already assuming that this is correct. So you're begging that your own question. But he won't have the conversation yet. So it's like, and normally if I ask Sly for a conversation, he'll normally agree because he sees me as a jackass and he'll have to come because he likes to apply the ridiculous. But on this one, he just won't. And I don't know if it's because it's me or if it's because it's Bev or is he hiding or what. But for some reason, he won't do it and he should do.
Yeah, it's an interesting one. I just pulled up Sly's YouTube and just looking through it. It looks like the latest video is what he's referred to as flat Earth contradiction, and the opening shot is like Bevan Riley's contradiction or something.
Because we're applying what Rumpus told us was the standard, and it causes a contradiction. And essentially, Rumpus is incorrect, but Rumpus is claiming that he's correct based on the interpretation of the word level. Now, at the end of the day, however you want to interpret the word level, I think when you use a spirit level, or in any context, colloquial or scientific, the word level needs to be defined, and we need to have the agreement on that term so that we can have the conversation based on that term. Now, if you're going to say level is curved, then we need to address it from the perspective that level is curved. But if you say that level is horizontal and level and flat, like we would say, then the conversation is based on that term. But because we were doing what Rumpus said, which was that level is following the curvature of the Earth, it causes a contradiction. Now, you can argue about the merits of the claim that we made, which is what he's doing, but that wouldn't have even happened if we'd have been able to have the conversation with Sly. He's just being a bit of a dick at the minute, and I don't really know why. But if you have any sway with Sly, or you know anybody that does, get him to have the conversation with Bev, because there is a conversation there about his own test, because it's not as good as what he thinks it is, and I don't think it is going to prove what he says it's going to prove. But I don't know.
Actually, I think I've commented on a few of his videos regarding this experiment, and I think I had pretty much the same criticism as you did, is that he can say, oh, okay, it's level, look, it's following a curve, and he could even show that the water curves or whatever throughout his experiment, but then there's probably some argument to be made that it wasn't representative of curvature from the Earth's point of view, if that makes sense.
Well,
and I think that the way that he has to approach it is he has to approach it from a flat earther approved point of view, and at least he should be taking seriously the feedback that you guys as flat earthers are giving him on his experiment. And
yeah, I mean, what he does is he describes it as all of his tubes are all vertical. He gets down one side of it, moves 100 yards back from it, and then looks down the length. And what he's saying is he sets level to the center of his frame so that he looks down it and he sets level, right, with two pieces of tape. But he's doing it optically based on that, right? And he's saying that that's level, right? Now, instantly, they normally tell us that light refracts over distance and it curves.
That's what I was going to say. So immediately, it's the refraction problem, isn't it? Because the flat earthers are going to say, well, it curved because of refraction. And he's going to say, no, it curved because it curved.
In his video, if you listen to how he words it in his video, he's classing that as straight, not curved. So if he goes with it, because he says that gives you a straight and level platform. And then he does it again, I think he says 6 inches above it. And then he says, then you've got two parallel lines. But he's implying that the lines are straight, not curved, straight, right? So then when he puts his water in it, it's going to he thinks it's going to conform to the curvature of the Earth. But he's got his straight line, parallel lines. He's got them based on visuals, which ordinarily they say are curved because light follows a curved path, they say. So we say, well, hang on, how is it straight in the first instance then? Because he's now saying that light's straight while he's setting his water levels, his tapes. And that's a direct contradiction to the refraction argument. But I think he knows that. And I think that, I don't know, I'm preempting him, but that's why there needs to be a conversation, because if you're going to set your ups and downs, your highs and your lows, and your band of your reasonableness for where your water's going to fit, you need to know whether you're going to accept that that's level or are you accepting that it's curved. Because if it's curved, then the water's going to appear level with it, and he's going to claim it's a curve. But if he says it's straight and then he says that there's a curve there, then that means that visually light travels in a straight line and it doesn't follow a curved path. So I mean, it's all to do with how he's setting it up and how he's wording it that needs to be clarified because it's ambiguous.
Yeah, I completely get it, and I completely agree with your argument. Is that it's you can't have it all ways. You can't say, well, it looks flat and it definitely is straight, but like curves. Or you
Yeah.
can't say oh it curves and it looks like it curves, but also like curves. So you have to at some point say, well, okay, here's my definition of control. You have to do it scientifically and say these are my control measures to make sure that curve is actually curve and straight is actually straight. And if he's not going to take it seriously from the proof point of view, then obviously the results are not going to be taken seriously. And I think it might be that, I don't know, maybe he's taken a lot of criticism and he's just like sick of taking criticism over it. I don't know, but
then
he should be called on it though.
But if he does it though, and then he doesn't get the feedback because it's not taken seriously by us, he'll then claim that and nobody challenged him on it. But we are trying to challenge him on it. He just doesn't at the moment. He doesn't want to listen to it. But he is going to claim at the end of it that nobody challenged him on it, and we are challenging him on it because we're not sure what he means when he says the words he says. Then we need the clarity on it so that we can say, hang on, if this is supposed to be straight, how are you addressing refraction and stuff, and challenging him, giving him that critique, but he doesn't want to do it. So it's like, well,
that's how I would challenge him, though. I wouldn't challenge him on terms. I wouldn't challenge him on definitions of words. I would challenge him on how are you proving that curve is actually curve and straight is actually straight. That's what I would challenge him on.
But then that does involve by process. It involves defining terms. So when he says, I'm going to set these with tape and these are going to be straight, what does he mean when he says straight? Does he mean straight as in curved, or does he mean straight as in straight? Because they're the terms that we need to have clarity on so that we can distinguish between the two models and say, if it's this, then it's that. If it's that, then it's the other. But
that's where Bev's test experiment it negates the use of words.
What's Bev's experiment then? Because I've seen Sly's one, I haven't seen Bev's one.
It's basically a water level that's done on a canal, a 2-mile stretch of canal. It's a shame that Bev's not here actually to explain it to him. To you.
A variation of the Bedford Levels one.
No, because the Bedford Levels was just a telescope 8 inches above the water with a flag on the back of a boat. So no, it's nothing like that. This is a water level that's along a 2-mile stretch of a canal. The canal itself is a 21 mile stretch of canal that has no locks in it. So the water is a level plane. We're going to use a 2-mile long water level that has 3 vials in it, one at each end and one in the centre. There are then 2 1-mile water levels. One runs from the centre to one end of the 2-mile water level. The other runs from the centre to the other end of the 2-mile water level. And that basically is it. It will be checked optically for level. And if the water in the canal curves, then the water in the level will curve. If the water in the level is straight and the water in the canal is straight and level, then optically is checked. There is no curve.
So the common example that I like to cite, particularly with long distance experiments, is Soundly. And the way that he addressed this was, whether or not you guys agree, I don't
On
mind.
the Pontchartrain. You mean the Pontchartrain Bridge?
Yeah, so
No, it's rubbish.
He obviously took the photos, right? And everybody said, no.
It is rubbish. It's optical compression. The photographs are optical compression, and the model has been modelled to the photographs. It's rubbish.
Right.
It's absolute tosh.
So he took the photos, which obviously we would expect to see refraction and things like that going on. So to some extent, flat earthers could say, well, we expect that drop because that's part of our model. Yeah. So,
but hang on.
Just let me finish, okay?
Yeah. Go on.
What he then did was he took Jesse with him, who drove along the bridge, and they took the GPS points, and then they plotted the points, and the model that they produced from the raw data curved in the same way. So they had 2 different sources, if you like, of raw data showing that they were curving. Now, there's a lot of obviously disagreement around whether or not you feel that that's a valid experiment. But my point is simply, okay, they were choosing to decide that optical was one source of data, but then there was another source of data, which was the GPS information. Now, obviously, you can say, okay, fine, that's not valid for other flat earther reasons, but this is the kind of approach I would like to see from, say, Slyer's or Bev's experiment, where you can basically say, okay, I'm not just going to trust taking a picture as being the result. We need to show something else as well, because clearly, optically, it doesn't work. Because, you can make a picture prove anything, as the black swan proves, right? We can have the black swan picture, and then you can have the picture from 2 hours before that, and they show two completely different things, and you can infer or claim whichever model you want from whichever picture you want, but they both say both things, so to speak. So you need to have
but hang on,
an experiment that's unambiguous.
That's not what the black swan photo proves, though. The black swan photo proves that the horizon is not geometric, it's not physical, it's apparent, it's optical, it's perceived, and therefore, if boats are going over it, it's in the wrong place. But it's more likely that it's an apparent horizon, not a fixed
There's no geometry to it.
geometry.
Yeah.
That's the word. Geometric.
So that's Quantum Eraser's argument, isn't it? Is the fact that in the Black Swan picture, the horizon is behind both oil rigs despite the distance, proves that the only limitation is to do with sight, line of sight, effectively, yeah?
Well, hang on
No,
a minute.
he's saying that it proves that the horizon isn't a physical place, it's an apparent place. It varies.
Also, if for those oil rigs to be refracted, they need to be refracted over a geometric horizon.
Yes.
Which would put two horizons, one geometric, one apparent, in that photograph. And everybody knows that aren't two horizons.
Yep.
Okay, I think that's
and to claim there is just...
Where'd he go? So I think where the problem comes in here is that from what you guys have said, is that you're expecting there to be one, a geometric horizon, and two, an apparent horizon. But from my understanding of...
Why would we expect a geometric horizon? We don't need one.
Well,
your geometry states that there should be one.
Right. What I'm stating is that on a globe there is on a globe there is the fact of a curve. Okay, on a globe, and that fact means that physically there is drop, which means past that drop point you can't see, and we refer to that as the geometric horizon. But on a globe, you never see the geometric horizon. You only see the apparent horizon.
How come up until January of this year, boats always went over the horizon?
Yes, the horizon. Now, the problem that we've got here is that this concept of...
Forgive me. The adjective used with regards to the horizon is over the horizon, not just the horizon, over.
So, yeah, the point that I was going to raise here is that until probably the last, 6 months or so, when all this stuff around Black Swan started coming up, there was just the horizon. Now there's geometric horizons and apparent horizons. From a globe Earth point of view, there is only one horizon, and that's the furthest point that you can see, and all horizons are apparent.
So that means Galileo was wrong when he observed the boat going over the horizon with his telescope, then? You can see
No, what he was seeing was a boat going over the apparent horizon, which is correct.
Over the apparent horizon, that makes it geometric.
Yes.
But you've just said that all horizons are apparent, not geometric.
So, where I'm drawing the discrepancy here, right, is when we talk about the geometric horizon, you're talking about the actual shape of a globe, okay? You don't see the actual shape of a globe due to things like atmospheric effects and refraction, right? You never see that because there's always refraction present. So what you always see is an apparent horizon.
Hang on. Which children's entertainer, as he is, who am I quoting? Curvature of the Earth Horizon Model of Science.
Bill Nye?
Bill Nye. Curvature of the Earth Horizon Model of Science. This is from his teaching of children, shall we say.
Yeah, this is the paint, the boat on the paint thing, isn't it?
Yeah, I'll drop a link in the chat.
Is it like a little model railway thing, and he like drives it over, and then he gets really low down, and you see the boat disappear
Curvature
over.
model, yeah, exactly.
Yeah. So what you're seeing there, because obviously of the scale of that model, you're not going to have any refraction. That is only geometric. But in reality, we also see an adjustment on that based on refraction. It's an oversimplification, but it is essentially what we see, is it not?
Well, no, it's not what we see.
You're saying you don't see horizons dropping down, disappearing from the bottom first?
No.
What, boats? No.
No,
Sometimes.
we don't. And there's another point here. You keep claiming the geometric horizon based upon measurements. How exactly was a geometric horizon measured or seen to be measured if you can never see it because of the atmosphere?
The geodesy? So these days it's done.
No, you can claim
No.
geodesy, but unless you've actually physically got something to measure or see it to be able to perceive where it is impossible to measure. So how is it measured when you cannot see it? This is what you're claiming, that you cannot see the geometric horizon because of the atmosphere. When was the atmosphere not here in order to be able to see this thing?
Now,
Okay,
when you
so-
answered geodesy, hang on, when you answered geodesy, his question was when was it measured? Geodesy doesn't measure, it calculates as though there is a geoid there. It doesn't measure anything, it calculates.
This is the same calculation as gravity. You're calculating a model,
So
and there is no actual physicality to that model. It's just numbers on a piece of paper or in a calculator.
yeah, okay. So
There's no
I'm not
physicality to it.
I'm not a geodetic surveyor, but this is my understanding of it, and I could be wrong. Okay, you have a known start point, which is a sort of control point, if you like, and then you have like a kind of known end point, which is above, a certain level above sea level, and the line that you draw between them allows you to triangulate that measurement of what you're seeing. Now, obviously, there's going to be a certain.
The problem is they then apply that line to a datum point that is a conceptual geoid that is below the surface of the Earth that they tell us is elliptical. Well, that reference point that they're referencing is a calculation. It's not a measurement, and it's a calculation relative to a conceptual imaginary line that we say, well, it's a conceptual imaginary line, but it's a datum point. So it's not actually measuring anything. It's converting it into a sphere, but referencing a geoid model, a conceptual point that doesn't actually exist.
A presupposed
When we measure it
point.
with normal surveying, non-geodesic surveying, actual normal surveying, it's flat.
So my understanding, and again, I am definitely not a geodetic surveyor or anything, but my understanding is the way that it works in modern times is they're using GPS to triangulate positions. So GPS is well understood and well recognized to be accurate down to, well, it's pretty much as accurate as you want to go.
You need a physical reference, and there isn't a physical reference available, as you cannot see the geometric horizon. You've got nothing even to put there or to find it or be on it. It's all presupposed. This is the issue.
So your physical reference is your base point.
They have attempted. This has been obfuscated the opposite way by saying that these things are all being by the geometric horizon. This is what we were told for the last 4 years. Now the shoe's on the other foot. Now we are all claiming everything's apparent. If it's all apparent, how was it all measured in the first place? And it's all based upon presupposition of all of it.
Well, I would disagree with that. I think you've majorly trivialized the way that geodesy works, and I've not been able to kind of explain it properly to you because partly my understanding and partly I feel like I've been cut off a lot. But it's one of these things where it's like geodesy is extremely complex, and triangulation is not something that I want to go into, because I would quite happily hold my hands up and say, you know what, guys, if you want to call me a liar for any point that I've got on it, fine, you call me that, because I'm not going to claim to be a professional in this area. But I can say for sure, here's the things that I do know, okay? I used to work for the local council. I was responsible for a geospatial data system that looked after a patch of land that was roughly a couple of hundred miles, square miles in total. And we had a point every 10 meters across that entire patch of land. And I, for kicks and giggles, this was a while back, mind, have taken a cut of that data myself and drawn straight lines across it and seen curvature in that data. Now, what that may mean to you is it probably doesn't prove anything, but the data that I was looking at was raw data from the surveyors. How they acquire that data, I could not explain to you the detailed process, but there are people out there that probably could, and you probably wouldn't accept their explanations. So whether or not you feel that that proves something to you, I would probably say it probably doesn't. But to me, I felt that that was quite interesting to see curvature in a data set like that.
Well, that's something we can only take your word for. That is
Well,
actually
that's a similar position that was taken with the hockey stick graph, whereas Ross McKittrick and I forget his partner's name actually wanted the source code for how the data was being compiled, and they wouldn't actually produce it until somebody got hold of it, and they found that whatever numbers you put into that particular code produced a hockey stick graph. It had absolutely nothing to do with the correlation of temperature data that was being received. It was deliberately skewed. So there's a presupposition wrote into whatever's measuring or whatever's happening, because it's presumed. This is what's going on without it ever actually being proven.
Well, again, I would disagree with that, because I've worked with these people and I have no reason to believe that they would lie to me. But at the same time,
no, it's the code that's written. If it's coming out of that thing, it's the algorithm itself which is causing it, not the people putting the data in. This is what I've just said. This is what Ross McKittrick found out with a hockey stick graph.
But I'm a programmer. I had the opportunity to look at the code, and I couldn't see anything that was presupposing any R value. The data was absolutes, X, Y, Z, this point in space.
When you say you're a programmer, whereabouts are you from?
I'm based in Andover at the moment. I've been in programming for about 20 years. I'm a cloud solutions architect.
Told you, Tony. Sorry, we were having a bet on the accent, and I was like, no, he's down my way.
Where are you from, Emma?
I am from Wiltshire.
Oh, brilliant! I was originally from Plymouth, and I moved up here with my family when I was at school or whatever, and I've since obviously gravitated slowly towards London because that's where the work is. But I refuse to go and work in London because it's one of these places where it's like, oh, I really don't want to be there.
No, I hate London. Every time I visit, I'm like, no, I just want to go home again. It's just too
damn
crazy.
Straight. Yeah. Yes, we can agree on something.
Yeah. London is lost. Sorry, yeah, me and Tony were arguing in the background. He thought you had a South Manchester accent.
Well, it's just that you said that you're a programmer. You've got a dialect that's very similar to Mick West. You work in programming, and I'm like, Jesus, are we talking to Mick West again here? But
This is why I say, I'm quite happily, like, if you guys have gathered a set of data or something and you just want me to model it, fine, throw me the data and I'll see what I can do. But,
well, I'll tell you what, we actually trying to put this test experiment, this canal water level experiment together, and it would be nice to have opposing views. I mean, this is why Bev is going on Fight the Flat Earth and who else has he been? He's been on loads of books. He's always in Jose's server. Not only is Bev raising awareness of this test that we're doing, this experiment, he wants to know not what standards the ballers expect, the globe believers expect, but what we need to do to satisfy their requirements as well.
Yeah, damn straight. That sounds good. And it's good that he's reaching out as well, because he's getting the standard for the scientific process effectively, and he's hearing it from the people that are going to most deny his results basically. And that's the only way that you're going to get approval, is to appeal to your opposition effectively.
They're not making it easy though, I must say, especially Sly.
Would you expect them to, in all fairness?
No, I know it's difficult, and I mean, I agree. A lot of places you go, they want you to come in, they'll have a shout and whatever at you, but that's not what we were about here. We kind of like the discussion, and as you've probably heard, we want some feedback and input on this test. So
all the servers that I've been on, like particularly the ones that have flat earthers as administrators, this is probably one of the most chilled out. I'd have to say, because I've been on servers and literally within, I think my record is 97 seconds for being banned from a flat earth server.
oh dear.
And all I did on that occasion was I said, here's a video that was posted by a flat earther that shows curvature of the earth. And I think it was Jeranism's balloon footage from 4 or 5 years ago. And they went, ban. I was like, oh, okay. Because in that footage, it was, and Jeranism posted it. So I thought, well, maybe a flat earther posting it, it would be accepted. But
No, some places you're not allowed, it's like that in some places, unfortunately, but
very
we're trying to
clicky, isn't
do
it?
things. Yeah, we're trying to do things a little bit differently here. Tony, why have you got your camera on? Just in case you didn't realise, you're walking around with your camera on.
Yeah.
But yeah, we try and do things a bit differently here. We try and get people in and actually have discussions rather than the shouting. And obviously we get a bit heated sometimes, and I have to step in and tell people off. Tony.
It happens
DP.
on all servers. I came over here from James'
Yeah.
server. You should hear the rants they have. Jeez.
I know. I can't be in there for too long. I just, yeah.
Seriously, I'd rather lick piss off a nettle than go in there.
Gross.
I think the problem that they have over there, though, is that there's this crowd. There's a group of about 10 globe earthers, and as soon as a flat earther sets foot in there, it's like they descend on him like wolves and just tear him apart. It's like, no, you can't have a discussion if that's what you're going to do, because they're just going to feel alienated and just run away.
Yeah. So as I was saying,
apart, they literally just bombard you with utter shite most of the time, answer nothing, and obfuscate most things. So let's be honest about it. They don't provide any actual answers to anything.
Would you say I've done that today?
I'd say
no.
you've been cordial, and you've not shied away. So respect to you for that, sir.
I've tried to answer fairly what I believe my understanding is.
Well, you said something before which I thought was very telling and very honest. You said belief. And I'm happy with people having beliefs, because you claim these things about globe belief. Well, I'm happy to people have beliefs, yeah? Whichever way you want to be. But when people are claiming to be proven and scientific proof, and it's this, that, and the other, then bring forward them proofs or admit the beliefs. So you seem to be more on the happy to have beliefs, so that's fine for me.
When I'm referring to what is accepted science, and I say I believe this is true, I believe it in the sense that I'm saying I have no reason not to believe it, because I feel that the evidence that I've been presented with is enough to convince me that I'm not just blindly believing it on faith, for example.
You're saying that, but this is the point. Don't try and sidestep it now. You was stalking and taking a believist attitude, which is what this is about. You go and ask any of them others or approach them about belief. They will deny it absolutely all the way. This is absolutely as it is. You're an idiot. So just bear that in mind. You did admit to belief. So, your other lot will hold you over the coals for that.
So the reason why I take that stance is because when we're talking about something as complex as relativity, I agreed with what Tony's stance was, which is it's so bloody complicated. If anyone claims to you that they understand relativity in detail, I would either say, fine, you've got 2 or 3 PhDs and you've been doing this your entire life, or you're talking out of your ass, because relativity is fucking complicated and it requires essentially such an understanding of mathematics that it's not something that the average layman is just going to get, basically. So when we're talking about like Newtonian physics, I can say, well, we all agree that, you know, F equals ma is a fairly trivial formula. Whether or not we accept that and agree on it, that's a different matter, but it's a lot easier to understand. So Newtonian physics is generally what we discuss, but when we move into relativity, there's that, I believe it's true because it's built on a good foundation.
You weren't talking about that particular type of physics earlier when you were mentioning beliefs. So you either said it as an appeasement or didn't realise you'd said it, but it is actually there in the chat.
Yeah, but hang on, we can accept that Einsteinian relativity is complicated, right? But gas pressure without a container is not. You can't have it. So let's concede the gravity point. It's complicated. What's the explanation for having you when you said there's no reason to believe that there's anything wrong with the current system, or however you worded it? Well, why is gas pressure without a container not considered a reason to at least question it?
Whether or not you accept relativity, Newtonian gravity essentially still works in the same way. So that gas pressure that we see in the atmosphere is a fact of life. So I can reasonably say, well, I believe we have gas pressure because of the thing that science refers to as gravity. Now, I accept that there are multiple explanations for gravity with varying levels of detail, the most basic of which is Newtonian gravity, and it seems reasonable for me to accept, and therefore I accept gravity. However, do I understand all of the ins and outs and all of the intricacy that comes with what I'm saying in this? No. I'm happy to say that at some level, I'm taking science on faith, and I'm appealing to authority.
But even if you accept Newtonian gravitation to explain gas pressure without a container, the fact that you can't demonstrate it is an issue, because you should be able to get a smaller mass. And bear in mind that the Earth is a mass. You should be able to get a smaller mass. Add it. Hang on a sec. Just hang on while my dog goes mad. You should be able to get a smaller mass, like a big chunk of lead, right? Put it underneath a bigger mass, and then show that the bigger mass gets heavier because there's a big chunk of lead underneath it, and the effect is that you've added to the Earth's force of attraction below the object, and you've increased its weight. But that doesn't even exist.
I've seen that.
You've seen that?
Yeah. So if you get like a large weight and you hang it slightly above the ground, and under the weight put a set of scales, and then put something on the scales, okay, it'll weigh something, yeah? And if you remove the large weight above the scales, that thing will weigh heavier. And that's mass attracting mass.
Phil, can we see that citation and evidence?
I've seen that myself. I did it during my physics A level.
I've never seen any evidence that a mass above or below a weight adds or removes weight from that weight by its proximity.
Yeah, I'll try it. Actually, try it yourself, because I would love to cite like a source, but I don't think you'd ever accept any source that I cited. But if you did it for yourself, I think you might be surprised.
But is it not reasonable to think that this evidence should already exist in the bank of science, the whole body of science, to demonstrate the point? Because if there was evidence that supported the assertion that another mass above or below a mass can influence its weight, that might have some element of persuasion.
So another example that I've seen is somebody weighed themselves very close to sea level, then took the scales up the top of a mountain and weighed themselves again, and they weighed differently.
Yeah, but that's because the medium's changed. They've changed the medium, but their mass has stayed the same. That's relative density. That's not.
But what is weight?
Well, weight's defined in physics as mass times the acceleration due to gravity.
Right. So if you're further away from the center of mass, then there's less gravity acting on you, so you weigh less. So that's the description.
But you've also changed the density of the medium around you, so I would expect you to be more heavy, more dense, because the medium around you's got lighter, so you should be, relatively speaking, more heavy.
Oh, that's fair. So that's an argument that fits both models. But my previous example of putting a weight above a weight and then it weighing differently, that wouldn't fit your model in quite the same way, would it? And would be more direct proof of gravity.
Hang on, I would say it's actually opposing, because on your model, if you get further away from the center of mass, you actually get lighter because the gravitational pull is less. So I would say it would go the opposite way on your model.
So, which one are we talking about here? The person that weighed themselves?
If you weigh yourself at the bottom of Mount Everest, you weigh X.
Yes.
If you weigh yourself at the top of Everest, you're going to weigh either more or less, according to one or the other of the models.
Yeah, so I've seen a TV show where they did this, and they weighed less at the top of a mountain to the bottom of the mountain, which is what we would expect. Yeah.
That is what you in line with what you would expect. That would be the opposite of what I would expect, because if the density of the air around him gets less dense, he's essentially getting more dense. So I would expect him to be more heavy, not less heavy.
Oh, interesting. So we have an experiment here that we can all independently try and verify for ourselves whether or not we trust the results.
Perhaps, but you'd have to measure the density of the person. How would you keep the however long it takes you to get up the mountain, your mass is going to vary over time, isn't it? Because you're going to lose weight, because you're going to sweat. How would you control that?
Yeah, so the way that they did it, so first they did it with themselves, basically at sea level, and I think it was like on the highest peak on Dartmoor was another example that they tried, and then they went up I think it was one of the Welsh mountains. They went up the top of that, but when they did all this, they took a smaller set of like kitchen scales and a 1 kilo weight, and the kilo weighed exactly a kilo at sea level, and then as they took it up the mountain, it started to weigh a little bit less. It wasn't much. It was like fractions of a gram or whatever, but it was something that they could see because they had sensitive enough scales. But it was an interesting thing to watch.
If you could get a citation for that so you can show us, that would be cool, because I would say that if the weight is going up the mountain, the temperature gets colder, so that its mass gets bigger because metal contracts or expands with heat or cold, but also the air around it is getting less thin, so it's essentially getting heavy. So it would be a balance between the air getting thinner and the volume changing, however much it changes or stretches or shrinks as a function of heat.
Yeah, I'll see if I can find the video. I mean, it was a long time ago that I was watching it, and I didn't think it would be relevant. And so, of course, now I'm kicking myself because I'm thinking, God, if I'd have kept that would have been brilliant.
Yeah.
It was a TV show, I'm sure of it. It was like a BBC thing, and I'm really annoyed by that now. I remember thinking, God, this is really cool. This would be great in like a flat Earth debate or whatever. I just didn't keep it because I thought, well, no flat earther would ever accept that.
12 years later, you end up in a flat Earth debate where you now need it.
It's bloody stupid, isn't it? Weird how the world works. Oh. Do you know what? I'd be half tempted to say, like, let's get a group of us together in here and let's do it. Let's go to like a beach, weigh ourselves, and then go up like a mountain and weigh ourselves. But we'll do the same thing they did on the TV show. We'll have some kitchen scales and like a known 1 kilogram weight, and we'll weigh that at both locations. And we could do it together, and it'd be interesting to like discuss what we think we've observed there. That'd be really cool. And you could do it like as a live stream thing as well.
But the only problem is you'd have to do it at the same pressure at the top. Same pressure, same temperature, same humidity. Because you'd have to keep all the other controls the same, wouldn't you? So that you've only got the one variable.
Oh, that's the problem, though. So the air pressure is obviously going to be different because on Earth we have a pressure gradient in the atmosphere, right?
Yeah, I know, but they're the controls that you'd have to try and control to rule out that they were actually a false positive.
Oh, that's really annoying. Everybody's seen the Brian Cox video in the vacuum chamber.
Yeah. What about it?
I don't know. It's just everybody's seen it, and I think everybody's disagreed with that one as well and what it
Well,
means.
if they could do it in one shot without it being edited, it might mean something, but it's edited. So it proves nothing.
Oh, interesting. Yeah, I've never heard that argument before. I've heard that the results that they got were expected on a flat Earth because of various reasons. I think Tony's given a few today of his reasons and why he would expect them to hit the ground at the same time. Actually,
Well,
no.
yeah, because all masses are greater than zero. The medium is zero, or very close to zero.
But a bowling ball would be higher than a feather, right?
Yeah, but they've still got a terminal velocity, haven't they? Once they get to terminal velocity, whatever that velocity is,
Not in a vacuum.
which is an interesting concept. Interesting concept in itself. Is there a terminal velocity in a vacuum chamber? I don't know. Would it continue accelerating, or does it stop at a certain velocity?
Why would it stop? Why would it have a terminal velocity?
I was going to say, on a globe model, terminal velocity is described as when the air is pushing up, basically, as resistance against the force pulling you down. And so when the two are equal, that's when you hit terminal velocity. If there's no air, there's no terminal velocity.
So it should continuously accelerate until infinity, right?
Or until it hits something, yeah.
Well, yeah. I mean, I don't know whether it would or wouldn't, but it's an interesting concept anyway, because it's like, well, what would happen if you had like a huge vacuum? But in any event, I would say that if the medium is removed, so the medium value is zero, all masses are greater than zero, and there's no air resistance against it, what would you expect?
But not all masses are, say, 1, are they? So some masses will be 1 and other masses will be 2.
But they are all greater than zero, though, right?
Right.
So what would you expect?
So based on my understanding of what you're presenting as your model, I would say if something has a mass of 1, it would fall at a given rate. And if something has a mass of 2, it would fall at a faster rate because it's more dense. It's got more pull.
Yeah, but if you haven't got any air to act as like a brake or as a clutch to slow it down or influence its trajectory for like velocity, then I don't know how you could come to any other conclusion that all masses would fall at the same rate, because there's nothing influencing that fall rate. It's a philosophical question to see what would happen if they were to be infinitely long. Would it continue to gain in acceleration and gain speed? But we have limits, don't we, realistically speaking, so we can't really do that. But I wouldn't expect it to do anything else.
And my view is why, if they're going to be honest with the experiment, then why edit the footage?
I don't think they thought that it would be watched by flat earthers, to be fair, who would be discrediting it on the basis that it wasn't one continuous shot. I think that
if you want to show anything like that, to prove anything, then it has to be one continuous shot.
I think that was the point, though. He wasn't proving anything. He was explaining what we believe has already been proven, essentially.
But if he wasn't proving something, then why the ball earthers cite it as a proof of something?
As a proof, yeah.
We cite it because it's interesting from a globe Earth point of view. But Brian Cox himself wouldn't cite that as proof in a sense, because his argument would be, well, if you want to see the proof, come to the chamber with me, we'll do the experiment, and then you can prove it to yourself.
Well, I've tried to get inside an establishment where it's controlled by science, and Brian Cox happens to be one of the key people in it. It's the observatory, what's it called, Jodrell Bank in Knutsford. It's owned by the University of Manchester. And whilst I was a student, I wanted to try and get in there to see the proof of the radio transmissions to and from Venus, to prove that Venus got an echo, a bounce signal. And I was stonewalled. They just ignored me, even though I was an academic. And I got my dean of the university to try and engage. And she said, I'm the last resort. Come to me when all else fails. But the clock's ticking, and I ran out of time in the end. But the point is that even when I was in education, I couldn't get access to it. But that doesn't seem transparent, because we should be able to get access to this kind of information. And I was just stonewalled, even as an academic.
Yeah, you'd think, certainly in an academic context, you'd think they'd be more open to it. It's hard to say without having been there. I don't know how you presented the proposition to them. Maybe they probably just didn't take you seriously or something, because like you said early on in this conversation, flat earthers are definitely not taken seriously. They're laughed out the door a lot and they're called all sorts of names under the sun. So it's one of these things where it's like, it is highly offensive, but at the same time, if they want you to understand science in the way that they understand science, the only way they're going to get through to you is to say, here you go, here's the evidence, here it is.
Yeah, but they also say that science is not, they don't ever prove anything in science. They're continuously trying to disprove things in science, but the minute you try and disprove something in science, you get ridiculed. So it's like contradictory, directly contradictory.
Funnily enough, yeah, that's one of the points I often make with flat earthers is I basically say, look, if you want to get popular in science, or if you want to prove something, the trick is to prove that one of your predecessors was wrong in some way. But the way that you do that is obviously on scientific grounds, by putting through a white paper that the community agrees is more correct than a previous one. Of course, the problem with that is that first you have to do science on the scientific community's terms, which is tricky for flat earthers, I think, because of the way that they think. The second thing is that once you're
hang on.
Sorry? Was that offensive?
The way that they think.
Well,
How do you mean?
Can we just define a flat earther, please? Because you're defining how people think, and you're labeling them. Can you define that for us, please?
Yeah, so it wasn't meant to be offensive. What I was basically getting at is, like, as evidenced by the conversation that me and Tony have had today, we have very different ways of thinking about what is essentially the same concept. However, the way that we understand it and the way that we describe it is drastically different. And so part of that is because you're inherently using different terminology and different concepts and different ways of looking at the world, you have to define that base level first before you can build on that foundation. And if you're trying to disprove someone like Einstein, for example, you've got to first disprove the whole of the foundation that's built on and start from the ground up, which is a big ask.
Einstein, you consider Einstein as flat Earth, do you?
No, that's not what I was saying.
No, well, okay then. Well, I was asking you to define what you consider a flat earther, because you said flat earthers think differently. Can you define a flat earther for me, please?
So I would say that Tony here is a flat earther.
You would define a flat earther as a Tony.
Okay.
They're great.
Okay,
I don't want to be one of those. I really don't want to be one of those.
Yeah, I don't think I'm one of those either. I wouldn't qualify as a flat earther then, right? There would only be one.
Would you feel less offended if I said globe denier? Would that be better?
Well,
no, but you're trying to quantify the way they think, and this is the question that Bev's asking you. What is it about the way somebody thinks that puts them in your category?
Yeah, so I think it is fair to say that the way that the scientific consensus and globe Earth community thinks of the universe in which we live and the way that a globe denier thinks of the universe are very different.
Well, sorry, like, I know you're saying that, but I mean, you're talking about the Earth, right?
Yeah.
So could we define flat earthers as thinking that level is horizontal, and globe Earth believers as believing that level has a curvature to it? Would that be more accurate?
So that's an example of one difference, I would say. There are many such differences.
That's a great difference, that, though, isn't it? That is the difference, rather than space and all of that stuff that we can't go to.
So, I think this is where the kind of issue comes from, is that first you have to establish what dialect, if you like, of conversation you're going to have, i.e. what set of definitions of terms you're going to use. If you're going to use the globe earther definition of terms, for example, to disprove the globe, you have to, using that terminology, explain why it's wrong. And I think that is a challenge for many globe deniers.
No,
that's where the trick comes
here
in.
We go, right. Flat Earth would sort of necessitate a horizontal plane, or a plane, right? Right, and then globe Earth is a curvature.
Yeah.
Because it's a three-dimensional object, right? It's a curvature in 3 dimensions. The
Yeah.
surface
So from
of a
where you're
sphere,
stood, everywhere is down.
yeah, the surface of a sphere is a 3-dimensional surface, right?
Yeah.
Okay, so you wouldn't say that a sphere has a 2-dimensional surface, would you?
That's an interesting conversation point. Somebody posted that earlier, actually. Wasn't there a Twitter feed thread about it? Was that
Yeah,
you, Bev?
Yeah.
So I literally responded to that my standpoint on it is it depends on the context of the discussion that you're having. You could argue that the surface of a sphere is both 2D and 3D.
Well, you could argue it, right? Yeah, but
Yeah.
the surface of a sphere is 3-dimensional, right? You could express it
in terms of-
mathematically, but in reality, the surface of a sphere is 3-dimensional, right? Because that's what we're dealing with. We're dealing with reality, not mathematical models.
So if I'm an outsider looking in at a ball, basically, I can say, yeah, that's a 3-dimensional thing that I'm looking at. Okay. But if I'm trying to represent, say, a position on the surface of that, I can represent that with 2-dimensional coordinate systems, as long as I have a reference point.
But you think you live on that surface of a sphere, right? So is that surface that you think you live on, is that 3-dimensional or 2-dimensional?
The nature of reality is 3-dimensional.
Okay, so it's a 3-dimensional surface then, right? Measurable curvature.
Yeah, it's measurable, certainly.
Okay, right. Now, when we were dealing with Rumpus and all of them the other day, they said that level is no change in elevation. So how would that fit with you? Right, so that is a curve to you, right?
Yeah, so if I... Right, taking...
How do you have no elevation change but a measurable curvature?
It is a complicated question, isn't it? I can't think off the top of my head of a way of explaining that. I can't think of a way of explaining that off the top of my head in such a way that it would relate to both sides of the community. And that would be
just reality is the only thing that most of us here are concerned in. I mean, I'm not saying about you. You might have a model to fit, but I mean, most of us here are just after knowing what's going on in reality.
I think this is where the bulk of the debate comes from: is how do we measure curvature or flatness? Right.
That's easy. You use a level. Surveyors do it. That's their job.
But then, when they're using a level, they're not measuring the curvature. They're leveling their equipment so that they can line it up with a point.
Yeah, sorry.
Hang on, that's not what you said about Sly earlier. Sly and the Pontchartrain Bridge.
Sly? That's not Sly.
No, not
Soundly.
Sly. Soundly.
Yeah.
Soundly, right. So Soundly's bridge observation. He pointed a camera along a bridge which is deemed to be level by the flat earthers' definition of level, in that it's the same height above the ground all the way, and it is horizontal the whole way, but it visibly curves.
Sorry?
And that is compression, that is optical compression.
Perspective compression.
Yeah, perspective compression.
Right, Mick, that's what Mick West said anyway.
Yeah.
So if I have a pool cue, and I look at it side on and it looks straight, and then I look down it and it looks curved, is the pool cue straight or is it curved?
We've got a curve in it. It's got a curve in it, hasn't it? If it's curved when you look down it, it's got a curve in it, right?
Right, so that's Soundly's argument. He's saying, I looked down the bridge, I took a picture of what I saw, and look at that curve.
No. What Mick West says, right, is the pool cue, the slight curve within the pool cue is magnified by perspective compression.
Yes.
Right, okay. So that picture that we have that Soundly took, now, is there any chance there is any refraction in that picture?
Because most definitely going to be. I mean, he went back there for a whole year.
There is then perspective compression that could magnify that slight refraction into a big curve, as stated by Mick West, right? The perspective compression magnifies a curve, so it can magnify refraction to make it look like it's a curve, right?
Not to forget the 2 panes of glass as well that the photo was taken through, Bev.
Well, yeah.
Sure, I mean, that seems like a reasonable argument on face value.
And you've just said that bridge, by flat earther standards, is a horizontal bridge all the way across.
Yeah, it's what chemo refers to as forced a line in some sense, but not in others.
It's
because
over the water as well, you know. Like
so
you have
if
a
the water
to the water as well, don't you?
So if the water is both flat and level, as per the current argumentational points, then that bridge has been forced aligned by being the same height above water the whole way along. However, if water does curve, obviously the bridge is going to curve with it, because by being the same height above it the whole way along, then it's going to curve, right?
Are you advocating for a horizontal curve there?
What I'm saying
it's
is
horizontal, right?
So yeah, what I'm saying is that if level is in alignment or perpendicular to the center of gravity, essentially, which is the kind of
is 2 straight lines, right?
So I'm trying to second guess everything I'm saying now, because you're questioning literally every term that I use. Level
have to
is
use the terms that you the right terms.
Right. Level is if I have a spirit level and the bubble is in the middle of it, that's level.
Yeah. And like a water level, that too.
Yeah. What that means on a globe Earth is that bubble will be in the middle, and the orientation of that spirit level will be different on a globe. But on a flat Earth, it will be the same no matter where you are on Earth. Would we agree on that?
What about in reality?
So, well, that's where the debate comes in, is which one most closely represents reality, right?
The level is level. That's what happens in reality, right?
So if I pull out a spirit level and I put it on a level surface and the bubble's slap bang in the middle, and then I move 1,000 miles down the road and then I put it on a surface and the bubble's level.
Yeah.
What the discussion point is how do we determine that those two levels are the same level, or they're different orientations of level? By that I mean, because you're 1,000 miles down the road, you've gone over a curve, and that new level is now round a curve from the old level, or it's not.
Right, well...
And I guess the original question that you asked me is, well, how do you measure curve? And I said, well, that's kind of it. That's the point of the whole debate, isn't it? Is determining that.
But you use a level datum to measure curvature from. Deviation from the level is how you extrapolate curvature, right? That's how they work the topography. That's how surveyors work, right? A deviation from the level is either an inclination or a declination, right? The topography of the land.
When you're talking about surveyors, yeah.
So that level is horizontal, provably so, right?
Yeah.
Right, so the water level, the tool that does the same thing, also establishes a horizontal plane of reference.
Yes.
Right, so if that's horizontal, are you suggesting that might curve?
Spirit level, or
like a water level.
Water, so like the bubble in the water level, or just water in general, like a body of water, like an ocean.
Well, yeah, that would do. Like a canal. Let's imagine a canal of water that's filled up.
So based on my understanding of the globe model, I would expect a dead super flat and level canal to curve over distance. Yeah.
Would you?
Yeah.
So you'd expect right. So like a surveyor's level that they look through, the optical one, and say let's say a laser level as well. Let's go high tech, right?
Okay.
Would you say that you're happy with that to be a horizontal
So given that we
doesn't curve, right? Is what I'm saying. When the surveyors are doing that,
so
not
given
like
that we
a spirit
accept,
level, but like a theodolite
yeah,
or a
right.
laser level, right?
Given that we accept in both models that refraction is a thing and a laser is a beam of light, I would say I would expect a beam of light to curve.
Okay, so you'd expect them to curve in any direction, particularly, or just
In
sort
just
of
any direction through atmosphere, right?
I don't know, like up, down, left, right, anything could be anything, right?
Yeah, so I would say any place where you've got atmosphere
So-
and over a long distance you fire a beam of light, you're going to get curvature.
Okay, so
because-
you're throwing out the surveyor's optical laser things as a way of establishing a horizontal plane of reference.
my suggestion would be that that's not how geodesy works today,
Okay.
but I
Okay,
accept
so
your point, yeah.
What would you take for establishing a horizontal plane of reference? Because you're going to see if there's going to be a problem here pretty soon that I don't think you know what a tool is enabled to do that, because you're not going to be able to measure.
Hang on, I've just thought of a problem. If you're going to say that the water over a canal over distance curves, when you look down the length of it, if you see that curving, but that's actually level, does that mean that you have to bend a line up to be able to get level? If you're looking down the length of it,
I don't think there's a way of him establishing a horizontal, Tony. He's just
I
said
agree.
that optical lights are curving any which way. It doesn't really matter. So they're no
yeah, we're
good.
making the same point. How do you get your horizontal level line?
If we're talking about, like, at the point that I'm stood, if I wanted, for example, a perfectly level platform sat on top of a tripod, I could use something like a plumb bob.
That's vertical, right?
Right, but 90 degrees to that is level.
All right, so you're having perpendicular from a vertical is
Yes.
definitely right. Well, is that not what a level tool does?
Yes.
Right, so the optical tool that we've just discussed and you've said is no good. You've just
Right,
said
so
that's the tool that you're going to use.
I'm going to use for what? Hang on, I've been given lots of theoretical questions here and I've tried to answer them honestly.
These aren't theoretical questions, are they?
So when we're talking about geodesy and the way that geodesy works, okay, my understanding is that they have a control point and they have a measurement point, okay, and they use the GPS difference between those two locations to determine what the...
Well, let's go old school, right?
Yeah.
'Cause there was a time before GPS, before we went blip with little buttons, right?
Yeah.
Right.
So what we had before would have been done visually, and there would have been a margin for error due to refraction. But
from
the way
the
that
horizontal, right?
Yes. So the way that you would offset that is you would take more discrete measurements over shorter distances, because then the impact of refraction is much reduced because there's less to refract, right?
Right. Okay. Well, you know, like you'd say in optical.
Yeah.
I mean, do you know what's more accurate than that?
GPS. That's why they use it.
You think GPS is more accurate, right? Give us an idea on how you think GPS works.
GPS is done by computing the distance between control points. And
Yes, and it's based
where
on
are the
geology.
control points? Where do you think the control points are?
well, nothing that you're going to accept, but they are satellites.
Okay. How far away are these satellites?
They're like hundreds of miles up, aren't they?
Hundreds.
I think actually they're like thousands of miles up.
All right. So
It's been a while since I've looked at anything to do with GPS, to be honest.
They measure a horizontal plane of reference better than the tools we can use.
So the way that it works is you get an absolute point in three-dimensional space.
How? Please.
By triangulating your position using 3 or more satellites.
From how far away?
From like 1,000+ miles away.
Right. How does that satellite know how far away you are from it?
The satellite doesn't. It broadcasts a signal.
Right, so that signal goes from the satellite to your phone. Now, how does your phone know which satellite is sending what signal and when it sent the signal and from what direction it sent the signal?
Jeez. So it's been a while since I've done anything with GPS, but from what I can recall from like college courses, like 2 decades ago, to be fair, okay, and I could be wrong, and everything could have changed by now, right? There is a set known frequency for GPS signals, and the reason why we use that frequency is because different frequencies are affected by things like gravity and relativity in different ways, and therefore can be adjusted in different ways. And what happens is the signal is broadcasted in such a way that it states this is effectively the position of the control point. It's at this point in time, effectively, and we take multiple such
Time
signals,
as well.
and yes, time is taken into account. And then you take multiple such signals, you do a load of math, and you come out with an absolute position in 3-dimensional space. And then you can relatively
Three-dimensional space.
Yes, 3-dimensional space. You need
Can I just get clarity on something? Did you say that the signals are affected by gravity?
So you need the 4th dimension to account for adjustments in the relativity stuff. And then once you've done the calculation, you've got an absolute point in 3-dimensional space.
And when it
And
uses
signals
these points, hang on, when it
affected
uses
by
those
gravity?
when it uses those 3 points, it's plotting the references to the a geoid model, correct?
So GPS satellites are obviously around a globe, and the position that you then compute from that is an absolute position in relation to 000, which would be the center of the Earth.
I'm
now
not
the
so
key-
sure that's right, you know. I'm not so sure you've got that right. Because if you can remember when Jesse Kozlowski surveyed that bridge, he got a load of what looked like you said, a horizontal on the bridge. And then he had to hand all of his data over to Walter. And that Walter then made a model that made it match the Soundleys Bridge, right? So that...
Do you understand what happened?
Isn't the 3-dimensional thing that he got the coordinates, right?
Yes. So the LiDAR detector that he attached to the roof of his car on regular interval would have recorded its absolute position in 3-dimensional space.
Yeah. He marked them all. He showed them all. I think we've got a little
it's
video.
Absolute position. It's absolute position based on the geoid model, not based on...
No, it's not based on anything. It's just an absolute position in 3-dimensional space. That's all it is.
Right. But then when it was applied to a construct that had to be created that they called the bridge, correct?
Are you suggesting that they've manipulated the data to make it look like
have a look.
curve on the bridge?
Not manipulated the data. Not manipulated the data. They've made the model match the data.
Yeah.
That's
made a
what
model
I said.
to make the
Match
data
the photo.
match the photo. Yeah, that's what Walter did.
Yeah,
That was
that's exactly what they did.
I'm just
So
uploading
they
now
recorded...
the measurements. I got my lad to blow them up a bit so you can see the actual measurements that Jesse, when he clicks on it and he's showing everyone all of the data points that he puts on there, you'll see what sort of height they are. Then there isn't much different.
And have you noticed how small your sphere would be if you continued the curve of that model, the bridge in that model?
So I'm trying to think about which point to address here, because you guys are throwing a lot at me right now. So what happened with Jesse's data is the LiDAR detector receives the signal, computes the position, stores it into a file, okay? And it repeats that every X number of...
There now.
Yeah, and it repeats that process X number of seconds. What he then did was give it to Walter Bislin, who took that raw data, and he said, okay, I'm going to get the computer to draw a model with those points as being absolute positions in the model in 3-dimensional space. So it's a computer model based on the actual data from reality. So that's our measurement typed in effectively. They haven't changed anything, and then all they've done is they've joined the dots up, so to speak, and that's how they've ended up with the curved line that is the bridge.
Yeah, just going through it now. We're about 5.8 meters nearly all the way across, apart from where the little bridges are, for the raises for getting the boat.
About 5.8 meters above sea level, isn't it, or above water level?
I don't know. Like, it's just 5.8 meters. I mean, that's like he doesn't measure the water underneath and give you a distance to the bridge, or he doesn't really do any of that. He just puts the thing on his roof and then drives across the bridge. But these are all the measurements, like 5.81, 5.8 whatever, and then he turns it round and he goes back the other way. They're all like 5.8. So, you're saying, do you know that, right? Do you know much about logic and logical fallacies?
I've been a programmer for 20 years, so I'd say I know a fair bit about logic.
So you start at one end of the bridge and you go to the other end of the bridge. Now, you've got a supposed curvature, right?
You can presuppose one if you like.
No, Walter got it in his diagram, right? So the model that Walter made has a curvature, right? And although it goes 5.8 all the way across this, how much difference in the middle, like from the two endpoints, it goes up in the middle, doesn't it? It has to, right? Because the two ends have to stay level, so you have to have a raise up in the middle. I mean, it sounds ridiculous because it's not logical, but I mean, that's what you have to have in your model, right?
So if you draw a point, if you draw a line, shall we say, between a start point and an end point, then the arc that goes above that is the bulge that we often describe. But from the start point, that whole curve is dropping away from you. Right, it's just an orientation thing.
Okay, right. So then, well, let's take this bridge for instance. Then 20 odd miles, is it 23?
24, isn't it?
I don't know. I thought it was let's say it's 20 miles, right? It's 20 miles from A to B, one end to the other. So are we going to draw a straight line there? Yeah, we're going to call that because it's on the water. I'd call that a horizontal plane of reference on the water, right? So you go from A to B, 20 miles, boom, straight line. That okay with you?
So if you drew that line, and then obviously traversed the bridge, the line that you originally drew would go through the water.
Okay, so you would call that a chord then, right? Cutting through the middle, and there would be a raise in it where you would call that a sagittar, right? That would be a height of above it, like from the chord to the radius in the center. Is that what you're imagining now?
Sure. So you're talking about the difference between that straight line that you drew and the arc above it.
Yeah. Right. Yeah. So across that bridge, that when Walter did his thing with Jesse, do you know how big that middle bit was?
Nope. I haven't looked at the raw data.
Would you have a guess? Go on. What would you guess for your model? Or your model, Walter's model, or the model that Walter came up with? Let's say.
I don't know if flat earthers or globe deniers are to be believed. I don't know, 8 inches per mile squared, but it's probably not quite that.
20 odd miles though. So what would that sagittar be at the halfway distance? That like you imagine to drop, but you've just said it's a sagittar and it's rising. So, like how would you do that? Because this is a bridge, right?
Yeah.
You're not going downhill on this bridge, are you?
Right, I'll be honest with you. I haven't seen the raw data. I haven't criticised it. I've just said, look, this is what they've shown. Do you accept it or not? And that's on you guys.
Well, it's like I've just done all of the Jesse bridge measurements, and it said 5.8 near enough all the way across, right? So would you be surprised to hear that Walter's model has a 24.5 meter sagittar in the middle there?
No, I wouldn't be surprised to hear that.
Well,
that would sound
you said
reasonable.
You were good at logic, right? Now,
Yeah.
If it goes from A to B all the way across and has a 24-meter rise in the middle, now imagine the bank along one of the sides, and put like go 10 miles one way and 10 miles the other way, and draw a line there. Can you see the problem? Because you might have a 24-meter rise at the end of where the bridge starts, right? That isn't there when you
like
do your calculation the other way across.
So you're saying take our original straight line and then above that draw a peak to a triangle, essentially.
No, I'm saying that it's a fallacy. It can only be horizontal. There is no curvature possible.
I don't know how you came to that conclusion, but yeah, okay, I can accept that you would deny it.
No, you can't demonstrate it. Because do you realise, like, if you were stood at the one edge of the bridge and there was a sagitter at the middle of the bridge point that was 28 metres high, right?
Yeah.
How much do you think you get to see of the other side of that bridge? Do you think you'd be able to see a water tower 4 miles past the other edge of the bridge?
If you're like at the level of the bridge, so to speak, taking a picture, looking down the bridge, yeah, you're probably not going to see much at all. But the photographs that Jesse Soundly takes are not at the bridge level. They're like 10 floors up or something on a hotel, aren't they?
Right, so they're at the sagitter then, right? They're getting up to the height. Are they 28 metres high?
I would probably say that they would be a lot higher than 28 metres because they're... I think they did try and get access to the roof of the building, but the hotel wouldn't allow it. So they just tried to book a room that was like on the highest floor that they could get on the day that they did this.
Okay, so that...
You'd have to... I can actually ask Soundly directly about this if you want. I do bump into him on occasion and talk to him about this stuff. I PM him regularly on Discord and ask him questions about it.
Ask him how much curvature he would imagine there to be on the surface of that lake.
Well, he's just going to respond, well, look, I pictured it, I've GPS'd it, so that much. Do you see what I mean? It's not like... He's not going to turn around and say, well, I expect there to be X, but there was actually Y. He's just going to say, look, I've taken a picture of it. That's how much curve there is. I was there.
Right, so he thinks that a horizontal plane curves.
From his point of view, he knows a level line on Earth isn't a plane, it's a curve. That's from his point of view, though. I'm not suggesting that, I'm not imposing my views or anything on you, or I'm not saying even what my view is. I'm just saying from Soundly's point of view, he's justified in saying, look, I've actually pictured and driven along and taken LiDAR data for that curve. Okay. And so if you still don't believe it, you're crazy, is probably what he would say.
You think level is subjective?
I think level on a flat Earth is... There is only one way is down, so level is a dead straight line. I think level on a globe Earth is not a dead straight line, it is a curve.
Okay, so not perpendicular.
Perpendicular to centre of gravity.
But perpendicular is two straight lines. You're not imagining one of those straight lines curving, are you?
So when you're talking about level on a sphere, you're talking about
perpendicular at the minute. I mean, that's much easier
we're talking
to
about,
define, isn't it? Than level.
So yeah,
but
just level
to curve.
Level is equidistant from the centre point of a sphere.
No, it isn't. That's what you call the circumference of a circle.
Okay, if I have a wheel and I deem it to be perfectly round, it's deemed to be level all the way around.
Who's deemed that? Have you been talking to Sean?
No, it's not. It's never, ever, ever, ever been described as level.
That's by Sean Hufford. Yeah, that's his thing. That is that who's told you this, or is this just what you imagine?
Oh, this is just commonly accepted terminology, as I understand it.
No, it's not. Like you must have either heard that from someone or just imagined it yourself. You've never heard any professional or anybody ever say that level is a curved line.
I heard that on multiple occasions during my A-level math class.
Level would go in the skip. It is of no use whatsoever.
Okay, that's a different kind of level.
What do you mean a different kind of level?
So your implication is that level, there is level, which is a table is level, okay? And there is level, which is
that's a table.
This is
A
equidistant.
table's a table. A leveled table would be level.
Absolutely.
Okay, we're just quibbling terminology now. I don't.
No, you're not. You're not quibbling
very
terminology. You're literally changing the definition of words because it doesn't suit your premise and argument. That's literally it.
But I've not presented any argument. I've literally not presented. I've just been barraged by questions, and I don't even know what the point of this conversation is. You're just arguing the definition of level with me at this point. I don't even know what
I'm not arguing a definition of level with you. You're the one that's denying the commonly known facts that level is horizontal.
Okay, the engineer that built the Lake Pontchartrain Bridge will argue that that bridge is level all the way along.
Yeah, he'll know it's level
because he
all
didn't
the way
build any
along.
curve into
Because
it.
it is.
Absolutely agree.
Yeah, and all the way along that bridge, he would have used a spirit level to build each section.
Wouldn't. Don't be ridiculous.
Or some equivalent.
Yeah, like
a digital one,
like
probably.
A water level, probably. He
would have used some form of
water level of the lake tremendously.
He will have used some form of level to determine that that bridge is level all the way along. What I'm saying is, what Soundly has taken a picture of is a bridge that is seemingly level and going over a curve. That tells you something about the definition of level.
No, it doesn't.
Optical compression.
Like, level is horizontal, and just because Soundly's took a picture doesn't change the definition of level.
Okay, I'm saying to you that the engineering definition of level is not what you guys think it is.
Yeah, yes, it is. Absolutely, it is. Having worked in engineering and lots of other things and known lots of people, level is level. Even the most basic 7 or 8 year old schoolboy girl knows what level is, and it's not what you're pretending it is.
If you say so.
What sort of practical experience do you have of this sort of thing?
I'm just more than happy to disagree with you guys on this.
Keep
Obviously, we're not
using
going
a
to come
spirit
to
level. Is that your limit of knowing what level is?
I'm saying a spirit level is a classic tool that is used to determine level at the current
it's like a brickies
point.
tool, really, isn't it?
Yeah.
You do agree with the law of non-contradiction, don't you?
Sorry, at what point have I contradicted myself?
By saying that level is curved. You don't think that's a contradiction?
Level is perpendicular to the center of mass. So
say it. Level is curved in your world. Say it. Admit it.
On a globe Earth, yes, level is a curved line.
In other words, level is curved, and you don't see any contradiction in that at all. It's fine.
That's because by your definition, level is equal to flat.
Not by my definition. It's what it is.
Just have a look in the live stream for us, will you?
Yeah.
That's definition 10 of Euclidean geometry, and that is the definition for perpendicular.
Yeah.
Right. Straight lines all the way, right?
Yeah.
Right. So
when I say perpendicular to the center of gravity, if the Earth is curved, then so is level.
But it can't be, because perpendiculars are straight lines, as defined. You just said it was perpendicular, and perpendicular are straight lines, not curved lines. So, is it an imagined curve, or do you actually have some sort of proof for it?
Sure, I mean, that's you've quoted a definition from somewhere there. Great.
That's
Okay.
Euclidean geometry definition. Do you have another definition better than Euclidean geometry? Definition of straight lines?
In the context of a three-dimensional object such as a sphere, define level.
A horizontal plane. Level doesn't change whatever the object is. It will be level. You understand that when a water level goes, right, it doesn't care what the underneath of the container is, right? It will always have a level surface.
I'm actually talking about Euclidean geometry here. I'm purely talking about spheres. Yes. What is level in context when we're talking about spheres?
In Euclidean geometry, level, horizontal and vertical and plumb are real life terms, right? They're not in Euclidean geometry. It's not stated. They are known as perpendiculars, though. Plumb, level, vertical and horizontal, right? They are perpendicular, and perpendicular within Euclidean geometry is known as two straight lines.
Do you know what perpendicular is in when you were talking about circles? Do you know what the perpendicular reference is in circles in Euclidean geometry? You've got the radius as one straight line. What's the other straight line? Are you going to say it's the circumference?
The circumference isn't a straight line by definition.
No. So it can't be perpendicular then, right?
So if something is equidistant from the circumference all the way around, it's level.
No.
But is it straight? Because you need a straight line for perpendicular, right?
So if that circle was like fucking massive and you were looking at a very small segment of it, it would appear to be pretty much straight, yeah.
Wouldn't be straight though, would it? Wouldn't actually be straight.
But when we're talking about things like geodesy and the shape of the Earth, level is, for all intensive purposes, appears to be a straight line, but it isn't.
Well, if it's perpendicular, like you say, it is as defined within Euclidean geometry, as in perpendicular. Right? We are using Euclidean geometry, are we?
Sure.
Yeah. Well, then perpendicular is two straight lines. It's there defined for you.
But
surely you can't just go round that, can you?
Yeah, but hang on. My question hasn't been answered. It's been given an alternative, but there is an answer. In Euclidean geometry, relative to a circle, there is two straight lines that we can call perpendicular. One will be the radius to the center of the mass. What's the other one? It's not circumference.
It's not the center of
You're
mass.
thinking it's the diameter then?
Nope.
What, the radius is perpendicular to the diameter?
Tangent.
Oh, tangent. Tangents are straight lines, yeah.
Yeah. So when them two straight lines meet at 90 degrees, when the radius meets the tangent line, that would be perpendicular within circular geometry, right? The question is, are we living on the tangent or on the circumference? Now, if we're going to demonstrate that we can show curvature, we need to create the tangent so that we can show the drop from it. But if you're telling us that water level isn't level, how would we create the tangent to demonstrate the curvature for which water must curve away from? How do we do that?
Yeah, I mean, that's the question I've been asking all day, and that's essentially what it boils down to. That's where the dispute is how
No. It's not
how can
where
we agree?
The dispute is, because
What do you
you've
mean?
just bent a straight line.
So, hang on, that wasn't the question. The question was about that water, determining whether water curves or is flat.
Mm-hmm.
Okay, so
Is it perpendicular?
it boils down to, can we measure whether or not it's curved or flat?
So, can we tell, is there a difference between a straight line and a curved line? Is that what you're saying?
Yeah, in reality, the lines that we have over a long distance for a body of water, we have lines, right? And the fact is they are either straight or they're curved, right? That's just a reality. That is a fact. We can all agree on that. The problem is, how do we measure that when we can't trust what we see or what we can take pictures of because light bends? So you can't use light as your mechanism for measuring anything. So you have to try and find some other way, right?
Yeah, so in real world, we will put a straight line against something and say, is it following that straight line or is it moving away from the straight line? So the question is, how do we get a straight line? We would say a straight line would be a water level, the 2 points between which water sits. But you say that's actually the circumference.
Yeah,
Well, we want the tangent.
Have a read in the
to
live
get-
stream, just to get up
Yeah.
to speed if you don't actually know. What
No,
water...
Tony's right. No, Tony's right. So yeah, in one model we're saying what flat earthers are expecting is the tangent.
Yeah. Is
and
that a flat Earth model then? That when Wikipedia modelled the water level as a tool, a device.
I guess, Bev, what I'm getting at
flat
is that Bev, what I'm getting at is quibbling over the definition of level proves nothing. What we need to focus on is how to measure.
Just have a read of what a water level is, please.
Seriously, I don't see the value in this argument.
You don't see the value in having a tool that establishes a horizontal...
Maybe that's the problem. Maybe the problem is that you don't see the value in it. And maybe, just maybe, perhaps, there might be a value there that you didn't realise was there before you looked.
No, what I'm getting at is quibbling over the definition of level and throwing lots of dictionary definitions at me and saying, oh, is this your definition? It doesn't change anything. The problem is in the measurement.
Practical tool.
Yeah. Yes, the problem is the practicality. The water level device that you keep repeatedly quoting is not something that's designed to work over a long distance unless you want something that follows the shape of the Earth. The problem that we have is not following the shape of the Earth. The problem is determining the shape of the Earth.
I'll read it for you.
Did you know water levels are actually more accurate over distance?
Yeah, water levels have been used for many years. The water level is a lower tech than the laser level, but it can be more accurate.
You're missing the point.
Over long distances and works without a sight line.
Can you please at least listen to my point? The point that you're missing...
Did you just hear that, though?
The point that you're missing is that we've already established that
He's not going to acknowledge you, Bev.
Water conforms...
He won't acknowledge that he heard you read that definition to him.
Yeah, I know. It kills it, doesn't it?
He does.
It's bad.
Water conforms...
Are you going to acknowledge, Bev, that you heard the definition that he read to you? Just do him that courtesy.
Fine, I acknowledge it. What's the point?
Well done.
What's
the point is there's some value in the definition, and I would suggest that you've missed it because you spoke over him at the crescendo, and perhaps it would be polite if you allowed him to finish it off, perhaps by saying it again and listen to what he says.
Go for it.
Okay. Water levels have been used for many years. The water level is lower tech than the laser level, but it can be more accurate over long distances and works without a sight line.
To establish
a horizontal plane of reference.
Nope.
In the beginning bit, a water level is any device utilizing the surface of liquid water to establish a horizontal plane of reference.
No, that's where you've gone wrong.
What do you mean? I've just read that from the thing. I read it. I didn't make that up then. I read it.
So the problem that you've got in the context of the discussion that we're having...
I've got with you.
Can I finish a point? The problem that you've got is that in the context of the discussion that we're having, if the debate is the shape of the Earth, we all agree that water conforms to that shape, whatever it is. So having something that conforms to that shape as our guide doesn't prove anything.
No, we don't agree that the water conforms to the surface of the shape of the thing that we're on, do we? Or do you just imagine that? Like, because
No, we don't. We don't agree that. That's not agreement.
No, I don't agree.
You don't agree to that?
no,
So
'cause it
what?
doesn't.
so-
Water
the slide.
establishes a horizontal plane of reference. Always, every time.
Right. So your argument
If it's
is,
not,
if the Earth
if
is
it's not
flat, water's
horizontal,
flat.
it's flowing downhill, right? Doesn't flow uphill,
Yes.
even though you're Xanax. But some people believe that they have rivers flowing uphill. But like
Okay.
water flows downhill to find its level, right?
Let me reword what I was saying, okay? Because clearly you've misrepresented what I was getting at. If
But
you
all three of
believe,
us.
yes. If,
Okay, not that you said it wrong.
okay. If you
'Cause
believe,
we misrepresented what you
seriously,
said.
man, stop talking over me. If you believe that the Earth is flat, then do we agree that water runs downhill and then falls flat?
I see mountains and valleys. That's the topography of the land, right?
It's
That-
a simple question.
That's
Water
not.
finds its
Listen,
level,
no, let me
yes or no?
finish. Let me finish. It's quite important. This, right? The water flows down that to find its level, right? So that bit isn't flat. It's got lumps and bumps on it, right? But the water is level, and level is a horizontal plane of reference. Okay. Can we move on from there and stop saying that the Earth is flat? Because the Earth is the land that you walk on, and it's got lumps and bumps on it. It's not flat. Okay? We're just dealing about level here. Not Earth, just level. What shape do you think level is? You think it curves. Have you got an amount of curvature that you figure into your level? I say
have
it's a
never
horizontal
heard.
plane of reference, so I don't have any curvature to my level.
Right, I have never heard of anyone that in the globe denier community that would deny the comment that water finds its level.
Okay.
And level is a horizontal plane of reference.
On both models, whether it be globe or flat, we
In
all
reality-
agree that that statement is true.
So in reality, the water level is a horizontal plane of reference.
Plane of reference. Well done.
Thank you.
This man, what's his name? Waddy, when I think he's got it.
So here's the thing, right? We all agree that water finds its level. The
And
problem
level
is
a
we
horizontal
disagree on the
plane of
definition of.
reference.
You disagree with me on the definition of level, so you can't use water as your measurement because we don't agree what level is.
Where is your definition of level, please?
I'm not having that discussion again.
You just say we disagree on it, right? If we don't know what your definition is, then how do we know you disagree?
Okay, my definition is the same height as something else.
How are you measuring your height from a horizontal plane of reference?
Doesn't matter. That's my
it does.
definition.
So, like, if you have the same height, that's how surveyors work, right? That's
Yeah.
how they would establish a level.
Yeah.
Yeah, well, it's a horizontal plane of reference then, right?
That's
'Cause,
what you're claiming. That's not what I'm claiming.
Oh. Well, so you could have a 4-foot guy on a 2-foot stool, and that would be the same height as a 6-foot dude. You'd be fine with that, would you?
If you could draw a straight line and they were equidistant all the way along that line from the earth below them, then
From the
yeah, that
line
would be level.
underneath them,
Yeah.
parallel lines.
If those two lines were parallel, then yes, they would be level.
And if we was to add a third person in, would they be on the same line?
That's the
same
point that I've
height?
been making. Is
What is?
in your definition of level and my definition of level, those heights would not be equal. The person in the middle would not be between those two lines.
So a difference in elevation then? You talk height, you mean in elevation when you say height, right?
So elevation is distance above sea level. They would be the same distance above sea level, but on a globe, those lines would not be straight. They would curve.
But the same elevation.
Yes.
Above
and
a
they would
level.
also be, and they would be level. Yes.
But that would mean level would be curved, and level isn't curved, is it?
Which is the point that I've been making.
Plane of reference. No, we just
We can't agree on the definition.
It was horizontal.
We can't agree on the definition of level, so it's pointless.
That didn't take long.
Well done. We've just wasted an hour playing word games. We've achieved nothing.
No. You're trying to play word games. We've been the same all the way along. Level is a horizontal plane of reference.
Yes, that is your definition for a level. Thank you.
That's not Bev's definition. But that's not Bev pulling that out of his arse.
How many definitions of level do you want? Because Google cites at least 6.
How many of them mention horizontal?
Some of them.
Some of them. Are you going to pick one that doesn't? Are you? Let me say, like, stipulations. You can't use Merriam-Webster.
Hang on. Okay, of the 6 definitions, 3 of them mention the word horizontal.
So half of them.
Yeah.
Do the other half mention curvature?
Let's have a look. They talk about leveling the ground and to have an even surface.
Even. Doesn't sound like curvature, does it?
No, not really.
If something is even, you could argue that it's equidistant from something else.
You could argue it, but it's not saying equidistant. It just says even.
Sure. Here we go. A position on a scale of amount, quantity, extent, or quality. As in a high level of unemployment.
What about on the level? That's a good one, isn't it? Have you heard that? Means to be honest.
Yeah. What I'm saying is that there are different definitions of level, and there are different contexts in which the term is used.
Did any of the definitions you found have the word curved in it? Which is Bev's original question.
Find a mathematical definition.
Out of the 6,
level, flat, even, plane. That would be the best mathematical one. Would be a horizontal plane, right? That's about as exact as you could get with level, mathematically. It tells you position and shape or flatness, doesn't it? It tells you a hell of a lot. A horizontal plane tells you way more, doesn't it? And vertical is perpendicular, so like it even